Guys, sir, good morning. Tiwari sir, good morning.
Very good morning.
If you feel we can start around 9:40.
Good morning, Dr. Virendra.
Good morning.
Yes, sir, please, you can start, sir.
Okay. Very good morning, everyone. This session is special as one of the very much accomplished young scientists will be presenting the work for which he has been considered for Krishnan Gold Medal award this year by Indian Geophysical Union. KM Srijit is working mainly on the geodetic data and addressing different geophysical problems. And today we plan to speak on the geodetic data for the understanding of hazards in the Himalayan region. Srijit, it's over to you. Please start and keep the time.
Okay, thank you, sir. Can you share the presentation from your side?
Yes, sir, one second. One second. Yes, sir, you can continue.
Yeah, thank you very much for the introduction and a very good morning to all of you. So today I'll be discussing the applications of the space geodesy, particularly the interferometric synthetic aperture radar for understanding the earthquake cycle and related seismic hazard in the Himalayan region. Next slide, please. So I'll start with a brief introduction to the INSA technique and its applications, and moving on to the earthquake cycle and the Himalayan in the Himalayan region and the related seismic hazard. So I'll be mostly talking with special reference to the 2015 Gorkha Nepal earthquake, and also slightly brief on the recent work on 2019 Mirpur earthquake in the northwestern Himalaya. Please go back. Yeah, Himalaya and its source characteristics. So moving on to the first session, that is interferometric synthetic aperture radar, which works on the principle of the famous Young's double slit experiment. That experimental setup is shown on the left side. So two coherent light sources can produce an interference fringe on a screen put onto the right side as shown in the image. And one of the important property of this interferometric technique is that the phase difference at any point on the screen could be expressed as a function of the effective distance between the sources S1 and S2, as shown in the equation here. Now, in the case of a radar interferometry, the two sources are the radars put on satellite, SAR, that is a synthetic aperture radar 1 and 2, and which is made to look at the ground in a side-looking ways. And here the screen is the Earth's surface. And the two radar images could be allowed to interfere. It produces an interferometric fringe. Next slide, please. Yeah, so the phase of the interferometric fringe so produced is sensitive to two parameters, two primary parameters. The one is the topography itself and the change in topography. The change in topography, nothing but a deformation that or due to any earthquake, volcano, or any other phenomena happened between the time T1, the image, the time of the image taken 1 and 2. So normally few days apart, we get the next image. So if you have a time series image, we can map the deformation. The beauty of this technique is that the phase change is sensitive, more sensitive to the differential topography or the deformation rather than the topography itself. So this technique can able to measure the deformation to a level of few millimeters at the satellite height along the line of sight of the satellite. So the difference between the GPS is that here the measurement is in a one-dimensional along the line of sight of the satellite. But the same technique could be used to map the topography with an accuracy of few tens of meters. Next slide, please. Yeah, there are a lot of applications for the INSAR, both in the environmental science and the geophysical science, the solid earth geophysics. So it could be categorized into the tectonic processes, the earthquake cycle, volcano deformation, landslide, and so on, and the non-tectonic process like the groundwater abstraction, mining, underground explosion, and reservoir loading. So the minute deformation or the subtle deformation of the surface could be effectively mapped. So the left side image shows a global uh, earthquakes map using selected earthquakes, shallow focus earthquake mapped using the INSAR technique. And the right side two images are two our own examples where we use this technique to study the deformation happening at a volcano, the Barren Island volcano, and to estimate the source parameter of the 2017 North Korean nuclear test. I'm not going to the details of the study. Next. Yeah, coming to the topic, the earthquake cycle. The concept of earthquake cycle was developed based on the elastic rebound theory put forward by Harry Fielding Reid after the 1906 San Francisco earthquake, which essentially suggests that the earthquakes are results of sudden elastic rebound of previously stored energy. That means the earthquake cycle consists of three different phases: the interseismic phase, where along the faults, the seismic energy is slowly accumulated and which will be burst as a earthquake, giving few meters of deformation, that is the co-seismic, and there is a slow relaxation in the post-seismic period. So if you see the time bound to that, in centuries time, the earthquake, the interseismic deformation happens, and the elastic strain energy will be stored in few seconds during the co-seismic phase, and there will be a post-seismic phase for few months to few tens of years. So the manifestation of the earthquake cycle process subsurface is a surface deformation, and geodesy could be effectively used to probe the earthquake deformation cycle and thereby to understand the processes. And for over the last 25 years, the INSAR, both INSAR and GPS has revolutionized our understanding on the earthquake cycle. Next. Coming to the Himalayan tectonics, the earthquakes in the Himalayan tectonics as a result of a geological processes, as we understand the continent collision that happened almost 50 million years back and still continues. And half of the India-Eurasia convergence is stored as the strain energy at the plate interface, that is the main Himalayan thrust. The geometry of the main Himalayan thrust on a south to north section is shown on the bottom figure, and we can see that most of the earthquakes are a result of the strain release at the main Himalayan thrust. And if you look at the Himalayan earthquakes, there are two kinds of earthquakes. The great magnitude earthquake, that 8+ magnitude, which can rupture all the way. It can start deep in the main Himalayan thrust and rupture all the way to the Himalayan front or the main frontal thrust. Can you please click once or twice? Please click twice. Yeah. So these are two kinds of earthquake. Then 8+ magnitude earthquake typically reaches to the surface. So there are several examples like the 1934 and 1950 earthquake. And most of the moderate earthquake or larger magnitude from 6 to 8 are confined to the within the main Himalayan thrust without any surface expression. One exception would be the 2005 Kashmir earthquake, which has short-circuited and expressed of the and created the surface rupture. So today we'll concentrate on the earthquake cycle with respect to the Nepal earthquake. Next slide, please. So these are the core seismic deformation field measured using the INSAR and GPS. As we all know, the 25th April, very destructive Nepal earthquake initiated in the Gorkha and ruptured the fault plain up to the Kathmandu, almost 140 kilometers, as shown by the earthquake epicenters. And the INSAR could image the surface deformation, and it suggests almost 1 meter uplift towards south near the Kathmandu and an equal amount of subsidence or the negative Eloise deformation towards north. And on 12th May, the earthquake rupture, there is a major aftershock of 7.3 that could also image using the INSAR technique shown on the right-handmost side. Next image. Yeah, this is a compilation of the INSAR measurements with the co-seismic deformation and snapshots of post-seismic deformation from 4 days up to 3 months. And a section from AB is shown here, showing the co-seismic and post-seismic deformation, which suggests that the post-seismic deformation is opposite in nature, in polarity compared to the co-seismic deformation, suggesting that most of the slip is towards the post-seismic slip is towards north. Next slide, please. We use the geodetic data to understand the slip on the main Himalayan thrust, and the geodetic data were inverted to understand the distribution of the slip on the main Himalayan thrust. As we can see, the maximum slip is around 6 meters, that is somewhat 80 kilometers east of the epicenter on the deeper portion of the main Himalayan thrust between a depth of around 10 to 15. And the right side image shows a 3D illustration of both the surface deformation and how it has slipped on the main Himalayan thrust. And it's very important to note that the slip is confined within the ramp or the mid-crustal ramp, but we say within the deeper region of the main Himalayan thrust without propagating towards south. And another interesting fact is that the earthquake did not rupture towards west, and it's a unilateral rupture propagation. And there are several hypotheses why it has happened so. So the majority of the people think that it is because of the structural discontinuity which has arrested the rupture towards propagating west. And this has implication in the seismic hazard as well, because in the co-seismic period, the southern portion where the strain maximum energy is there is not ruptured. Next. So we invert for the post-seismic period also the post-seismic slip, and you can find that the post-seismic slip is confined to the north of the main rupture as shown in the left period, and this is a very early post-seismic slip of few days to few months. And recently we have looked at the long-term post-seismic deformation almost 4.5 years using a time series INSAR technique, and which is shown on the right side, which suggests that even at the post-seismic period, the slip is confined to the north, and maximum slip and the time series for a point is shown on the right-handmost image, which shows that there is a rapid after slip and then got stabilized after 2.5 to 3 years. So the point to be noted here is that the huge stress transferred during the co-seismic slip is not relaxed, especially towards west and towards the southern side also. Next. So the third phase of the earthquake cycle is the interseismic deformation, and we attempt to constrain the interseismic deformation happening on the Himalayan front in the central Himalayan region using almost 15 years of geodetic data, both GPS and INSAR. So the horizontal velocity is what we get from the GPS is shown on the left top image, which we can clearly see that the higher Himalayan region has larger velocity as expected, and a model is shown as the inset map. And INSAR is more important in Himalaya because it can give the spatial distribution of the deformation, but it is equally challenging due to the steep topography. The INSAR measurements are really challenging. So the only two reliable measurements so far happened using a previous study using the NVSAT data that is shown on the top, the bottom left, and our own data using the LOs. And both the measurements are using a time series INSAR, which suggests almost 6 to 7 millimeter per year vertical deformation. The INSAR is more sensitive to vertical, and due to the satellite geometry over the central Himalayan region, it primarily tells about the vertical deformation. So and it matches well with the GPS vertical as shown in the profile in the right-handmost image. Next. So we use the long-term measurements, almost 15 years measurements, the average of all these measurements, the geodetic measurements, to invert for the interseismic coupling on the main Himalayan thrust. The ISE or the interseismic coupling is a ratio between slip deficient to the long-term slip rate. That tells that a strong coupling or the coupling equivalent to 1 says that the fault is completely locked, and a coupling coefficient almost 0 says that it's a seismic slip. So you can see that there's a uniform coupling from main frontal thrust to almost 100 kilometers, and that says that that could be ruptured due to an earthquake. And I would emphasize the INSAR has a good potential for understanding the interseismic coupling as shown in the resolution test there. So where the GPS is triangle and the INSAR is shown in the dots. So in the resolution test, when we invert, we can see that wherever the INSAR measurements are there, the fault patches are very well resolved and we can use it more. Next. So we also looked at the total strain rate from the GPS measurements. And here it is somewhat interesting. And all these measurements are before earthquake. So we could find two patches of high strain, and one coincide with the rupture of the 2015 earthquake to the east, and the other one, and in equally high strain is there towards the west as well. Next, please. So for the confirmation of this kind of heterogeneity in the strain accumulation, we looked at the seismic B value of this region using a very good data of 15 years data of seismological data from the Nepal Geodetic Network, and which says that similar to the strain pattern, towards west and east, there is a low B value region of the 2015 Nepal earthquake rupture region, which suggests that the low value obviously suggests that high stress in the region. So both the measurements says that there is a high stress region which was ruptured during the 2015 earthquake. Next. So if I combine all the observations together, we can see that there is two asperities. The eastern asperity of high stress and strain, which was ruptured during the 2015 earthquake, and the other asperity towards west is not yet ruptured. And there is a chance that that could be visited by another earthquake. And if we think of a similar magnitude or similar kind of rupture, a 3 meter average slip, it can give a magnitude up to 7.6. Not necessary because, and we need of course more studies to confirmation of the existence of such heterogeneity or the asperities within the Himalayan region. So the rightmost slide compile all the observations, which shows how on a cross section how the rupture propagated. It started from there is a high gradient in the interseismic coupling and stopped half the way before. And another important aspect is that, so whether the partial ruptures so happened during the 2015 earthquake can act as a catalyst for generating a larger magnitude earthquake, which can rupture all the way up to the main frontal thrust. So several partial ruptures may fuel for a large or great magnitude earthquake causing the frontal thrust rupture. So this is one theory which is coming up. It has to be tested more. Next. So when you talk about the seismic hazard, it is really important to understand the coupling pattern. And there are two families of models. One says the homogeneous couple shown in the left, including our model. And recent studies says that there is a heterogeneous couple. And if we have low coupling patches in between the high coupled region, that could arrest the rupture propagation, and it has larger implication in the estimation of the maximum magnitude earthquake in the region. So one way to look at this problem is using the high quality INSAR and advanced modeling like the Bayesian inversion techniques. Next, that we are currently working on. Next, please. So this is last part of my presentation. So I'll briefly talk about a unique earthquake which happened in 2019, September 24, at the northwestern part of the Himalaya in the Mirpur region. So the about 6 magnitude earthquake. And this earthquake is interesting because this is the largest instrumentally recorded event near the MFT, because we normally expect an earthquake away or about 100 or at least about 100 kilometers north of the MFT. But this happened very close to the MFT. And again, we use the INSAR technique to understand the source characteristics. So the INSAR suggests almost 12 centimeter deformation towards south of the rupture. Next slide, please. So in order to do the source characteristics, we use a two-step modeling, a Bayesian inversion to understand the rupture, which suggests a very compact rupture of 5 to 5 kilometers with a uniform slip of 0.82 meter, basically thrust mechanism. And the important thing is the dip. The dip of the earthquake is only 2.5. It's almost horizontal. And we use the INSAR data also to derive the distributed slip model, which again suggests a very compact slip. And we estimated the coefficient of friction from the fault model, which suggests a very low coefficient of friction of 0.06, which is much low compared to the experimental value.
Srijit, if you can bind us.
So yeah, I'm coming to the end. Next slide, please. Yeah. So the important point here is what must have triggered an earthquake at deep portion of the MST close to the main frontal thrust. That is quite uncharacteristic in the Himalayan region. So one plausible mechanism is the low fault friction as inferred from the fault model due to high pore fluid pressure or due to or local weakening of the fault that must have triggered the earthquake. And this earthquake must have transferred stress towards south to the MFT, which is not released even in the post-seismic period, and increasing the seismic hazard in this region. Next. So I summarize that the INSAR and the GPS are extremely important to understand the earthquake cycle in the Himalaya, which has direct implications in understanding the seismic hazard. So along with the geodetic observation, other seismic and other geophysical imaging are important to understand the heterogeneities in the Himalayan thrust, which are very much important to understand the rupture propagation. So coming to the last part is the new mission coming up. I would like to brief on a new mission coming up, the NISA mission, the NASA ISRO SAR mission, with a focus on the solid earth geoscience in order to understand the global plate motions with an unprecedented coverage and accuracy. It's a dedicated INSAR mission, which will be launched in another 1.5 years, and we are all excited about it and looking for that. Next. Thank you very much for your attention, and special thanks to IGU for conferring with me the Krishnan Medal. Thank you very much.
Please answer. I understand that we are late, but I think we can take up one or two questions from young participants, not from seniors. Afterwards, you can discuss with Srijit. Any specific question to Srijit? I think we are getting
Excuse me,
delayed.
sir.
Yes, please.
Excuse me, sir. So I have one question.
Yeah,
Vineet sir. I'm from University, Nepal, and I'm working on Gurkha aspect. It was a nice presentation, sir. I have a query that when we say YAMCT, main central thrust, YAMBT, and YAMFT, in literature somewhere I found YAMST and somewhere I found YAMFT, main Himalayan thrust or main frontal thrust. What is suitable, sir? Should we say YAMST or YAMFT for the rupture area?
Okay. So the MHT is a decolorment form, which is the plate interface between the Indian plate and the Eurasian plate. And all the other fault systems like the MFT, MBT, and MCT are joining to this decolorment at subsurface. So the main strain which is accumulating is on the MHT, which can propagate to the along the MHT, and which can rupture the MFT during a large, great magnitude earthquake, or it can, yeah. So I hope I answer your question.
Yeah, I think we need to close because we may get delayed. So it had been a very nice talk, Srijit. So once again, compliments to you for a wonderful presentation and congratulations on being awarded the prestigious Krishnan Gold Medal. Thank you
very much, sir. Thank you for your support as well.
It's over to Dr. Bansal and Dr. Prasad for next session.
Thank you, sir. Devesh Walia ji. Devesh Walia ji. So we can start next session. It is solid Earth Geosciences, crustal lithosphere studies. It will be chaired by Professor M. Radhakrishna and Professor Y. Srinivas. And Tara Sharma will be reporter for this session. Radhakrishna sir, you can start, sir, please.
I can start.
Yes.
Yeah. Good morning, Dr. Srinivas. Good morning to all of you. And then the session 5 is a continuation of the session 5. It is on the solid earth geosciences with special emphasis on crustal and lithosphere studies. So there are 12 papers in this session. I hope all of presenters are here and share their presentations. So there are only 5 minutes, since we are giving only 5 minutes for each presenter. Please highlight only the salient results of your study without going into very much details. That much time will not be there. Okay, and I request all presenters to stick to their time, very strictly follow the time, because at the end of this session, for half an hour, we have discussion. At the same time, all the presenters who are listening to these different talks, they can note down the presenter's name as well as the question they want to ask, so that at the end of the session, they can refer to the presenter and know any specific questions are there. So with this brief introduction, I request the present first one, Mr. Abhishek Saha. Abhishek Saha, are you there?
He's not there, sir, and his PPT is also not uploaded. So the second we have.
Okay, we can go to second presentation by Ambikapati Amani. Or who will be presenting? Shikha Vashisht will be presenting, or Ambikapati Amani will be presenting?
Shikha Vashisht will be presenting.
Okay, Shikha Vashisht, please start your presentation on co-seismic ionospheric disturbances due to 2004 and 2005 earthquakes, analysis of total electron content. Please.
Yeah. Good morning, everyone. Myself, Shikha Vashisht. Can you please open next slide? So, topic of my presentation is co-seismic ionospheric disturbances due to 2004 Andaman Sumatra earthquake analysis of total electron content. On 26 December 2004, magnitude 9.2 earthquake was occurred in the Sumatra Andaman subduction zone at 0058 UTC. This earthquake ruptured about 1400 kilometers of the Sunda Andaman subduction boundary between the Indian, Australian, and Sunda plate. First of all, I would like to explain that the source of generation of disturbance in the TEC, that is total electron content in ionosphere, can be due to many factors in the upper atmosphere, like solar and geomagnetic disturbances, and also below the atmosphere due to earthquake seismic activity of magnitude greater than 7. As this great earthquake has magnitude greater than 7, we had decided to do this study for this earthquake. So basically, when an earthquake occurs, some type of faulting is present. It could be normal fault, reverse fault, and strike slip fault. Normal and reverse fault lead to vertical surface displacement during the earthquake, while strike slip faults produce horizontal displacement. Shallow thrust earthquakes giving strong vertical ground displacement, which produces infrasonic pressure waves in the vicinity of the neutral atmosphere. These neutral atmospheric disturbances are known as acoustic gravity waves, which propagate upwards to ionospheric altitudes and create disturbances in the electron density there. These disturbances are known as seismo-traveling ionospheric disturbances, that is STID, or co-seismic ionospheric disturbances, that is CID. In this map, a solid green star denotes the epicenter of 2004 earthquake. The red solid triangles are the location of the continuous GPS station that are used in our study. Black open stars along the trajectories are the sub-ionospheric points of the co-seismic ionospheric disturbances arrival of earthquake for the GPS station LLNG. Blue, yellow, and green dotted curves indicate the trajectories of satellites 3, 16, and 19 PRNs respectively for the continuous GPS station LLNG. So can we move on to next slide, please? Next slide, please. Yeah, thank you. Here, as you can see, figure on the left side shows variation of STEC for different PRNs for near field stations located on the south of the epicenter, and figure on the right side shows variation of STEC for different PRNs for the far field station located to the northwest of the epicenter. From both the figures, it can be clearly seen that there is a variation in STEC because of this event between 0100 to 0200 UTC. Next slide, please. Here, as you can see in figure on the left side, we have used 3 PRNs, that is 11, 13, and 20 for all the near field stations to estimate the velocity. The CID was observed within 2 to 10 minutes of the occurrence of the earthquake. Here, we have estimated velocity not only due to earthquake and not due to tsunami wave and not due to tsunami wave and Rayleigh wave. From the time distance plot of these 3 PRNs, the slope was estimated from the best fitting line. This slope corresponds to the propagation velocities of the respective PRNs. Here, the estimated velocity for PRN 11 is 694 meter per second. For 13 is 595 meter per second, and for 20 is 641 meter per second. Hence, the average propagation velocity estimated is 635 meter per second. Here, figure on the right side, that is filter TEC for different PRNs for both near field and far field stations. From these figures, it is evident that the CID has occurred within 2 to 10 minutes of the earthquake at the station ABGS, MSAI, PBAI, and SAMP, which are closer station to the epicenter in the study. At the rest of the 5 station field continuous GPS station, that is LLNG, MKMK, NGNG, PRKB, and NTUS, CID is observed to have occurred after 10 to 20 minutes from the occurrence of the earthquake. In case of 2 far-field IGS stations used in our study, the variation is not prominent as the distance of these earthquakes from the epicenter is more than 2,000 kilometers. Next slide, please. Here, we have plotted variations at continuous GPS stations corresponding to various PRNs for Julian date 360, 361, and 362, that is a day before and after the earthquake, which occurred on 361 at 0058 UTC. and the corresponding TEC fluctuations can be seen between 01 to 0130 UTC. Such variations are not present on the day before and after the earthquake. In order to show the variation estimated in our analysis, we have also analyzed the filter TEC 1 day prior and after the earthquake for PRN 11, 13, and 20. We can see the fluctuation at PRN 11 for MSCI, NGNG, PRKB, and ABGS, and at PRN 13 for SAMP, and at PRN 20 for MKMK, SAM, LLNG, PRKB, and ABGS for Julian date 360, 361, and 362 during the same period. The earthquake occurred on 361 at 0058 UTC, and the TEC fluctuation can be seen between 0100 to 0200 UTC. It can be clearly seen that the variations are not significant on the day before and after the earthquake, as compared with the variations on the day of the earthquake during the period. This implies that the observed variations are indeed due to the 2004 Sumatra Andaman earthquake. Next slide, please. From this study, I want to conclude that the CID with the propagation velocity of 595 to 694 meter per second arrived within 2 to 10 minutes after the earthquake, depending upon the distance of station from the epicenter, and the variation in the CIDs can be prominently seen at the nearest continuous GPS station immediately after the earthquake. NTUS being the farthest station shows a small variation. The delay in the occurrence of variation at GPS site can be associated with a rupture propagation. Thank you.
Thank you, Shika Vasis. So next presenter is Mr. Arun Prasant. Arun Prasant, are you there?
Yes, sir. Yes, sir. Good morning, sir.
Yeah. Please make a presentation. Change in kinematics across the basal decoloma. Insights from the earthquake of
Yes, sir.
Garhwal Himalaya and appraisal to other Himalayan regions. Okay.
Yes, sir.
Go ahead.
A very good morning to
Srinivas, will
everyone.
you be maintaining the timing? Mr. Srinivas?
Yes, sir. Yes,
Yeah,
sir. Yes, sir. Sure.
Yeah. Bhaskar, I think you are noting down the. Yeah.
Very good morning to everyone. Today, I'm going to present my work on the change in kinematics across the basal decollement, focused on the earthquakes of the Garhwal Himalaya region and comparison with other parts of the Himalaya. Next slide, please. Yeah, this conceptual diagram just shows the different occurrences of earthquakes in the Himalayan regions. So the frontal portions, which is the left part of this diagram, which shows the locked portion of the decollement, or famously known as the main Himalayan thrust, which is locked. And this portion is actually ruptured in the large or great earthquakes, and in the Himalayan seismic belt, which is located around the MCT regions, which is the northern lesser Himalaya and the higher Himalaya region. Beneath this, the RAM structure exists between the seismic and aseismic detachment, and the interseismic activity, which is like a small, micro, and moderate size earthquakes. They frequently occur in this particular region. Apart from these earthquakes, there are also some earthquakes that occurred in the lower crust and the upper mantle part of the region. I'm going to talking about these earthquakes in the study. Next slide, please. Yeah, here my study area is Garhwal Himalaya, which is located in the in a seismic gap known as central seismic gap, which is a probable zone for future large or great earthquakes. So in this region, we have a few stations. As we are going to study the lower crustal earthquakes, which needs a more network coverage. So we have taken some other stations from Kinnor and Kumaon networks. We have around 23 stations to study these earthquakes. As you can see from the top right corner plot, which shows the depth distribution of these earthquakes, which clearly states that around 80% to 85% of the earthquakes are located in the upper crustal regions, particularly around 23 kilometers, which is clearly correlated with the region around the mid-crustal ramp. But however, the entire crust is actually seismogenic, And this is supported by earlier studies also regarding the moderate earthquakes occurrences in the Himalaya depth-wise. And from our study as well, compiled from other published records, we have around 51 moment into solutions for the upper crust and 10 moment into solution for the lower crust. The upper crust solutions are around for the earthquakes up to 6.8 magnitude, and lower crust is up to 5.5. And the bottom right plot shows the moment into solutions spread in the whole region around Gadwal Himalaya. So as you can see clearly, bearing one earthquake which located in the around the MBT, all other earthquakes that occurred in lower crust, either lower crust or the mantle, upper mantle, they are clearly strike slip mechanisms. Next slide, please. Yeah, this plot shows the depth distribution of these earthquakes with respect to the geodynamic and tectonic features. They have taken from a published records like Caldwell and Hazarika study by them based on receiver function. And this clearly shows that, and you can note one more thing, that the frontal portions, which has very less seismicity, but those all earthquakes actually are normal faults, but this is out of the focus of the present study. And if you see the mid-crustal ramp, all the earthquakes, majority of them, at least 90% of them, they are thrust faults, and they are clearly correlated with, can be comparable with a dip angle of the ramp structures and the Himalayan ridge. But at the same time, as you cross the decollment, particularly after 23 kilometers beneath that, what you see is mostly of strike slip earthquakes. And here there is one typical question that these earthquakes mostly concentrated around the Moho. They can either be lower crust or upper mantle earthquakes. So we have checked the phases received from the earthquakes to the different stations, particularly the stations located with 100 kilometers or something. We have received both the PG and PN phases, which is upper crustal phases, as well the upper mantle phases. So this can be clearly stated that this only happens because when the earthquake occurs in the lower crust. Next slide, please.
Please conclude.
Make it faster, sir.
Yes, it is. So I have compared this scenario, the change in kinematics across the decollment, compared this scenario with other studies. For example, this study happened in the eastern Nepal and the surrounding regions. As you can see from the depth ranges of 20 to 60, or even the deeper ones up to 80, they all follow the Moho trend, and they are mostly of strike slip locations. Please note the depth section, they are the side views of the focal mechanism, and they are all strike slip. So for this, there are some theories why these earthquakes happening. The one of them was the tearing of the Indian lithospheric mantle. Though this study was conducted for the southern Tibet, but we are inferring that this may also be one of the causes for the earthquakes of strike slip mechanisms in this region. And given that these earthquakes are occurring in the flexure, where the flexure begins in the Indian plate flexure begins, considering the mountain load, bending forces, and the horizontal compression, this is justifiable that these earthquakes having a strike slip mechanisms. Next slide, please. And and we are just concluding that a change in kinematics is not just in a Gadwal Himalaya. This is occurring in the throughout the Himalaya regions. And there are some theories that ecliptation and dehydration, embrittlement, they are as the cause of these earthquakes. And the main conclusion is that we are stating that these earthquakes may be caused by the tearing approach. Next, please. Yeah, thanks for the opportunity.
Thank you, Arun.
Yes, sir.
The next presenter is Who will be ready? Biswajit Mandal.
Yes, sir, Biswajit Mandal.
Seismic imaging of the southern Indian shield using the common reflection surface stack overview. Please, Biswajit.
Yes, sir. Slide, please.
We intimate the presenter 1 minute before.
Yes, sir.
Elect him 1 minute before.
Yeah.
So that take time.
Yeah.
Good morning, everyone. Today I will talk about deep seismic imaging of the southern Indian shield using common deflection surface stack. A review. Next slide, please. In general, the conventional seismic data processing chain, just like CMP stack, needs an accurate velocity model for subsurface imaging. But we know very well that Earth is inhomogeneous and it is very difficult to get an accurate velocity model of the subsurface of the Earth. So we need such a processing trajectory which is independent of velocity model. Here we apply common deflection surface stack method. This method is independent of velocity model and it uses more number of data sets from common deflection surface instead of common deflection point. Therefore, more number of data sets and improve signal to noise ratio. It also takes care the local slope and curvature of the reflector automatically during its stacking process. That's why no need to do for further DMO processing in this chain. If you see the mathematics over here, the CMP hyperbola, and there are we also adding in CRS hyperbola, there are two another terminology, that is deep dependency and curvature dependency during a stacking process. Due to deep dependency and curvature dependency during a stacking process, the improved signal to noise ratio we will get. Next slide. Here is the examples. We are doing comparison between CMP and CRS images. Here, this is the deep seismic reflection images, and deep seismic reflection images, the velocity of deep seismic data to get a velocity is very difficult. That's why if you see the CMP images, it is very much poor. Instead of that, if you come to below to the CRS image, the reflector is very good and all the dipping reflections are coming out very well. In the right hand side also same thing, the comparison between CMP and CRS. Next slide, please. Here we have acquired the seismic data set in Dharwar Craton, starting from Peru to Chikmagalur, from left to, if you see from east to west, there's a red lines, almost 200 line kilometers. So we have done CRS stack imaging in these regions, and if you see the CRS stack image, the eastern Dharwar Craton and western Dharwar Craton are imaged very well. Not only that, if you see the eastern part or eastern Dharwar Craton, the eastern Dharwar Craton exhibits a complex reflectivity patterns, whereas if you see the western Dharwar Craton, it exhibits a simple reflectivity patterns contrary to the conventionally believed. Not only that, if you see the line drawing in the lower bottom part, if you see, we could clearly able to image the Chitradurga thrust in that region. And if you see the Moho variation from eastern Dharwar Craton and western Dharwar Craton is very less. Here in the western Dharwar Craton, the Moho depth is almost 38 kilometers. And if you come to the eastern Dharwar Craton, the Moho depth is 34 kilometers. We also see the western dipping reflection in the extreme right side of the images, and it proves that subduction of the eastern Dharwar Craton towards western Dharwar Craton at Chitradurga thrust. Next slide. Here, if you see another same profile, that is east to west profile, and also we have acquired the seismic data to the another profiles, that is north to south profile, starting from Sira to from SP1 to SP150. So there is we have made a orthogonal profiles. That means north-south and east-west profile. With this north-south and east-west profile, we have imaged a three-dimensional structures of the Dharwar Craton. And this three-dimensional structures shows a 10-kilometer thick magmatic underplating in that region. And it also proves a moho is a regional features on that region. Next slide, please.
Sir, one more minute.
This is seismic data we have acquired from in southern granite terrains. It is from southern granite terrains. It is Kalugu, Malai to Kanyakumari. In these sections, we could able to image the Madurai block as well as the Trivandrum block very well. And in between the Madurai block and Trivandrum blocks, there is two shared zones. One is Achan Kavil shared zones. In between Madurai blocks and to the Tenamalai blocks, there is a Tenamalai shared zones. Not only that, we could able to image a thrust which is starting from surface to upper mantle up to 70 kilometers by this shear stack imaging. Next slide, please. So, in this presentation, we see the WDC exhibits a complex, simpler structures, whereas the EDC exhibits a complex structures. The three-dimensional shear stack image derived from the orthogonal seismic profile suggests that lower crust is modified with a 10-kilometer thick underplating in Dharwar Cratons. The shear stack image of the Kalugu Malai Kanyakumari seismic profile identify a distinct south-dipping reflection fabric from the surface to upper mantle up to 70 kilometer depth. Thank you.
Thank you, Biswajit. Our next presentation is by Chandan Day. Are you there, Chandan Day?
Yes, sir. Yes, I'm there.
We'll be presenting on application of spectral density ratio technique for isolation of seismo-electromagnetic emission from composite low-frequency magnetic field cluster. Please carry
Yes,
on.
sir. Can I have my slides, please? Okay, thank you. Good morning. I, Chandan Dey, a research scholar from Geoscience Division of CSI and NEIST, Jorhat, would like to present my research entitled Application of Spectral Density Ratio Technique for Isolation of Seismo-Electromagnetic Emission from Composite Low-Frequency Magnetic Field Cluster in the 50th Convention of Indian Geophysical Union 2022. Mechanical deformations from within the earthquake preparation zones are believed to cause seismo-electromagnetic emission in the ultra-low frequency band, that is 0.001 to 10 Hertz. And these are studied as precursor candidate for short-range earthquake forecast. However, these emissions overlap with the PC2, PC3 geomagnetic pulsations originating from the magnetosphere. So the spectral density ratio technique, popularly known as the polarization ratio analysis technique, is one of the most commonly used tools for isolating candidate seismo-electromagnetic emissions from the background geomagnetic field. Now it is very well established that Northeast India is seismically one of the most active regions of the world due to its tri-junction tectonic configuration as shown in figure 2. A multiparametric geophysical observatory shown by the orange triangle in the map was set up for earthquake forecast research, including the instrumentation facility of a highly noise resilient 3-component induction coil magnetometer operating in the frequency range of 0.001 to 30 Hertz. Now, in this presentation, I wish to present the results of polarization ratio analysis techniques studied using the data accrued from MPGeo during an intense phase of seismicity. And then next slide, please. Here, table 2 shows here in the table it's a few notable earthquake events for which seismo-electromagnetic emissions were recorded in the ULF zone are shown, respective to their earthquake events, with a precursor time spanning from several weeks to a couple of hours. The polarization ratio techniques is one of the methods applied in this table. Now the polarization ratio gives the ratio of spectral intensities of vertical and horizontal magnetic field components in selected range of frequencies. The theoretical reasoning of The technique may be explained using figure 3. Here in the upper part of the figure, with a spectral scale length in several thousand kilometers of magnetospheric system, plane wave approximation of natural electromagnetic waves of the associated geomagnetic pulse, plane wave approximation may be considered, and as a result, the amplitude of vertical components of the associated pulsations tends towards 0. However, the spectral scale length of an earthquake preparation zone shown here is not more than a few hundred kilometers, and the candidate emissions should strongly prevail in the vertical component of the magnetic field. Therefore, the polarization ratio for such emissions would significantly increase while being in fraction for geomagnetic pulsations. The next slide, please. Yes. Now the ICM data for a period of 137 days was used for this research. Local 3-hour nighttime data confirming with the 18 to 21 hours window of the Kepi index in the frequency range of 0.03 to 1.1 Hertz was considered for the study. Now around 52 earthquake events occurred during the campaign period as shown in the map. However, these events were filtered to identify the earthquake preparation zone with respect to the epicentral distance from MPGU using 3 different parameters, and 7 credible events were nominated for retrospective comparison. The next final slide, please. So these are the results of the analysis. Here, the top panel in figure 6 shows the credible events. The second panel represents the polarization ratio, that is the ratio of spectral density of the horizontal and vertical magnetic field. The third and the fourth panel shows the ratio of X and Y fields against the vertical field respectively. The fifth panel shows the corresponding global geomagnetic activity, and the overall seismicity is shown in the bottommost panel with specialized indicators showing depth, magnitude, and distance from MPGU. Statistical treatment shows that the temporal variability of the ratios exhibit negative correlation with the global geomagnetic activity, shown in the fourth panel. And the ratios display discernible variability, indicating local anomalous influence on the time-dependent vertical magnetic field. If a boundary limit of a mean plus standard deviation is considered, then a total of 13 enhancements are observed in the polarization ratio in the second panel. And out of it, 4 precedes the occurrence of at least 1 credible events. Now, and it is important to note that all the earthquake events which occurred within the 50-kilometer radius of MPGU exhibit an adjacent enhancement. However, there are several inconsistencies with respect to credible events also. And these inconsistencies of enhancements arise the concern that earthquake manifest as a result of complex dynamic processes at varying depth and isolation of seismo-electromagnetic emissions prior to earthquake with a higher degree of conviction demands analysis of multi-station data. With this, I conclude my presentation. Thank you for giving me this opportunity.
Thank you, Chandan. We're going to the next presentation. Mahesh Patel. Mahesh, are you there?
Yes, sir, I'm there.
Muang Nong tektites, the result of an oblique impact in Tibet.
Yes.
Based on crater. Please, carry on.
Good morning, everyone. I'm Mahesh Patil. I'm a freelancer. Today, we will discuss alternate mechanism for Myeongdong tektites as a result of oblique impact. This is the study is based on Skull's model of Hell crater. Next slide, please. So this is a diagram which is depicting the angle of impact and the differences. In normal hypervelocity impact at 45 degrees, projectile instantly melt or vaporizes. But in the event of a highly oblique impact of 10 to 15 degree or a grazing impact, ricochet occurs. This ricochet depends upon the strength of projectile and velocity. The ricocheted fragment continue traveling closer to initial impact velocity in a downrange trajectory. If the velocity is less than the escape velocity, eventually they fall down on Earth.
if we look at the distribution of ejecta in case of oblique impact, it is limited in a narrow fan, unlike a normal impact which is circular. And this ejecta distribution is mix of impact melt and projectile fragment. So these are the findings of Skull's study. And there is also a possibility of sibling impact craters in the event of oblique impact, apart from the oblique crater shape. So we'll go to next slide. When we talk about Myeongdong are a part of Australasian strewn field known to be formed by a highly oblique impact on Indo-China border. This is what is widely accepted. Till date, it is believed that Myeongdong, since they weigh up to 24 kilogram, they have not traveled too much, or they have not traveled far from the source crater. So the search for impact crater has been near the Laos, Thailand, Vietnam, these areas, or Cambodia. But if that is true, that if they have not traveled far from the impact crater, then all other strewn fields should also have Myeongdong kind of tektites, which is not the case. Rather, Myeongdong are nearly exclusive only to Asia. So there is a possibility that Myeongdong formation process is little different. Apart from these tektites, there are unconfirmed reports of tektites from Tibet and Myanmar, which has been discussed. So if we draw now a spread of tektites in Asia and Myeongdong, then we can clearly see it's a narrow fan in which these tektites are distributed. Second important thing, if we look at inclusion part, so it's very similar to oblique impact, and that has been widely accepted that these tektites are result of oblique impact. So we have two types of tektites in this field: one heterogeneous Myeongdong and homogeneous normal tektites. So it's possible that, like Skulls is predicting, that in the oblique impact, strewn field is mix of impact melt as well as projectile fragment. Myeongdong may be projectile fragments. That's our argument. There are a few things which support the argument. First, Myeongdong are layered and heterogeneous. It clearly means they are not melted completely. If they are a part of impact melt, then they can't be heterogeneous. Second, there is a cosite inclusion inside these Myeongdong, and O'Keefe has been arguing on this, saying that this cosite inclusion suggests that they are extraterrestrial origin. Third, but on the other hand, you have inclusions like lithium, which suggest they have inclusions from the target rock. So there is a confusion whether they are from a celestial origin or a target rock. Here we are proposing that Myeongdong are nothing but projectile fragment which got ricocheted after the impact, but at the same time they are contaminated with target rock. So it's important to look at inclusions in Myeongdong. Can we go to the next slide? So if we look at Myeongdong inclusions, and then we will try to understand role of projectile as well as target rock in the inclusions. So on one hand, we have inclusions like lithium and boron, and Coibrel has been insisting that these inclusions are much higher than normal tektites, and thus they are of the opinion they are from a Mekong River Delta. Okay, but till date there hasn't been any crater that has been identified or successfully proposed in Cambodia or this entire region of Southeast Asia. Rather, if we look at Indo-China border, then Tibet has most of the inclusions which are found in Myeongdong are present in Tibet. Whether it is lithium, whether it is kyanite, whether we talk about boron, because Tibet is the biggest source of lithium. Lithium is not found anywhere else on Indo-China border. Kyanite is again, Tibet is very well known for. So there is a possibility, plus we have tektites in Tibet as well. So there is a possibility that Myeongdong, the inclusion in Myeongdong came from impact that occurred at Tibet. Second argument that we are having is that Tibet is also known for some of the ultra high pressure finds. These are like cosite after stishovite, cubic boron nitride. Dobnetskaya and some of the Chinese people working on it have been proposing origin. But our argument, they are from impact origin of a comet, and ultra high pressure minerals like cubic boron nitride or boron carbide, which are otherwise not found in nature, are difficult to justify in a mantle origin. Apart from that, there is an inclusion of FeNIS or Shenzhungite in Myeongdong. Now, the inclusion found is near an end member of the family, which is generally not reported or never ever reported in nature. Rather, study of comet Wild 2 has proved that FENIS is a part of a cometary structure. And there is an argument which is going on, or rather there is a theory that Jupiter family comets may have FENIS as a part of it, which suggests that Myeongdong may be a part of a cometary composition. O'Keefe has been arguing this, used to argue this, that Myeongdong are nothing but celestial rocks based on the cosites and diffusion rate of silicates. So here we propose the mechanism for formation of Myeongdong is nothing but an oblique impact which occurred on the Tibet border, and thus the Asian strewn field is mix of a projectile fragment, that is Myeongdong contaminated with target rock, and normal tektites which are present in Tibet. Now question is that can they travel so much? Can we go to the next slide?
But already time is up, sir.
I'll just take a second.
Yeah, come to
If we look at the trajectory calculation, yes, it matches. Myeongdong can travel this much of distance. We have also found certain structures which appear like sibling impact craters or craters formed by fragment. We are also working on larger structures. I think that's it from our side. Sorry for the time exceeded.
Thank you, Dr. Mahesh, with this presentation.
Thank you, sir.
Whose next presenter is Dr. K. Lakshmi Narayana.
Yeah.
Delineation of basement configuration.
Sir, sorry to interrupt, but his presentation is not with me.
Yeah, he is not there.
No, sir.
Okay, next presenter.
Yes.
Who is that? Swapna Sri?
Oh, sorry.
Swapna Sri will be presenting.
Yes, Swapna Shri, are you there?
Pearson correlation coefficient statistics for dispersive.
She's there, but her voice is not here.
She is there?
She's here, but we can't hear her. She seems to be unmuted. Swapna Shri, can you hear us? Slide share. Swapna Shri?
No, she's also not here.
Yeah, I think she's presenting. Oh, okay. She is not there. She's
sir,
not there.
the presentation is coming from us.
Yeah, from you. Okay, understood.
She's there, but she's not responding.
Maybe we can
move on to the next one.
In the next presentation, and we can give her a chance when she is available.
Yes, sir.
Okay. So next presenter is Bhaskar. Make it anisotropic PN velocity tomography beneath the Indian shield and the external regions.
Yes, sir. Yes, sir.
Srinivas, you note down his.
Yeah.
Yes, sir. Yes, sir. Good morning to all. Myself, Illa Bhaskara, working with Dr. Prakash Kumar at CSR and GRI. So, I'm presenting PN tomography and anisotropic study of the Indian shield and the adjacent regions as a part of this IGU convention. Next slide, please. My present tectonic study region very complex and tectonics consists of diverse geodynamic regions. So present tectonic region consists of various cratons in Indian shield, and the oceanic part of the Indian plate is the Bay of Bengal, and southern regions are the Burmese plate, Tibetan Plateau, Hindukush region, and Himalayan regions. Still, debatable features not yet resolved completely, like anospheric nature and decoupling nature of the crust and mantle, and mantle latent effect of collision of Indian plate, and structure of the Bay of Bengal by using the seismological data. Recently, seismic data is increased in Indian regions, so it is unable to image the uppermost mantle more precisely. The precise seismic velocity structure, PN velocity and anisotropic of the uppermost mantle structure may help to better understand the velocity structure and composition dynamics. Next slide, please. This is the PN cartoon. This is the wave propagation. So where is the crust and mantle velocity significant velocity difference that enable to propagate PN waves through the uppermost mantle? Due to velocity gradient and source ratio distance increasing, the waves are deviate from MOHO and deviate to the deeper part of the uppermost mantle. So composition, presence of partial melt, water, and even anisotropy all substantial influence on the PO speeds. Next slide, please. So uppermost mantle most probably dominated by highly anisotropic medium, that is called olivine. Olivine crystals highly anisotropic. So the crystallized preferred element of one or more of their axis elements, they have generated the bulk anisotropic interaction uppermost mantle. This is the first globally find out the PN anisotropy by Harry Hess in Pacific version 1964. So next slide, please. So we have to compare the PN and SKS anisotropy is very important because PN waves propagate to the laterally in uppermost mantle and SKS propagate to the vertically. So we have to compare the both PN anisotropy, then we can resolve the proper dynamics of the Indian lithosphere in any other study region. Next slide, please. So we have to make it the linear fit of the PN data. We have to restrict the epicenter distance to 15 degree for PN, and we have to take the subcrustal events. So we have to restrict the depth of the events per kilometer. We have to choose always magnitude above 4 because PN is a very low amplitude phases. So we have to take the always magnitude more than 4. And further, we have to incorporate the ASC data. Finally, we have left with high resolution, high quality PN data, 19,500 error waves recorded at 170 stations. This is the final data we plotted here. Next slide, please. So the refracted phase of PN wave propagated to separated into 3 segments. One is this is a downgoing PN event propagating event side. Further ray propagated to the uppermost mantle, and further ray propagated to monitor to the again station side. And this is a isotropic problem considers the crustal delays and mantle times. When you incorporate the anisotropic times, we have to incorporate the azimuthal information, 2 theta and sin theta. The anisotropic magnitude fast forward direction represented by these formulas. The large isotropic anisotropic problems are solved by LSM or least square algorithm developed by Fong and Saunders. The total work is have been done in written codes have written in Python and scripting. Next slide, please. This is the final PN tomographic image of the Indian region surrounding regions. The average PN velocity in this region is 8.22 km/s. This is relatively faster than global average. And you can see Indian region is varying the velocity 8 to 8.47. And the whole cratons are separated by low velocities. You can find out Dava craton, Basta craton separated by Godavari region, like it is a low velocity. At the same time, Western Dava craton and Eastern Dava craton velocity is quite different. Western Dava cratons are lower PN velocity as compared to EDS. And pericratonic Kadapa basin showing the faster PN velocities is indicating the tectonical stability region. And western part of the Indian region considers the low PN velocities indicate the Deccan volcanism subtend altered. But Aravalli and Singham craton, Bhatta cratons are showing the lower PN velocities. At the same time, you can find out the at the final, we can find the higher PN velocities in this Himal region. It indicates the cold Indian condor slab subducting the beneath the Eurasian plate, and Hindu Kush, Tibetan plate and Burmese are showing lower PN velocities. This clearly indicated the subduction and weak lithosphere in these regions. And you can find out the Bay of Bengal region that PN velocity is varying 80 to 8.3 km/s and comparable to the constant part of the Indian shield. Next slide, please. So now we are comparing the anisotropy, PN anisotropy with SKS previous studies. We can find out outside the Indian region that the SKS and PN anisotropies are well matching and supporting the east side flow of the Tibetan lithosphere. For that is turned along the eastern Himalayan syntax. Further flow towards the Burmese region in this region. At the same time, when you are comparing the PN and SKS studies in Indian region, both are completely deviating, which suggesting the frozen anisotropy in the Indian lithosphere. Due to it is a part of the breakup, it is a deformation alteration after its breakup from the Gondwana land. Next slide, please. This is the final conclusion we drawn from our studies. The average PN velocity is 8.2. This is globally faster than, and the craton regions are varying 8 to 8.24 km/s. High and lows are indicate the mantle deformation episodes. And we can see central India is faster PN velocities. It indicates in the basaltic lava pillows. And we can find out the undersetting of thrusting of cold Indian slab beneath the Himalayas. And the PN-SK studies are directions are completely deviate in Indian region, indicates the remnant past anisotropy. And you can see east and west side trend of Tibetan flow supporting the eastward flow. And we can see the Bay Bengal lithosphere maybe have the continental affinity. Further, more studies results you can find out in this paper. Next slide, please. These are references. And next slide. I would like to thank to Director C.S. Ranjare, published this works. I would like to thank to Professor Thomas and Jane for during discussions of writing codes. I would like to thank the CS Anjara for forwarding the project fellow. Next slide, please. Yeah, thank you.
Thank you, Bhaskar.
Yes, sir.
Yeah. For next presenter ready? Ananya P. Mukherjee, are you ready?
Yes, sir. Yes, sir.
Yeah. And adjoining areas along the Cretan boundary. Go ahead.
Good morning to everyone. Myself, Ananya, a PhD student under Dr. Animesh Mandal at the Department of Earth Sciences at IIT Kanpur, and I'll be presenting my work on integrated gravity magnetic study in the southern region of the Bundelkhand Craton and adjoining areas along the Craton boundary. Next, please. Gravity magnetic field data is used over here to delineate the shallow subsurface features in the southern region of the Bundelkhand Craton, covering the Madavra and the Sonrai regions of Uttar Pradesh. Available global gravity grid data is also used to conduct a regional scale gravity study over areas covering the southern Bundelkhand Craton and the area surrounding its southern boundary. The regional study area includes the Bundelkhand granitoid complex surrounded by the Vindhyan supergroup rocks along the southern region, the outcrops of Deccan Traps to the southwest, and the Bijawar Basin rocks along the southern and southeastern margin. The surveyed area consists of the Bundelkhand gneissic complex, Madavra ultramafic complex, and Bijawar group of the Sonrai Basin. It also shows the occurrence of mafic dikes, few quartz reefs, and the east-west trending Sonrai Girar shear zone, along with some smaller faults, which are shown in the as the blue lines. Next, please. Next, the obtained field data is corrected, processed, and gridded on the Geosoft software to plot the complete Booker anomaly map and the total magnetic anomaly maps. Reduced to equator transformation is applied on the total magnetic anomaly map using the MagMap feature on the Geosoft software. The figure D is the Booger anomaly using the free air gravity anomaly and topography grid data obtained from the website of Scripps Institute of Oceanography. The observed gravity data and magnetic anomalies are used to compute the radially average power spectrum to estimate the depths to the various sources, giving the respective anomalies. The depth estimates obtained are shown in the plots below. Next, please. Next, the anomalies are then subjected to regional residual separation using upward continuation method. The 15-kilometer upward continued regional Booger anomaly shows the regional trend corresponding to the prevalent geology. The gravity high seen in the residual anomaly is due to the high density Madavra ultramafic complex, the mafic sequences of the Bijawar group. Next, please. Click twice. Within the Bijawar group within the Sonrai Basin, and the pockets of gravity highs in the south and the southwest region is due to the Bijawar rocks and the Deccan Traps. Next, please. Next. Similarly, the reduced to equator magnetic anomaly was upward continued up to 10 kilometers to give the regional anomaly showing a suitable regional trend. The resultant residual magnetic anomaly delineates the ultramafic and the mafic lithologies that are seen here. And the magnetic low and high pair is also seen in the southern region. The low is corresponding to the presence of the Sonrai Gira shear zone and the associated smaller faults. The southern magnetic high delineates the sequences of the Bijawar group overlain by the Sonrai basin sediments. Next, please. Next, the Booger anomaly from the global gravity data has been separated into the regional residual by upward continuing up to the 30 kilometers. The east-west trending central high is seen in the regional as well as the residual anomaly, which indicates a deep source affecting the gravity variations in the areas along the southern boundary of the craton covered by the Vindhyan sedimentary rocks. The depth estimates from the RAPS plot and the regional Booger anomaly using the global gravity data indicates a source situated approximately at depths near in the lower crust depths. The gravity highs can be seen in the regional as well as the residual anomalies, which point to the probable large dimension of the high density source. These inferences can be corroborated by the previous studies. The presence of large-scale high-density mafic structures at such depths have been stated to be due to rifting mechanisms. The gravity high seen in the southwest corner of the anomalies point at the effects due to the proximity to the Deccan volcanic province. Next, please. With the results obtained till now, we attempted to develop a 2D forward model using prior information along the profile shown to understand the proposed underplated layer, giving rise to the observed gravity high anomaly. These preliminary observations set up a foundation to attempt 2D forward modeling across the other region in the established study area to understand the possible correlation between the observed gravity results suggested underplating and the tectonic history of the studied area. Next, please. So to conclude the presentation, this work will be carried forward to understand the crustal structure beneath the areas flanking the southern Bundelkhand craton boundary and present findings that bring insights on the tectonics linked with the formation of the intracratonic basins like the Bijavar and the Vindhyan basins to reconstruct the evolution history of the associated landmass. I would like to convey my gratitude towards IGU for giving me this opportunity to present at the first convention of my research time over here, and I thank my supervisor for his guidance. Thank you.
Thank you, Ananya, for sticking to the time. Next presenter is Antara Sharma.
Yes, sir.
Are you there?
Sir, yes, sir. Am I audible?
Yeah, please. Yeah. Correlation between crustal anisotropy and seismogenic stress field beneath Shillong Mikir Plateau and its vicinity in the northeastern Ocean.
Thank you, sir.
India, sir, not India.
Okay. Good morning, everyone. So I am Antara Sharma from CSIR NEST, and I'm going to present my work on correlation between crustal anisotropy and seismogenic stress field beneath Shillong Mikir Plateau and its vicinity of Northeast India. So Northeast India is tectonically complex and a seismically active region. This Northeast India is demarcated from lower eastern Himalaya by MCT and MPT. There are lots of faults, and shear zone, etc. Within these regions like Dauki Fault, Kopili Fault, Missimi Trust, and Lohit Trust, etc. And these Kopili faults separate the Shillong Plateau from Mikir Massif. And this Northeast India region experienced two great earthquakes, like 1897 Shillong earthquake and also 1950 Assam earthquake. Next slide, please. So crustal anisotropy is basically used to determine to observe the Earth's interior. So one of the methods is to determine the crustal anisotropy is the shear wave splitting analysis. So when a shear wave passes through an anisotropic medium, it splits into two components, and one is faster than the other, and it gives an angle between the two splitted shear waves, which known as polarization angle, and this polarization angle gives the direction of the anisotropic material. And also there is a time delay between the splitted shear waves, which gives the thickness of the anisotropic material. And for crustal anisotropy, the time difference between S and P interval should be less than 10 seconds. And here is an example of an earthquake occurred on 1st of January 2004 of magnitude 3.1. Here we can see the S minus P is 4.19 seconds. So in the left bottom, the figure shows the result of crustal anisotropy for 17 broadband stations in Northeast India. Almost 11 stations shows the direction is towards northeast-southwest direction. And for stations like Boku, the crustal anisotropy or first polarization directions is towards east-west. And for some stations like BKD, Tura, Shillong, etc., this station shows the two-directional orthogonal two-directional first polarization direction. And this two-directional first polarization direction is maybe due to the presence of the local active faults, lineaments, etc. Next slide, please. Okay, in the next step, we have found the focal mechanism solutions for earthquakes occurred in Shillong Mikir Plateau area, and by using those solutions, we are able to find the stress tensor inversions for 12 stations. Next slide, please. And finally, we compare our result of first polarization direction or crustal anisotropy with the stress tensor inversion results. And for some stations like Kaziranga, NGL, Tejpur, we have found that the first polarization direction is in parallel with the first polarization direction is in parallel with the maximum stress directions. And for some stations, its first polarization directions is in parallel with the minimum as well as intermediate stress direction. And from these observations, we can say that the crustal anisotropy may be due to that stress within that region. And from this results, we can conclude that the seismic anisotropy is in agreement with the direction of maximum horizontal stress axis obtained from stress tensor inversion. And one of the causes of anisotropy is the fluid saturated microcracks. But the Shillong Plateau, Eastern Lower Himalaya, and Assam Valley, including Mikir Plateau, regions are hilly area. So there are almost null probabilities of presence of fluid migrations in the crust. To confirm this statement, further investigations are necessary. And finally, this result of crustal anisotropy and the stress tensor inversion is used to understand the geodynamics development and also to know the seismic hazard assessment as well. So thank you. So this work has been published in Geomatics in 2021. So thank you for giving me the opportunity. Thank you, sir.
Thank you, Antara.
Thank you, sir.
Yeah. Our next presentation is by Pavan Kumar. Pavan, are you there?
No, sir, he's not there. But Swapna Shri is ready.
Who is that?
Swapna Shri.
Swapna Shri is ready? Okay.
Yeah.
Yes, sir.
Swapna Shri.
Sir, am I audible, sir?
Yeah.
Yes.
Please go ahead with
Good
your
morning to
presentation.
all the respected. Sir, my presentation.
Yeah.
Presentation, please.
Yes, 1 minute.
Pearson correlation coefficient statistics for dispersive curve consistency.
Yes.
Yeah.
Good morning to one and all in virtual mode. Myself, Swapna Sri, working as project associate in CSIR NGRA. Today, my presentation topic is Pearson correlation coefficient statistics for dispersive curve consistency. To know dispersive curve, first we have to know what is MASWA. What is MASWA? MASWA is nothing but a multi-channel analysis of surface waves. Is one of the seismic exploration technique which utilizes the property of dispersive nature of the Rayleigh waves. Why we will do MASWA? MASWA we will do for the finding shear wave velocity, which is the important parameter in many geotechnical and earthquake engineering projects. In this first diagram, I'm showing general procedure of a MASWA field survey. First, we will take field measurements, then we will convert it into a dispersive curve, and then we will extract the dispersive energy from the dispersive curve, and then we will do inversion of that dispersive energy. Then we will get a shear wave velocity profile of that particular lithology. The factors which depend on the dispersive curve accuracy is main offset, group interval, spread length, source, and nature of the ground. In this topic, mainly we are discussing about the nature of the how nature of the ground affects the dispersive curve consistency. For that, I am using one statistical analysis tool known as Pearson correlation coefficient. By using that correlation tool, if we get positive correlation, that means the two dispersive curves which we are using are strongly correlated. If we get a negative correlation, then it is inversely correlated. If there is no correlation, then we will get a 0. So for that, I am taking one experimental model in Kaladi Basin. Next slide, please. Kaladi Basin, where I have taken two orthogonal profiles, P1 and P2. In that, the lithology seems to be laterite thick soil, followed by the quartzite, and followed by the granite basement. There we have collected MASWA data for two profiles, P1 and P2. Here, first one shows the pre-processed record, and after processing, we will get a dispersive curve, and after doing inversion, we will get shear wave velocity profile.
For this correlation, I have taken 2 dispersive curves. So next slide. Sir, next slide, please. Sir. Yeah, for profile 1, I have taken so many dispersive curves, and profile 2, I have taken so many dispersive curves. So for all dispersive curves, I can't do Pearson correlation question. So I have normalized all those dispersive curves into single curve. And for profile 1 and profile 2, for those 2 normalized curves, I have taken Pearson correlation quotient value. There I have got a 0.97, which indicates excellent correlation between the 2 data sets, which indicates that the MASVA study, if we do MASVA study with similar acquisition parameters in same lithological terrain, we will get the same phase velocities irrespective of the direction of the profile. Direction of the profile. So the present study helpful to understand the accuracy of data acquisition in the same lithological terrain, and for checking cross verification of MASVA data acquisition. Thank you, sir, for giving this opportunity.
Thank you, Swapna Sri.
Okay.
So are there any other presenters?
No, sir.
No?
No, sir.
Can we just...
So we can go on to the discussion session.
Yeah. So in that case, there are total 9 presentations here.
Yes. Yes.
And all the participants, whoever has been listening to these talks, please, the floor is open for discussion. You have 20 minutes. And please say the presenter's name and ask your question. Any questions? Hello?
I think everybody is muted, sir.
Huh?
Yeah, muted.
Yeah.
Also.
Please, organizers,
Yeah.
inform them to unmute and ask questions if they have specific questions. Hello, Professor Devesh. Yeah.
No, I'm not asking anything, sir.
No.
Yeah, yes,
I'm not asking. If there are any questions, please. If there are no questions,
anyone have any...
I have a few questions. Yeah, please. Anyone?
No, sir. I was just announcing. You continue, sir.
Yeah. So there's a question to Shika Vasisht. Shika Vasisht, are you there? Shika Vasisht?
She is not there, sir.
They left?
I think they're all are in a muted option
Yeah?
only. So they are not listening.
No, you can unmute, I think.
Yeah, they have to unmute first. Yeah.
Shika Vasisht is there?
No,
Otherwise,
sir.
Yeah, Biswajit Mandal. Biswajit,
Yes, sir, I am here.
Yeah. Biswajit, I have a question to you.
Yes, sir, please go ahead.
In your seismic section, okay, your stacked section, you have shown faults F1, F2, F3.
Yes, sir.
They are almost near vertical.
Yes, sir.
Whereas the reflections I see from these sections appear to be a little oblique. And then on what basis you have put these vertical faults? So this I didn't understand.
Actually, sir, vertical fault from the seismic section, there will be a sudden jump of the reflectors. Okay, sir.
Okay.
Reflector continuity is there. After that, this continuity will break up.
Yeah.
Okay, this breakup position will give you the vertical fault positions. Not
but
only that,
on the section they are not distinctly seen. Where
yes,
I see in the upper crustal area, they are near the reflections, in the obliquely trending reflections.
Yes, sir.
Wherever you have put the vertical faults.
Yes, sir. Wherever I put the fault, if you see that there is a sudden change of the reflectivity pattern in that position.
Okay.
If you clear
On
cut.
that basis, you have marked these vertical faults.
Yes, sir. Yes.
Okay. That's why. Just second thing is your crustal underplating. See, you have noticed this underplating in the north-south profile or along the east-west profile?
Which one, sir? Dharwar?
Dharwar.
Yes, sir. Dharwar, we see the underplating in north-south as well as east-west profile. That's why I have told it is a regional feature.
It's a regional feature. It is nothing to do with the eastern Dharwar or western Dharwar. Both the
it is very much clear cut. That is, sir, that is crossing point is there in between eastern and western Dharwars. Okay, sir. And we have imaged the 3D dimensional crustal structures of the western Dharwar craton and northern part.
That means you know. Okay. Okay. Mr. Chandan, are you there, Mr. Chandan?
Yes, sir. Yes, I'm there, sir.
Yeah. So in your method, okay,
yes, sir.
Can you just explain what is the epicentral distance up to which or minimum magnitude threshold your
Yes,
method
sir.
is very effective?
Yes, for all the.
I understand that see there is a requirement of number of stations to compile
Yes,
and say about some kind of quantification as far as this ratio is concerned. Okay. So,
yes,
but from the single station, can you
Yes,
just say approximately that what exactly is the threshold magnitude or the distance to which this your entire approach is sensitive?
Yes, sir. So for our analysis, earthquakes within the epicentral distance of 50 kilometers were all had enhancements like in the polarization ratio.
Okay.
And all the earthquakes occurred in the depth of around 15 to 25 kilometers.
Okay.
So like based on the gauging parameters, the three filters which we used, and also like our study for a magnitude range of 4 to 5 within 50 kilometer range, I think SEMs can be, candidate seismoelectromagnetic emissions can be detected, right?
Okay. Any time to that as a precursory?
Yes. For the for all the three events which occurred within 50 kilometer radius, the time was 2 to 3 days. SEM.
2 to 3 days before
yes.
you can mention.
Yes.
You can observe.
Yes, sir. Thank you, sir.
Yeah. Mr. Bhaskar.
Yes, sir. Yes, sir.
Yeah. No, I just it's a very good work, and I really congratulate you for
Yes.
that excellent paper.
Yes, sir.
On what basis you are saying that the continental lithosphere is below Bay of Bengal?
Yes, sir.
Continental affinity.
No,
Are you striking out the oceanic lithosphere completely, or continental nature of the lithosphere? What do you mean by that?
No, I'm talking about only Bay of Bengal lithosphere only, sir. But
yeah, Bay of Bengal only I am referring.
Yes, sir. What the velocity is coming like 8.0 to 8.32, it is very similar to the Indian shield velocity, sir. Based on velocity only, I compared it might be as continental affinity. Depends upon only velocity.
But in the oceanic, upper mantle also gives similar velocities, 8.1, 8.2 kilometers per second, observed in in the upper mantle velocities in the oceanic regime also. So, yes, based on the thickness of the lithosphere, do you feel that it is more of a continental nature? Or?
Thickness we are not considering, sir. Only velocity only talking.
Only velocities.
Yes, sir. Yes, sir.
Because that statement changes the entire tectonic scenario of the area. That
yes,
has to be carefully viewed. That's what I just want to make a comment on that.
Okay. Yes, sir.
Yeah.
Yes, still working on sir. Different phases also on that region. Yeah. Both PN and BPVS is also.
Yeah.
So in upcoming days, we are producing BPVS paper on Bay of Bengal and Indian region. We'll get similar type of results, might be or something else.
Yeah, because there is a resolution problem because of lack of stations in that entire area.
Yes, sir.
There is a huge gap. Yes, but before going into making a such a sweeping statement, continental affinity of the lithosphere.
Yes, sir.
Maybe you have to be careful about it.
Okay, sir. We'll change it. Yes.
Ananya Mukherjee, are you there?
Yes, sir.
Yeah, you have presented both gravity and magnetic data analysis and interpretation. Okay.
Yes, sir.
So both the data sets, you have used global gravity and magnetic, or you have acquired some data on your own?
Sir, actually, the field data was acquired before I joined the institute. So I have used the gravity and magnetic field data, which was acquired. And to understand the regional construct, I use the available global gravity data. I have not used any global magnetic data
Field
as
data
such till now.
results of your field magnetic data, have you shown here?
No, sir, I have not yet gone into the modeling of the magnetic data till now. I have stuck
Magnetic
to
anomaly map you prepared based on your acquired data, or
the acquired data. The anomaly data is the acquired data.
No, are you aware of the sensitivity or spatial resolution of the Sandwell's gravity database in the continental domain?
So the global gravity data which we use, the said resolution is to be 1 minute. So that is kind of
That is,
approximately
1
11
minute is for
kilometers.
oceanic areas. In the
Okay,
continental areas, were filled in with ECM 2008 data set.
Yes, sir.
2.5 minute resolution.
Okay, sir.
2.5 minute resolution. And I'm asking about the spatial resolution of this. So up to what frequencies you can, because you have done spectral analysis. You're a PhD student, okay, working on gravity magnetic. Okay. And then I know Animesh is an excellent worker. He takes care of that. But as a student, you must be aware that the limitations of the global data sets, okay, for inferring the shallow structural heterogeneities and in smaller areas. Okay.
Yes,
The
sir.
spatial resolution of your data sets are very, very important. Okay.
Okay, sir.
And then suppose you have used spectral analysis for your global gravity data. And what depths you have results of your spectral analysis? Can you?
So the spectral analysis, according to the depth, the plots that we got, it was around 29 to 30 kilometers was the deepest, as per the plot that we got.
What about shallow?
And the shallowest that we got was around 3 to 2.8, 2.7.
Here lies the problem.
Yes,
Can
sir.
your
So
global data resolve this?
yes, sir.
3
So we
kilometers,
were not we were not trying to get the shallower with the global data.
I understood.
Yes,
I
sir.
understood. But as a research student, you must be aware of all the limitations of each and every
Yes, sir.
data
Yes,
that
sir.
you use. Okay.
Yes, sir. Okay,
Thank
sir.
you.
Thank
Good.
you so
Good.
much.
Yeah.
Thank you,
Good
sir.
morning, sir.
Yeah.
So I have a question. This is
Yeah,
Anand
Anand,
from IAG.
Yeah,
So I
yeah,
also have a
go
question
ahead,
to I have a question to Ananya.
Yeah, please go ahead.
Yeah, because actually you are showing the magnetic maps also where you have used the reduced equator. So
Yes, sir.
first question is why you have used the reduced equator, and second thing is that the highs and lows will interchange when you actually do reduced equator and reduced pole. So I don't know whether you have taken care of that in your interpretation.
Sir, actually, we had tried the reduced to pole also, and we saw with the reduced to equator. With the reduced to pole, in our data, we were seeing a lot of north-south exaggeration of the anomalies. So then, as suggested by my supervisor, and also like with the literature that I referred to, so we went with the reduced to equator to remove that exaggeration and try to get it to the the prevalent geology sources, what we were trying to interpret.
No, when you do the reduced equator, so the highs will be actually low magnetization, and it is vice versa. So you have to take care of that in your interpretation. And what is the inclination of your area? So I think it is quite high. It is much above 20.
Yes, sir.
It
It is around 35, 36. The variation was.
Yeah,
It's an
then why
area where
that?
you can use RTP also.
Yeah, we can use RTP
Okay,
because it's
sir.
much above the that limit of the
Limit of
magnetic equator. No?
Okay, sir, I will take this into consideration.
What he is, Professor Anand saying is that when you are interpreting an RTE map, you have to be careful. Okay.
Yes, sir. Okay,
And then
sir.
that's he's keeping a caution to you. That's all. Okay.
Yeah. Also,
Yes,
I
sir.
think
Yes, sir.
when you
Thank you
do
so
an
much.
RTE,
Yes,
there
sir.
will be an east-west elongation also normally.
Yeah.
So that actually you
Okay.
will interpret it as some features which is not correct.
Okay.
Yeah,
Okay.
there will be always an east-west elongation.
Okay.
Please
Okay.
take
Thank
care
you
of
so
it.
much, sir. Yes, sir. Thank you for the comments.
Anyone else? Yeah, please, Sharma ji. Yeah, but no, you're muted.
Sarma sir, you are muted
You're
now.
muted.
Earlier you were unmuted, but your voice was not coming. There is some issue.
Please unmute.
No, it is not. It is muted, sir. It is not unmuted.
Currently it's muted.
Yeah.
Unmuted.
Earlier
I
it was
think,
unmuted, but his voice was not coming.
Good
Sarma
morning,
sir,
Sunil. I think we have 3 more minutes to complete.
Okay.
We will hand over on time.
Yeah, we'll finish it, sir. Okay. Yeah.
Yeah.
Please. No,
If there are no other doubts, anyone? We have 2 more minutes. If there are no doubts, we thank IGU organizers on my behalf and Professor Srinivas.
Yeah, we'll hand over, sir.
We thank organizers for giving this opportunity.
Yeah.
And then who is the Bhaskar?
Yes, sir.
You have to make a compile all the presentations and then give a report. You can mark a copy to me and Professor Srinivas. Okay.
Yes,
Thank you very much.
Thank you, sir.
No, Dr. Sunil, floor is yours.
Thank you very much. And I think it is really nice that you have finished it in time.
Right on time. No, because two presentations we cancelled.
Yeah, three are absent.
Three are absentees. That gave us scope. Thank you.
Okay.
Yeah, thank you, Professor Radhakrishnan and Srinivas ji.
Okay, thank you, Professor.
For managing within time. So hopefully the next session will also be like this only. So here, our next chairperson of the present session is Dr. Sunil Singh ji, and co-chair is Dr. Rashmi Sharma. Our rapporteur for the session is Dr. Meghali Barua. So 3 of them are there. So now I request Chairperson Dr. Sunil Singh ji to please take over.
Thank you very much. Thanks a lot, Walia ji.
Yeah, thank you.
We will start. So, Rasmi, good morning.
Good morning, sir. Good morning.
Yeah, and the rapporteur name, it was not mentioned. Could you please tell us?
Dr. Meghali Barua. She is there.
Okay. So, good morning, Dr. Barua. So, we'll start the session and maybe first few talks I will manage, and then I think Rasmi will take over after 2-3 talks. It's okay, Dr. Rasmi?
Yes, sir. Perfectly fine.
Okay. So I hope all the speakers are there. So we still have 1 minute to go. I will request Dr. Barua to make a note of all the talks, because at the end she has to submit the report.
Okay, sure, sir.
Yeah, please do that. And Rasmi, in the beginning, please keep a tab on the timing. So because you have to maintain that.
Sure, sir.
Our earlier session has given us very good timing.
Yeah, we need to maintain that.
Yes. Okay. Now it is already 11:30. We'll start that. So good morning, everybody, and welcome to this technical session 6, which is based on atmosphere, space, and planetary sciences, and marine sediments, ocean energy, plate boundary processes, etc. So in this, I welcome our co-chair, Dr. Rashmi Sharma, and rapporteur, Dr. Barua. So the first talk will be given on the topic annual cycle of black carbon radiative forcing over a representative central IGP location, Varanasi. And it will be delivered by the authors are Bharatji Mehrotra, Dirga Parasar, Vashu Singh, Atul Srivastava, R.S. Singh, Yogesh Kumar Vishkarma, Manoj Kumar Srivastava. And the talk will be given by Paratji Mehrotra. So please go ahead.
Okay, good morning to all. Myself, Bharatji Mehrotra. I am PhD scholar at the Department of Geophysics, Banaras Hindu University. The topic of the talk is annual cycle of black carbon radiative forcing over a representative central IGP location, Varanasi. Next slide, please. So introduction. Black carbon is a dominant absorbing component of carbonaceous aerosol, and it is mostly generated by combustion of fossil fuel, biofuel, biomass burning. Despite of having brief atmospheric lifetime of around 4 to 15 days, it has several direct, semi-direct, indirect and microphysical effect on Earth's climate. It has strong absorbing nature, which leads to warming of atmosphere and lead to global warming. The IPCC in its fifth assessment report reported that the clear sky radiative forcing of BC is around 0.4 watt per meter square, ranging from 0.05 to 8. Understanding the source contribution of BC aerosol is important because of its high concentration urban agglomeration near source and widespread distribution. So the main objective of the study was to assess the optical properties and radiative impact of black carbon during 2009 over Varanasi, which is a representative central IGP location. Next slide, please. So Varanasi is a urban location in the southeastern part of Uttar Pradesh, and the location is a representative of middle IGP location. The station Varanasi is a ISRO RF network. So methodology of the work, we collected the black carbon mass concentration using the athylometer AE42 instrument, and these BC mass concentration was fed in opaque model with atmospheric properties and relative humidity to get the optical properties of black carbon that are SSA, AP and AOD. As the direct observation of BC optical properties were not available, so opaque model was used. The opaque generated optical properties with column water vapor, column ozone, surface albedo was fed in SB-DART model to generate the radiative forcing at the top of the atmosphere and surface, and the difference of top of the atmosphere and surface was used to generate the radiative forcing in the atmosphere, and finally heating rate was calculated. Next slide, please. So results from the work, here is BC mass concentration variation, the monthly BC mass concentration variation, and the second graph shows the forcing and heating rate and AOD. Hourly BC concentration varied from 0.03 to 61 microgram per meter cube with an annual mean concentration of 0.8 microgram per meter cube. The modeled BC AOD at 550 nanometer varied from 0.0 to 0.0418 with an annual mean of 0.116, and the monthly MODIS AOD varied from 0.4 to 1.1 with an annual mean of 0.6 plus minus 0.23 at 500 nanometer. The and modeled BC AOD was significantly correlated with the global available MERA2 model data with a Pearson correlation coefficient of 0.87. The radiative forcing of BC within the atmosphere was found to be 48.44 plus minus 13.14 watt per meter square, which resulted in heating rate of 1.35 Kelvin per day in the atmosphere during the study period. Next slide, please. So on the daily basis, our BC mass concentration ranged from 1 to 43 microgram per meter cube with the highest measurement of around 62 microgram per meter cube. The modeled BC varied from 0.002 to 0.418, and the contribution of BC AOD in total AOD ranged from 5 to 31%. The average BC radiative forcing for the complete study period was found to be 17.9 watt per meter cube at the top of the atmosphere, minus 26 watt per meter at the surface, and 44.5 watt per meter square within the atmosphere. The heating rate varied from 0.5 to 2.1 Kelvin per day with an annual mean of 1.35 plus minus 0.4 Kelvin per day. Next. These are some references. Next. Acknowledgement. Next. Thank you.
Okay. Thank you very much. So I think time is not there, but if one question anybody has.
Sir, can we take questions in the discussion session at the end?
At the end, okay.
Yes, sir.
Okay, thank you, sir.
Yeah, thank you very much. Thank you very much, Bharatji. So you can log out now. The next talk will be given by A. Akilan, S. Padi, and HBS Satyanarayana on the zenith tropospheric delay anomalies associated with volcanic eruption and large earthquake, a case study. Please go ahead. Akilan, please go ahead.
Mr. Akilan, can you hear us? He's there, but he's not responding.
So,
Mr. Akilan, are you there? Sir, he's not responding. I will message him. We can move on to the next one. We can.
So we'll move to the next talk on the seasonal prediction of ISMR using WRF.
Sorry to interrupt again, sir. Mr. Mohanty is not there, so we have to move on to next, Mr. Sudesh.
Okay, so the next talk will be dust fall deposition of NH4 and nitrate along with other inorganic over and rural agriculture site in Delhi NCR.
Message will give.
And it will be delivered by Dr. Sudesh. So Dr. Sudesh, please.
Good morning, everyone. First of all, I want to thank for giving me the opportunity to present my presentation on this platform.
So presentation is not up.
I'm bringing, sir. One second.
Please share the slides.
Yes, 1 second.
Yeah, the topic of my presentation is dust fall deposition of ammonium and nitrate along with other inorganic species over an rural agricultural site in Delhi NCR. Next slide, please. First of all, we know the deposition of NR, that is reactive nitrogen species, has increased globally due to increasing emission of NR species from various anthropogenic sources. The increasing deposition of NR have concern in India and China mainly, where nitrogen compounds are reported to be increased at a very fast rate. Now, the dust particles which are deposited generally have aerodynamic diameter greater than 10 to 20 micrometer. And dust particles in fine mode remain in atmosphere for a week or more, and they are smoothly driven away from their emission sources. Now, methodology is, I have collected the dust samples from July 2017 to June 2018 over in rural agricultural site in Jhajjar in Haryana state, which comes in Delhi NCR region. These are the coordinates of my site. Dust was collected in 140 Petri plates. Each Petri plate was exposed for 15 days, and then the aqueous extract of dust bowl samples were prepared, they sonicated and filtered, and then analyzed using ion chromatography for various cations and anions. Next slide, please. These are the results of my study. Here the comparison of dust fall fluxes of major ions are for Kharif and Rabi season. We can see mainly during the Rabi season, the concentration of all the ions were higher as compared to Kharif season. The potassium mainly we can see significant variation in concentration of potassium during the Rabi season. It might be due to the biomass burning activities which are more common during the Rabi season, and due to stable atmospheric boundary layer, these undergo less dispersion and hence are accumulated in the atmosphere, which gives the concentration higher during the Rabi season. This is the ammonium and nitrate fluxes variation. Here we can see during the month of June, July, the concentration of ammonium and nitrate were lowest, and ammonium concentration in the month of December were highest. Also, because during Rabi season, wheat crop harvesting fertilizers are added during first stage of growth, and nitrate fluxes were observed to be highest during the month of September. And ammonium fluxes were invariably lesser as compared to nitrate fluxes throughout the entire sampling because since the dust is alkaline in Indian region, it opposes the absorption of NH3 onto the dust particles, and nitrate concentration were higher as compared to ammonium. These are the percentage contribution of all the cations in both Kharif and Rabi season. And concentration during Kharif season were followed this order. Sulfate were higher than calcium, followed by potassium chloride, and in this sequence. And during Rabi season, potassium concentration were higher, followed by sulfate, calcium, ammonium. Next slide, please. Next slide, please. Neutralization factors were calculated for all the cations versus sulfate and nitrate in order to determine the scavenging capacity of ions. For more detailed analysis into the regression plots of sulfate and nitrate, these calcium sulfate and nitrate versus major cation plots were seen. Here we can see almost all the data points in this graph are not above and below the neutralization line. It means higher concentration of calcium can be responsible for complete scavenging of sulfate and nitrate. But here the data points are mainly above the neutralization line. Then the morphological analysis of dust reflected the spherical, irregular, and spheroidal shapes of aerosols. These are the samples collected mainly during the biomass burning period in October, November, and April, May months. And these shapes revealed that these particles are mainly contributed from biomass burning activities. Thank you.
Thank you very much, Dr. Sudesh. We'll move to the next talk.
Sir, sorry to interrupt. Mr. Akilan is ready, and if
so
you allow, then we can correct it.
Take his talk. So,
okay.
Next talk will be given by Dr. A. Akilan.
Good morning, sir.
Yeah, please go ahead.
Can you have the slides?
I would also like to request all the presenters to switch on their video when they're presenting. If they are having network issues, then they can switch it off. Otherwise, it is better if they switch it on so that your video is also visible to everyone.
Yeah, good morning to everyone. My title of my talk is ECTD anomalies associated with associated with large earthquakes. May you go to the previous slide? Yeah. My title of my talk is ECTD anomalies associated with volcanic eruption and large earthquakes, case studies. Introduction. The atmospheric dry gases and wet water contents introduces additional delay to the primary GPS observer. The radio wave propagation period varies according to the dry gases and wet water content in the atmosphere. Monitoring ECTD is important during the troposphere event. It may help us for the weather forecast and it is varying according to the season. The global positioning system is one of the least cost tool to estimate zenith total delay. In this talk, there are two parts. The first part is the anomalies associated with the large earthquakes. And the second part is ECTD anomalies associated with volcanic eruption. Next. Now I am coming to the first part, ECTD anomalies associated with the large earthquakes. To investigate the troposphere response after the great Nepal earthquake based on the analysis of zenith total delay, we supplement our primary results with the findings from the another large earthquake, that is 1999 Chamal earthquake. The first map shows the location of the Nepal earthquake, and we have used the Lucknow and Hyderabad and the MS University data. In the next figure, we are showing the ECTD changes during the co-seismic period. The black color indicates the GPS derived ECTD, and the red color dots shows the numerical weather model derived ECTD. There is a good correlation between these two estimations. And the red color diamond shows the main shock and the after shocks. During the main shock and after shocks, there is a drop in the zenith total delay. Similarly, in the other station also, there is a drop in zenith total delay. And during that period, there is a drop in the pressure also, atmospheric pressure also, after the main shock and during the foreshocks. In the second map, we are showing the Chamal earthquake location, and we used Hyderabad data and the IAC data. In the next figure, I am showing the estimated zenith total delay. There is a drop during the seismic period in the zenith total delay. And this red color stars shows the 1999 Chamal earthquake and the foreshocks conclusion. A reduction in the density of the wet and hydrostatic components, which together form the zenith total delay in the atmosphere, can occur due to the intense movement of the atmosphere constituent during the passage of shock waves radiated from the earthquake source. Alternatively, the zenith total delay drop can arise from the expansion of the moisture in the atmosphere by the blast waves radiated from the earthquake source. Additionally, release of the helium following the large earthquakes may reduce the proportion of the oxygen and the nitrogen in the air, can also explain the observed drop in the zenith total delay. Next slide. Now I am coming to the second part. ECTD anomalies associated with volcanic eruption. Perturbation in the atmospheric gaseous components over coastal Antarctica detected in GPS signals and its natural origin in GPS signals to volcanic eruption after the Chaitan volcano, 19th February 2009. The first map shows the location of the Chaitan volcano and the GPS stations in Palmer, Maitri, Siao, Davis, and McBurrow. It's showing. And in the next figure, I am showing the ECTD estimated by using and numerical weather modeling derived total delay. There is a good agreement between the two estimations. After the volcanic eruption, there is a significant drop in the station Davis, Siao, and McBurrow and Maitri. In the last figure, I am showing the time of the eruption, and before the eruption, the amplitude of the black carbon is less, and after the eruption, the black carbon level is high in Antarctica, and the black carbon is estimated, and the ECTD has a good correlation. Thus, during the Mount Shaitan volcano eruption, showed a good correlation with abnormal atmospheric black carbon content noticed over Antarctica during this period. Next slide. We therefore suggest that the anomalous high acidity values might resulted from high BC influx into the atmosphere. We propose that the 19th February 2009 massive eruption of Chaitan volcano is the source of the black carbon, which moved from the volcanic front to the East Antarctica margin along with the circumpolar current. Conclusions: Zenith total delay perturbation well correlates with the abnormal atmospheric black carbon content changes noticed over the Indian Antarctic Station. Therefore, it could be concluded that the high BC content observed by Chowbey et al. 2010 at Maitri during the February 2009 is not due to the anthropogenic activity but resulted as a part of the natural process of volcanic eruption. Thus, volcanic eruption and large earthquakes are the likely sources causing changes in sensitivity observed. Thank you.
Thank you very much, Dr. Kilan. So we will move to the next talk. Next talk is on observation of mesospheric front-like structure over low latitude distribution silture. And talk will be given by Nilesh Chauhan.
Hello, am I audible?
Yes.
Slides, please. So, good morning, all. I'm Nilesh Chauhan. I'm from Indian Institute of Geomagnetism, Navi Mumbai, and I'm working under the guidance of Professor S. Gurubaran. Next. Next. So, the atmospheric waves, such as the planetary waves, atmospheric tides, and gravity waves, are considered as the primary source of the variability in the mesosphere lower thermosphere region. I'm focusing on the one of the waves, which is the gravity wave. So these are the wave created by the perturbation to the stably stratified atmosphere. Here, the buoyancy and gravity act as a restoring force for these waves. So these waves generally originate in the lower atmosphere from in the tropospheric region, and they propagate vertically up with their amplitude increasing with the altitude, since the density is decreasing as we go up in the altitude. So these waves contribute to the vertical coupling of the whole atmosphere ionospheric system, since we can see the wave sources located at the lower atmosphere. Then these wave undergo wave filtering, and this wave break in the upper atmosphere in between 180 to 100 kilometers. They transfer their energy and momentum which they are carrying to the background atmosphere, hence contributing to the dynamics of the MLT region. So the horizontal scales or the wavelength of this wave can be from few kilometers to 1,000 kilometers, while the vertical wavelength can be of few kilometers, and the temporal scale from minutes to several hours. Here I am showing the two examples of these gravity waves. So the general sources of these waves are the convective activity or the cyclones, orography, that means wind flow over the terrain or elevated mountain ranges can generate these gravity waves. Sometimes earthquake and volcanic eruption are also examples. So here on the right hand side, the example of the waves generated due to the convective activity, you can see the concentric wave like structures. And another is the example of the waves generated due to the volcanic eruption. This is actually a video. Can you play this? The first one. Yeah, this one. So you can see the waves in the gray region, in the gray color. So waves are being generated. So this is due to the volcanic eruption which happened recently in the 15th of January last month. So Hopatunga volcano. Next. So we use this all sky air glow instrument to observe these waves. So this consists of the top side, there is a lens known as the fisheye lens, which has a 180-degree field of view. And at the bottom, we have the CCD camera. And there are filters which corresponds to different altitude for the different air glow emissions are kept in the circular housing in between. So these actually the filters are correspond to the air glow emission originating at different altitudes. So currently IIG operates 4 imager at the sites marked by the red dot, and we are planning one more to install at the Port Blair. So in this other video, we can see the example of the one of the manifestation of the gravity wave, which is the frontal event. So here is the dark front, which is propagating towards the northeast. So there are different manifestations, such as the bands or ripples or this frontal structure. So next, so on February 22nd, 2020, we observed one such frontal event in the both at the 97-kilometer altitude as well as the 87-kilometer altitude emission images. So I'm presenting only the one emission images, which is from 97-kilometer. So here the XY axis represents the distances in kilometer, and the yellow arrow represents the direction of propagation of this frontal structure, which we observed. So usually these structures are accompanied by the trailing waves, or the they are not accompanied, but they are accompanied by turbulent region. So usually the trailing waves are propagate with the front, which we see here. But in this case, in this observation, we see that the front is moving, and later these wave-like structures are originated, known as the ripples, but they are not moving along with the front, they are stationary. So you can see in these plots, first plot. So I obtained the cross sections along across these front structure. So this red dotted line indicates the propagation of these front in the subsequent images. The time here is noted, and these small scale structure which are generated after that, these are stationary. They are growing in number, but they are stationary. They are not moving with the wave, which makes this case a peculiar one. Next slide. Since we do not have the simultaneous wind and temperature observation, we rely on the satellite based and the model winds. So here is the temperature profiles which are obtained from the timed Sabre satellite, Sabre instrument on board time satellite. So three different profiles I obtained. Now these profiles corresponds to 2 hours later the event. So these are not the simultaneous observation of the temperature, but here we can see from 85 to 95 kilometer in between, there is the temperature is increasing. So these increase in temperature is known as the temperature inversion. Now, actually, these fronts require a ducting region or a channel to propagate. So this temperature inversion can provide a stable ducting region for these waves to propagate in at those altitude. Similarly, a wind structure can also provide this kind of ducting region. So here in the below images, I am showing an example of the how temperature inversion act as a ducting region. So this increase in temperature usually occur in the temperature profile at the mesospheric altitudes. They are known as the mesospheric inversion layers. And here in the second, I am showing the HWM model winds actually. So the two vertical dash line represent the time of the observation of the event, and two horizontal lines are the ducting region corresponding to this temperature inversion. So we see, and here the positive values in the are the eastward winds, and the first plot in the zonal, the positive value represent the eastward and the negative is the westward wind. And similarly in the meridional plots, positive is northward and the negative values are the, that means blue value, are the southward winds. So we see the winds are approximately towards the south west region, which is orthogonal to the propagation of the front, which we observed in the last plot, which is in the northeast direction. So they are actually orthogonal. So in that case, winds do not provide any kind of ducting region, or they do not contribute in the propagation of this front. So we are kind of in a conclusion that this ducting region is provided by this the temperature inversion which we see here. So further analysis is still going on because we don't have simultaneous temperature. We are trying different data sets to bring out the more information about this event. Next. So to summarize my result, that we observed one of the remarkable front in the northeastern part of the India, and it is observed in two different emissions. And since it is at 97 kilometer that we observed the dark front, and at the 87 kilometer we observe the bright front, which correspond to the same observation. So which indicate that this ducting region is definitely between the 87 to 97 kilometer, which we can see in the plot also. And to find out the sources, so we think or that the source may be probably located over the Bay of Bengal, since the wave was providing towards the northeast. Next. Thank you so much.
Thank you very much, Dr. Nilesh. So We'll move to the next talk. The next talk is on ionospheric resonance oscillations during great earthquakes, and it will be delivered by Srinivas Nayak.
Hello, good morning, everyone. Yes, good morning, everyone. So I'm Srinivas Nayak from Shillong Geophysical Research Center. I'll be presenting my topic, ionospheric resonance oscillation during great earthquakes. So actually, this is an event-based study. So we have taken up 3 events, but in this presentation, I'll be just showing 1 event. So can we go to the next slide, please? Okay, first of all, basic introduction. Whenever there is an earthquake, the energy released at the ground, the energy released at the ground is transferred into the atmosphere and then to the ionosphere. So first of all, it can be directly from the epicenter. This is an offshore earthquake. So it can be directly from the epicenter, and this energy is in form of acoustic waves. These acoustic waves propagate to higher altitudes, and when they interact with the ionosphere, and they produce redistribution of the background electron density that leads to a generation of co-seismic ionospheric can be produced by the CIP can be it can be produced directly from the epicenter. It can be produced from the propagating Rayleigh waves, and but in particularly my study, I'm more curious about the ionospheric oscillations that follows after the decay of the CIP. So those oscillations are centered around a frequency of nearly 3.7 megahertz, and the literature says that these oscillations are centered at around Earth atmosphere resonance oscillation frequencies. So in this particular study, can we go to the next slide? Okay, in this particular study, we will be addressing the basic parameters that are affecting the manifestation of these ionospheric resonance ionospheric signatures, and the role of seismic and non-seismic forcing in their manifestation. So first of all, these are the 3 basic non-tectonic forcing parameters that govern the manifestation of ionospheric signatures. First is geomagnetic neutral wave coupling factor. So this factor can be quantified as K dot B, where K is the propagation vector and B is the background electron density factor. As we can see, like whenever the acoustic wave is propagating in the atmosphere, it will interact with the background electron density and try to redistribute it. But since the magnetic, in the presence of magnetic field, this charged particle will have some component or some effect of the magnetic field, and so the resultant effect can be quantized as GNF is equal to K dot IB. So next is satellite geometry factor. As GPS derived TEC is an integrated quantity. So like based on our line of sight between the satellite and receiver, sometimes if the line of sight is not particularly favorable, like in case of station A, you can see the line of sight is in a slant. So the waves, acoustic waves propagating will be crossing the line of sight one after another. But in case of from station B, for the same event, the line of sights will be integrated. So when we look at the resultant picture, we will not be getting any significant results. So line of sight is also a very important parameter that affects the manifestation of ionospheric signatures. And so this can be quantified as e to the power minus K dot R by cos chi, where R is the satellite line of sight wave vector, chi is the satellite zenith angle, and K is the wave vector. And final quantity that affects the non-tectonic forcing is the background electron density factor. So more the electron density, then more significantly the signature will manifest. Can we go to the next slide? Okay, so this is a simple example. This has been derived during the 2011 Tohoku earthquake. Sorry. So first of all, all these non-tectonic forcing parameters can be combined together to one non-tectonic forcing parameter, NTFM, which is a product of GNF, EDF, and SGF. So this is for 2011 event for a given station 0041. This is for Japan Tohoku earthquake. So this is the epicenter. This yellow star is the epicenter. And if you see on the right hand side panel, this is the background electron density. It is very slightly varying. And next in the middle on the right hand side, you can see this is the GNF. And the third one on the left is the satellite geometry factor. So as a product of all this, you will get a resultant non-tectonic forcing parameters that govern the manifestation of ionospheric signatures. So can we go to the next slide, please? So in this presentation, I'll be talking about the Sumatra 2012 doublet earthquake. This was a strike slip earthquake, and these two events were very closely spaced in time as well as space. So these triangles are the GPS stations that I have used in this current study. And these tracks are for the UMLH station, the GPS station, and the pentagons are for the seismometer stations used in this current study. Next slide, please. Okay, first of all, let's start with the ionospheric part, the GPS observations. So I have considered GPS observations for from all the stations listed in the previous slide. So for the stations UMLH and PBRI, we could see resonance ionospheric oscillations after the, so if you see at the figure panel on the right side, for PRN32 from UMLH station, initially we see a strong CIP, and after the decay of CIP, there are significant resonance ionospheric oscillations that sustained for a duration of nearly 1 hour or more. So these are filtered PECs, and these have been filtered within a range of 1 to 10 millihertz to remove the day-to-day background. And the second one is for PBRI station. Here also we have seen the same resonance ionospheric signature, but in this case, these oscillations were observed after the second earthquake event. So as you can see, the FFT is also plotted, and spectrogram is also plotted. In the spectrogram, you can see the frequency of oscillation is centered around 4 millihertz, same as in case of PBRI station. And here is the station, a list of all the time series plots. As you can see, only these two stations are like very peculiarly seeing this resonance ionospheric oscillation, not all the stations. So next slide, please.
Mr. Nayak, you need to conclude.
Okay, so just 1 minute.
Already we have taken more time.
Okay, sir. So this most of the oscillations were centered to the north-northeast of the epicenter. Resonance ionospheric oscillations were centered to the north-northeast of the epicenter. Next slide. Okay, so from these non-tectonic forcing parameters, we have seen that the resultant forcings were more favorable to the northeast of the epicenter. Next slide, please. And the seismic observations, filtered seismic observations also supported the same observations. And here we can see the R2 and R3 waves coincided with the arrival of were coincided with the same time as the station PBRI observed resonance. In the last slide, please. Okay, so finally we could conclude it from this this exercise that the resonant ionospheric oscillations could be linked to the seismic sources during great earthquake, and the resonance observed after the first earthquake could be linked to the excess release of energy at 4 millihertz during the Sumatra during the first event, and the resonance observed after the second earthquake could be linked to the R2 Rayleigh waves of the first event. So the amplitude anisotropy observed in the resonant ionospheric oscillations were also explained by highlighting the role of non-tectonic forcing mechanisms. So next slide. Thank you. Okay. Thank you for your attention. Thank you so much.
I will request now Dr. Rasmi to take over.
Thank you, sir. So moving ahead with the next presentation, which is by Dr. Shubhendu Pradhan. And he's going to talk on the spatial analysis of cirques in the Northwest Himalaya, application to paleo-environment reconstruction. So Dr. Pradhan, please.
Good morning, all. Am I audible?
Yes, you are.
Okay. So,
and please, just a request, please be short and try to complete in 5 minutes.
Yeah, sure, ma'am. Sure.
Thank you.
So my topic is spatial analysis of cirques in Northwest Himalaya and its application in paleo-environment reconstruction. So for my study, I am using cirque, a bowl-shaped glacial landform, to understand its climate condition during its formation and its pattern of evolution. So my study area is Northwest Himalaya, which comprises of 3 ranges, Jahaskar in the south, Ladakh in the central, and Karakoram in the northernmost regions. And two source of precipitation is present in the study area, that is Indian summer monsoon and mid-latitude westerlies. Sorry. So the objective is to prepare the SARCs in Northwest Himalaya is very less studied. The study is very limited. So in this paper, we tried to prepare the first detailed map of modern and paleo SARCs in Northwest Himalaya, and to estimate the Pleistocene ELA using Sauk flow Rajapaksa, and to understand the contributing role of different parameters like topography, lithology, and climate for its formation and evolution. Next slide, please. Okay, so to summarize my results, so first the ELA is equilibrium line of altitude, which is the zone between zone of accumulation and zone of ablation. So in this ELA, there is zero net accumulation. So on my study, when we used SARC as a proxy to understand the ELA, we found that ELA decreases to the north along the precipitation gradient of Indian summer monsoon. So in the first figure, if you see, it is from west to east. In the western sector, ELA is deeper, which indicates the area with higher moisture supply have deeper ELA. So SARC closer to the moisture supply have deeper ELA and more incised, less thickness, and more elongated. Now coming to the controlling factors, first altitude. So what I found that SARC become symmetrical distributed with increasing altitude. In the dark colored rose diagram, you can see from A to F the altitude is increasing. In lower altitude, all SARCs are facing towards a particular direction, that is north. As we move to the higher altitude, SARCs are getting distributed in all the direction. So what is the reason? Because in southern faces there is continuous cloud cover and increased lapse rate, which makes the southern place also suitable for glacial accumulation. So higher altitude becomes in higher altitude SARC getting distributed clearly. So SARCs are northward aspect because the north face have low insolation and higher precipitation. That's why most of the SARCs are faced towards the north. And mean aspect of all the SARCs in Northwest Himalaya is pointing towards the northeast direction, which is similar to the paleo wind direction in last glacial maximum, that is 20,000 years. Next slide, please. Now coming to the controlling factors, next is wind speed. When I plotted all the SARCs in the wind map, I found that all the SARCs are forming in the high wind speed region. In the map, in the first figure, you can see the blue indicates high wind speed. So all the SARCs are forming in the high wind speed regions, which indicates the SARCs get ice accumulation by wind drifted accumulation, not most by wind drifted than precipitate. Now in the second figure, when I plotted size to the area, I found that the low size, the SARCs with low dimension, that is younger SARCs, are more abundant than the older SARCs. And in the third figure, you can see when I plotted length and width, I found that younger SARCs, the SARC lengthened more than widened because the headwall erosion. SARC, when glacier move, the headwall erosion becomes more than the lateral erosion, which that's why the length increases more than the width. Second is a climate condition, the cloud condition. When I plotted the SARC aspect along with the SARC depth, there is no correlation found between them, which indicates that the SARCs in the Northwest Himalaya are formed in highly cloudy conditions. Next slide, please. Now, the development process, when I plotted the size along with length, width, and height, I found that there is when the correlation factor is 1, we can say that the SARC developed isometrically. But here we didn't find any value near to 1. So the inference can be SARC developed allometrically. That means the vertical erosion, lateral erosion, and lateral erosion are different rates. Now coming to the last inference, the glacial bursaw. The glacial bursaw is a hypothesis which says erosion limits upliftment. That means the area which have higher elevation will erode at a more rate than lower elevation. So it can be proved by showing strong correlation between peak elevation and ELA. When I plotted the ELA and peak elevation. Here the black trend line indicates high peak elevation, and the gray line indicates ELA, which moves almost parallelly, which indicates strong correlation between them. So I can infer that the mountains are shaped by glacial bursts in Northwest Himalaya. So summarizing all the conclusions, first ELA decreases to the north along a precipitation gradient of ISL, which follows the global ELA versus latitude pattern, that is equator have higher elevation ELA and pole have lower elevation ELA. And cirque closer to the moisture supply have deeper ELA, more insides, less steepness, and more elongated. Coming to the controlling factors, cirques become symmetrical distributed with increasing altitude. Now lithological control is absent, and cirque having northward aspect because it have a tendency to keep positive mass balance, because north face have less insolation at higher precipitation. So at higher altitude, even southern face become suitable for glacial occupancy because it have increased lap slate and continuous cloud shadowing. And cirques Northwest Himalaya are formed under cloudy conditions, and it gets ice by wind-drifted snow accumulation. And the main aspect of cirques pointing towards the LGM paleo wind direction, that is 20,000 years ago, the wind direction was northeast, which is our study area cirques also pointing toward northeast. And coming to the evolution pattern, younger cirques are found to be more abundant because a less resistant surface get created as cirque gets old, as the sediment gets trapped subglacially. And through the evolution process, cirque lengthen more than widen because of more headwall erosion than lateral erosion. Also, there is law of decreasing glacial asymmetry with increasing altitude. When we go to higher altitude, the glacial become asymmetric. The asymmetry increases and cirque get distributed uniformly. And the mountains is Northwest Himalaya is set by glacial. Thank you.
Thank you, Dr. Pradhan. That was a nice presentation. So we'll take the next one, which is by Dr. Satyanarayana, and he's going to talk about AI/ML.
Madam, sorry to interrupt. I got an email from Mr. Satyanarayana. He is unable to present. He has medical issue. He regrets that he couldn't present.
Okay. So the next presentation is by Dr. Manish Awasthi, and he will be talking on how the total electron content derived from GPS varies during different phases of the solar cycle. So, Dr. Manish, please.
Good afternoon to all. Am I audible?
Yes.
I am Manish Awasthi, PhD student from GL University, Mathura. The topic of my presentation is morphological study of a low latitude station GPS TEC data during ascending peak and descending phase of 24 solar cycle. Next slide, please. Next slide. Next slide, please. This slide is about the requirement of geomorphological study. The morphological study of GPS TEC data will provide an opportunity to understand the day-by-day variability of ionosphere, impact of solar activities, and magnetic storm on it. Next slide, please. And next slide. Okay. For morphological study of GPS TEC data, we have downloaded the GPS TEC data of Lucknow station for the year 2012, 2015, and 2018 to carrying out its variation at low latitude during ascending, peak, and descending phase of 24 solar cycle. We analyze daily, seasonal, and nighttime variation of GPS TEC data. In the slide, GPS TEC data of each month is plotted with local time. It is clear from the plot that BTEC increase in all the months from sunrise and attain a maximum value till noon, then decreasing continuously and attain a minimum value just before the sunset during all three phases of 24 solar cycle. Next slide, please. In this slide, monthly mean is plotted with yearly mean of vertical TEC data for the years 2012, 2015 and 2018. We observed enhancement and depletions in GPS TEC data. In figure first of 2012, we observed some major depletions in GPS TEC data in the month of January, February and December below yearly mean, while major enhancement found in the month of March, April, May and September, and some major enhancement in the month of June, August and October during 2012, an year of ascending phase of 24 solar cycle. In figure 2 of 2015, we observed major enhancement in GPS TEC data in the month of February, March and April. The blue color lines is for monthly GPS TEC data, which are representing the enhancement with yearly mean. And major depletions we are found in the month of October, November and December in the year 2015 when solar activities was at peak. In figure 3, we found a significant enhancement during April and May, and major depletions from yearly mean in January, March and November months is observed in TEC during the year 2018, which is the year of descending phase of solar cycle 24. Next slide, please. For detecting the month in which TEC enhance and depress anomalously, vertical TEC data for each month is plotted between M plus minus sigma lines for Lucknow station, a low latitude station in Indian region for the year 2012, 15 and 18, which lies in ascending peak and descending phase of 24 solar cycle. Here M and sigma indicates the yearly mean and standard deviation of TEC data. Figure 1 of 2012 is showing that there is no month in which monthly value of BTC exceed the M plus sigma line during 2012. In the figure of 2015, it is clear that the BTC value is below the M minus sigma line during the month of December in 2015. In the figure of 2018, it is clear that VTC is observed above M plus sigma line in the month of May and June, then depleted below M minus sigma line in the month of November during 2018. Next slide, please. This slide is showing the percentage value of previous slide. The first plot is showing the percentage depletion from M minus sigma are 22.58%, and the second slide is showing the percentage enhancement from M plus sigma are 20.95% and 3.37%, while percentage depletions from M minus sigma are 13 and 28% in 2018. Next slide, please. Next. For the study of seasonal variation, we have plotted GPS TEC data for the different season with the seasonal mean for the year 2012, 15 and 18. We observed that TEC maximized during equinox and minimized during winter in ascending phase of 24 solar cycle. However, during peak and descending phase of solar cycle, it maximizes in summer season and equinox respectively and minimize in winter season in both the phases. Next slide, please. Next.
Dr. Manish, you need to conclude in 1 minute.
Okay, ma'am. To study nighttime variation of GPS TEC data, we have plotted the monthly nighttime variation from 18 to 24 hours LT local means local time of GPS TEC data between M plus sigma line for the years 2012 and 15 and 18, which correspond to ascending peak and descending phase of 24 solar cycle. Next slide, please. These figures are showing percentage enhancement and depressions in nighttime data of previous slide. Okay, thank you, ma'am.
Okay, thank you, Dr. Manish. That was a nice observational study. So next talk is by Dr. Bade Saab, and he is going to present his analysis of a newly discovered active cold sea in the Gulf of Mannar. So Dr. Bade Saab, please.
Am I audible, madam?
Yes, you are.
Okay. Good afternoon, everyone. I'm going to present before you the results of my ongoing research, which basically focused on conducting the systematic diagenetic analysis on a sediment core, which we retrieved from the active ship site from the Gulf of Mannar. Next slide, please. So as I mentioned, during our expedition in 2020, we retrieved a gravity core from the active ship site. And what we observed is we could identify the presence of shallowest gas hydrates in a disseminated form at a shallowest depth, which is around 3.2 meters below seafloor. And here you can see we also retrieved a range of chemosynthetic communities at these ship sites, which basically feeds on the hydrogen sulfide produced at the cold ship vent during the anaerobic oxidation of methane. Next slide, please. So as I mentioned, I looked at the rock magnetic record of the sediment core, and based on the magnetic signature, we classified the rock magnetic profile into 3 distinct sediment magnetic zones. So on the top, you can see the different rock magnetic parameters, which basically gives you an information about the composition, the type of mineral assemblages, and the grain sizes. So if you look at the magnetic susceptibility profile, in the uppermost zone, we see a very low and uniform values of magnetic susceptibility. And concurrently, if you look at the Grigite diagnostic magnetic parameter, we see a small few peaks of rise in the SRM by kappa ratio, which gives you an indication about the diagenetic formation of Grigite in the uppermost sulfidic zone. So now if you come down into the zone 2 and zone 3, we see a systematic downcore increase in magnetic susceptibility, which is also accompanied by the increase in the S ratio, and basically identifies the presence of detrital as well as orthogenically formed fine grain as well as coarse grain magnetite in the methanic zones. So now we try to investigate how the magnetic particles in the uppermost sulfidic zone and the lowermost methanic zone respond to range of diagenetic reactions, which are basically produced by the methane-induced geochemical processes. So we extracted the magnetic particles from these different zones, and we looked at the compositional and the textural characteristics to evaluate the processes. Next slide, please. So in the uppermost zone, where we had very low and uniform magnetic susceptibility values, we could observe the well-preserved the detrital, titanomagnetite and titanohematite grains, which are mainly derived from the proximal highly metamorphic terrains and supplied via the Kaveri river systems to the Gulf of Mannar. But if you come into the near the sulfidic zone, we observed various features of oxidation of magnetic particles, wherein we can see a moderate to high degree of dissolution of magnetic particles. On these magnetic grains, you can see different features of diagenetic dissolution, which includes you have etching, pitting, and the lamellae-like structures on these magnetic particles, which provides evidences on the different stages of oxidation of these magnetic particles. Next slide, please. So coming back into the near sulfidic and the methanic zone, what happens is you have huge amount of dissolved hydrogen sulfide, which is produced by the anaerobic oxidation of methane. And this dissolved sulfide reacts with the available highly reactive iron, and the reaction proceeds towards the pyritization, where you have formation of well-developed rhombides of pyrites of different sizes. In addition to the sulfidization, we also notice the magnetization process, which is mainly deals with the partial oxidation of magnetic particle. So what happens is, during magnetization, you have a preferential leaching of Fe2 iron out of the titanomagnetic particles, since it gets very quickly detached from the titanomagnetite grain as compared to Fe3+. So this shrinkage cracks which you see on the top of the grains, it basically results from the internal stress which is created during the superficial oxidation of these magnetic particles. So we were very much successful in understanding the different stages of oxidation of magnetic particles, and followed by the magnetization and sulfidization process in this active cold-strip vent. Next slide, please. Here you can see a huge carbonate crust, orthogenic carbonate crust, followed by chemohum, which we recovered from the SIP location. Thank you very much.
Thank you, Dr. Badesa. That was a very nice talk with a very good amount of detailing on the magnetic minerals and the different stages of oxidation associated with these cold seeps. So thank you once again.
Yes, thank you, ma'am.
Yeah. So we move ahead with the next presentation, which is by Dr. Satyavani.
Sorry to interrupt again, ma'am. She
Okay.
won't be presenting.
All right, all right. So the next presentation is by Dr. Kadam, and who will be presenting his results on the sediments over the continental shelves of India, and what are its implications from the source
Am I audible, ma'am?
processes. So, Dr. Kadam, please.
Yes. Am I audible, ma'am?
Yes, yes, you are audible. Please go ahead.
My name is Nitin Kadam. I am working with Dr. Firoz Badesa. I am a PhD student at CSIR NEHU, Goa. So I'll be presenting today the mostly rock magnetic proxies study of sediments on the continental shelves of India, implications to the sediment source to sink processes. Next slide, please. Yes. So figure A shows the study area location. Study area location. 3 gravity cores were retrieved from the continental shelves of India. These core locations are unique in terms of the geology of the catchment areas, then the river length, drainage area, and their sediment loads. Now, first core was retrieved from the Gulf of Khambat. The code of the core is SSK 40 GC07. Then second core was retrieved offshore of Ganga and Brahmaputra River, SSK 35 and GC14, as you can see in figure A. And third core was retrieved offshore of Pennar and Swarnamukhi River, SSK 50 and GC14. So these core locations are unique in terms of the geology of the catchment areas. If you consider the suppose the first core, then the catchment, the rivers that deliver the sediment load are Narmada River, Narmada, Mahi, Tapti, and Sabarmati rivers. The catchment areas mostly consist of Deccan Trap rocks with mostly Deccan Trap rocks with some Precambrian rocks and quaternary sediments. If you go to Pennar River's sediment core, then the catchment area rocks are mostly consist of Kadapa supergroup rocks and granitic and gneissic terrains. And then the third core, that is offshore of Ganga and Brahmaputra River, the catchment area is consist of diverse rock types with ages ranging from from recent to Precambrian rocks. So the subsampling and all rock magnetic measurements were performed at CSIR NEHU, Goa. Routine rock magnetic measurements methods were followed, from measuring magnetic susceptibility to remanent magnetizations. Then figure B shows the downcore rock magnetic record of first core that is taken from Gulf of Khambat. The magnetic concentration proxies such as magnetic susceptibility, that is KLF, ARM, SIRM, show the highest values of all the three cores, and they are mostly consist of the content of the magnetic mineral is highest in this core. Based on that, we divided this profile into three zones, zone 1, 2, and 3. In zone 1, the values are high and consistent, KLF values. And in zone 2, the values are increasing. And in zone 3, the values of KLF are decreasing. The magnetic grain size proxy, that is ARM by SRM, shows presence of both fine and coarse magnetic minerals. On S ratio is consistently high. That means the magnetic mineralogy mainly consists of ferromagnetic minerals. And figure C shows the SCM images of the magnetic particles. They show the that grains are freshly exposed and with modest magnetization features. Next slide, please. Next slide. Yeah, the record of second core, that is of GB, shows a marked shift in magnetic susceptibility at around 110 cMe SF, around 10, at 110 centimeters. There is increase in magnetic susceptibility, which most probably reflect the increase in mafic material compared to the felsic material. Magnetic grain size consists of fine and coarse grains. S ratio is highly fluctuating. That means the magnetic mineralogies consist of both ferromagnetic and antiferromagnetic minerals. And at 110 centimeter, there is also fluctuation in the physical mean grain size. As you can see, the core location is in the western side of swatch of no ground. That is nothing but a submarine canyon which traps the sediments received from the Ganga Brahmaputra river and delivers that sediment to the Bengal fan. So most probably this swatch of no ground is trapping the coarse magnetic particles, and it is providing to the Bengal fan. So this there is a major role of this swatch of no ground in the sedimentation or record of this core. And the figure C shows the that magnetic grains have undergone magnetizations. Next slide. Next, yes. So this third core is very systematic in terms of zonation. You can see the decrease and systematic decrease and increase in the values of rock magnetic parameters. Susceptibility is also a opposite relation between magnetic grain size and content is seen. Both the occurrence of fine and coarse magnetic particles. In last zone, we can see the sudden drop in magnetic susceptibility and S ratio. So it basically represent the increase in the after 180 centimeters, you can see the sudden increase in the S ratio. So that means there is onset of ferromagnetic minerals, which is nothing from DCB source material. And in figure C, show the biplots of different rock magnetic parameters, which were successful in delineating the provenance and different depositional processes. You can see in distinct groupings of all these three core sediments. And in supposing second biplot, which is of ARM by SRM and KLF, you can see that finest magnetic particles were present in Ganga sediments, whereas coarses were found in your PS shelf. Yeah, next slide, please. Yeah, concluding remarks. In first core of NTMS, strong and energetic estuarine shelf and sediment exchange system limited the density-based fractionation processes, resulting in the deposition of fine as well as coarse magnetic particles on the shelf region. In off-GB core, a marked shift in magnetite content and grain size when manifested by the large fluctuation in physical grain size at 110 centimeters reflect a distinct change in detrital sedimentation, which is controlled by the changing magnetic contribution from mafic versus felsic sources. And in PS core, a clear transition in magnetic mineralogy, that is S ratio, followed by an increase in magnetic content and abundant presence of titanium magnetite particles from 180 cmb phase onwards, marks the commencement of DCB source, that is Deccan Trap source sediments from the distal region via southerly directed longshore drift system. Thank you, ma'am.
Okay, thank you, Dr. Kalam. That was a very interesting presentation. So next presentation is by Dr. Piketty, and the talk is on paleo-methane seepage events at a submarine mud volcano in the Andaman Sea. So Dr. Piketty, please.
Madam, I got an email from Dr. Piketty and she said he will be presenting, but I don't.
No, I will be presenting on behalf of Dr. Piketty because he is on election duty.
All right, please go ahead with your presentation.
So the talk will be uploaded by you.
Yes, 1 second, I am sharing this.
Thank you very much. Myself, Dr. Aninda Mazumdar, and part of this Andaman gas-headed and this program. So this is about paleomethane seepage events at a submarine mud volcano in the Andaman Sea. And Dr. Pawan Degangan, Dr. Shriram, myself, Mahale, Gatale, Rajurkar, Gautam, and Aditya Piketty, we are the members of this program. Next slide, please. Yeah, so mud volcanoes, we know that we detected some mud volcanoes in the Forak basin part of the Andaman Islands. And the mud volcanoes form as a result of emission of depressurized pore water, gases, clay-rich material from the deep-seated sources. And mud volcanoes can occur either on the land or on the seabed. Mud volcanoes can occur along the fault fracture or active plume margin. And why we are interested? Mud volcanoes are one of the significant contributors of methane. And mud volcanoes are key features to understand the regional geological processes in their place of occurrence. So an Andaman Forak Basin is known for occurrence of mud volcanoes. Next slide, please. So you can see that these are the core location. This is the core location. And in this region, we recorded some mud volcanoes. So gravity core and spade cores were collected along with routine CTD profiling to see the water temperature, pressure conditions. The sampling was carried out during the November-December in 2021 and on board Sindhu Sadhana, which is the NIO's research vessel. And this is the core location. Next slide, please. In this core, gravity core, we have recorded this, and in the spade core also, we have recorded chemosynthetic organisms like belonging to the family Thiaceridae and Vesicomidae. These organisms are capable of generating body mass by using hydrogen sulfide. So hydrogen sulfide is converted into elemental sulfur and energy, which is then used to produce the body mass. And this is done by chemosynthetic bacteria within the specialized gill tissues. And you can see within the sediment, there are white carbonate layers. Throughout the core, we have white carbonate layers. And also in this region, we have a lot of mud blocks and carbonate blocks. Carbonate chunks within the mud blocks, you can see this is a big mud blocks, and these are the carbonates. These are the calcium carbonate chunks, and these are the fossils. And next slide, please. So we carried out the carbon isotope and oxygen isotope ratio measurements, this delta 13C, of the carbonates chunks of the carbonate pieces or carbonate layers which are present, as you've seen in the whitish portions in the dark sediment. And you can see that they are isotopically very negative, -45 to -40 and -35, very depleted carbon isotope ratios. That means they are high in C12 relative to C13. And that possibility exists if there is a lot of methane seepage. Although we haven't yet recorded or measured methane concentrations in this region, which we will be carrying out. But the carbon isotope ratios of the calcium carbonate crystals clearly show that methane is the source of carbon for the precipitation of this calcium carbonate, which happens when there is a significant amount of methane diffusion or advection into the mud volcanoes from the deep, and which is then subsequently converted to bicarbonate ion by anaerobic oxidation of methane, which is carried out by sulfur-reducing bacteria and methanotrophic archaea in a synergetic process, which results in the formation of high concentration of bicarbonate and which subsequently reacts with calcium ion to precipitate calcium bicarbonate. And they form concretions or tubular or some other variegated structures of calcium carbonate precipitates. So the several carbonates and mud samples recovered at the different depths, multiple types of carbonate precipitation indicating different precipitation conditions. Highly depleted carbonates possibly indicate microbial methane source. The -40 to -35 value that we are recording possibly indicate microbial methane source, although it is right now little bit difficult to say that because it depends on the fractionation factor of the microbes involved, which converts the methane into bicarbonate ion. So we right now do not know the fractionation factor. If the fractionation factor is very low, then it's a different kind of interpretation, or if the fractionation factor is high, then it's a different interpretation. So we do not know that. But apparently, it looks like a microbial source of methane. So dead chemosynthetic shells show paleo H2S seepages, possibly driven by anaerobic methane oxidation. So presence of H2S is also indicated by chemosynthetic shells, which justifies this hypothesis that anaerobic methane oxidation was a dominant biogeochemical process in the sediments here, and the mud is possibly of Miocene deposits, which is referred to Basu et al. 2012. Thank you very much.
Thank you, Dr. Majumdar, for your very interesting talk on the submarine mud volcano. And we will discuss this more in the discussion session as to what are its large-scale implications. So now we will come to the next presentation, and which is the last presentation of this technical session. And it is by Dr. Ramesh, who is going to talk about multi-attribute analysis using PCA and FCC. Dr. Ramesh, please, you may go ahead with your presentation.
Okay, thank you, ma'am. Good morning, everyone. Myself, Anmirit Ramesh, PhD student of Satyavani at CSIR and GRI. Today's topic is multi-attribute analysis using PCA and false color composition, a case study from Andaman offshore. Next slide, please. As we know, seismic attribute analysis is widely used for geological interpretation. It is the first picture of geological interpretation. Nowadays, so many attributes available to address even a single problem. So it is very difficult to choose which attribute is perfect for our study. For that, we used principal component analysis to give a multi attributes in one picture. In principal component analysis, highest variance species give the enhanced picture of seismic section, where lowest species contains noise. It's some kind of noise. So we have done a principal component analysis on multiple attributes and extracted first few pieces showing highest variance. And then these first few pieces are visualized using false color composition technique. And next slide, please. This is the methodology. First, we have normalized the data. Data means each attribute, and then multi-attribute sample is prepared for each time trace, and then covariance matrix is estimated for these attributes, and then using this covariance matrix, we have calculated eigenvalues and eigenvectors, and percentage of variance is calculated using eigenvalues, and then we have extracted first few pieces which are having highest variance, and then we have prepared false color composite images by applying red, green, blue colors to PC1, PC2, PC3. I mean first three pieces. And next slide, please. In this, in the first table, we can see 13 attributes. We have used 13 attributes to calculate principal components. It gives 13 principal components, and percentage of variances of each principal component is plotted on the right side. And in this plot, we can see most of the variance, that is nearly 75% of the variance is concentrated on first three pieces. So we have taken first three pieces for our study. And the next slide. In this, to that first three pieces, we have applied red color to PC1, blue color to PC2, and green color to PC3, and prepared a false color composite image, which is the second one, FCC image. And the first one is a stack section from Andaman offshore region. In this false color composite image, we can see the enhanced reflections in the overall image, and then the reflector indicated with yellow color is enhanced. That means that noise level was reduced, and the blue oval shows the amplitude blanking. That yellow indicated reflector is interpreted as BSR in Satyavani et al. In 2008. So above the BSR, we observed this amplitude blanking, and on the right side, in the red circle, in the stack section, we can see the noisy image. I mean noisy reflector, and it is comes in the better way in FCC image. And these are my conclusions. Thank you.
Okay, thank you, Dr. Ramesh, for your nice presentation, which was, which was very short but very crisp. Thank you for that. So with this, we have come to the end of this technical session, and may I now request the organizers to suggest the way forward.
Yeah, we can go ahead with some discussion, madam.
Yes, sir. Sunil sir has arrived, so we will request him to please take the discussion session forward.
Yes. So now I think we can have some discussions. I hope all the presenters are present.
Sir, out of 14, 11 presentations were made.
Yes. So all 11 speakers are there. Then we can have some discussion, and I request audience to ask questions if it is there.
We can ask Dr. Meghali to give a short report of the session.
Yeah, that we have requested in the beginning, Dr. Barua to prepare a report, but she can tell even now, so if she feel comfortable.
Okay, sir, I will prepare a concise report and we'll send it.
Yeah.
Okay.
You can say something, how many presentations and all.
Okay, sir, out of 14 presentation, 11 presenters presented.
Yes.
Sir, can we take some questions from the participants?
Definitely, we have got 15 more minutes. There can be some discussion. If anybody has got any question, you are free to ask or clarify or give your opinion, suggestion, whatever. Because they were of diverse fields, so maybe.
Sir, can I ask one or two questions to the?
Please go ahead.
Okay, sir. So actually my question is to Dr. Akilan.
Yes, madam.
Yeah, so this zenith, this ZTD anomalies that you have shown due to the, I mean, you found because of these, the dry gas influx because of the earthquake. So I understand that there will be some background dry gas impact also. So how did you, segregate this, the two effect?
Madam, from the main shock to the aftershock means completion, there is a drop in the EZTD. Means during the earthquake, there is a drop. We checked with another earthquake also. That time also during the earthquake, there is a drop. Yeah, co-seismic period.
But did you take any normal period also? Because what happens is there will be always some dry gas in the atmosphere, and that will be introducing the delay.
Madam, in the first case, after the foreshock is over, it is a normal period. In the second case, before the co-seismic period, there is a normal period. In that, there is no drop in EZTD.
Okay, so that is what I wanted to see, that you have ensured that that effect is.
Yes, madam. Yes. Yeah.
Okay. Thank you, Dr. Akilan.
Thank you very much, madam.
Yeah. So my next question is to Dr. Sudesh, and I mean he presented the results for this reactive nitrogens. So the finding was that during the Rabi season, because of the biomass burning, all the ions are more than the Kharif season. But also it could be due to the less dispersion. If the meteorological conditions are not favorable to take away those biomass, you can find more, those reactive agents during the Rabi season. So have you analyzed any meteorological parameters like wind, humidity, rainfall, temperature, any such parameters?
Hello. Yes, ma'am. I have analyzed the meteorological parameters. Wind roses also I have plotted, and the wind directions were mainly very diverse during different months of the year. Like monthly variations I have shown. But one reason is I have also included in the presentation the dispersion of pollutants. But ma'am, during winter season, there are more stable atmospheric conditions, which causes less dispersion.
Right. So you have studied those boundary layer stability aspects also in your study, right?
No, ma'am, not the boundary layer stability aspects, but only the temperature, relative humidity, and wind roses.
Okay. So this is just a suggestion that this is a very good study and very pertinent study also. So maybe you can take it further by using more and more of these weather parameters.
Yeah, sure, ma'am. Ma'am, actually, it is my PhD work only. I haven't submitted yet.
All right. So good luck for your PhD. Thank you.
Thank you, ma'am.
The next question is to Dr. Badesa. Actually,
yes,
So you have, are there any known active these cold seeps also present in your site? The one which, apart from the one which you have discovered?
Yes, ma'am. We also have sites, the relic sites or the non-seep sites also. And we are presently working on analyzing the sediment cores from the relic site.
Okay, because if there are any such already discovered cold seep sites, that will give you a good clue to analyze your results from your discovered site.
Yes, ma'am.
Okay. Thank you. And my last question is to Dr. Majumdar. That was a very interesting one on the submarine mud volcano that you have found in the Andaman Sea. Actually, in one of my trips to Andaman, I also saw this, the active mud volcano over the land on in one of the islands actually. So, are these volcanoes still active? That was my question.
These mud volcanoes, yes, there are some signals. We got those geophysical data are in the process of interpretation. There is some signs of activities. these mud volcanoes. So we collected the CTD profiles and the water sample in which we are for right now measuring the methane concentrations to see that if methane is seeping out from there. But the very presence of calcium carbonates, which are soft calcium carbonates with the extremely depleted carbon isotope, is a telltale signature of methane seeping at shallow depth.
Okay, so now, continuing with that, actually, what is the large scale implication of this? Okay, so it is giving you the methane. So is the quantity so high that it will have a, the climatic impact or any such thing?
Oh, large scale implication means there are possibility of gas hydro deposits underneath this mud volcanoes.
Mm-hmm.
Some of the hydrates, as Dr. Badesa was talking about the Mannar Basin, some of the hydrates sometimes are located at very shallow depth.
Okay.
And the other could be at much greater depth, because when the hydrate comes from deep and it comes up, and then within the stability zone, it again a layer of hydrate can form, which forms the shallow component of the hydrates. So the hydrate deposits are also, of course, known from Andaman, but that is mostly from the Backarc Basin.
Okay.
In the Forearc Basin, we are seeing that that the possibility that hydrate is there underneath.
All right. Thank you.
Thank you.
Thank you, sir. Thank you from my side, please.
Yeah, okay. So I have some, I need some clarification. Actually, my first question is from the talk given by A. Akilan. So he was mentioning that the Antarctica, the black carbon is he thinks that it is because of this volcanic eruption, not because of man-made activity, so anthropogenic activity. So what is the basis for this conclusion? Why do you think it is not anthropogenic?
Sir, it is a very large area, means Antarctica. I mean, this black carbon is from volcano. It is a large quantity. It is coming. Means 25 stations are there in Antarctica, and there are few people are there. Few generators are running. This small quantity of effluents cannot make this much anthropogenic activity in the troposphere. That is my understanding. But these volcanoes, it emits several tens of tons of gas.
No, that's correct. But do you have some tracer which you can study and pinpoint that this is, you based on the area and based on the availability you are referring, but is it possible to pinpoint based on some geochemical tool or some proxies that it is volcanic, not the anthropogenic?
Yeah, the time is perfectly matching, sir. Timing is it is matching, and it is along the circumpolar current. The stations are there.
But it means in Antarctica only during that time people have observed this, or other time also?
No, during the means just before the volcanic eruption there is a black carbon measurement, and after the volcanic eruption there is a black carbon measurement. It is amplitude is very high.
Okay.
This much within no time, this much amplitude will not happen.
No, that's fine, but maybe it will be a good idea to have some proxies studied so that we can pinpoint that it's coming from volcanic activity.
Yeah, we can do it.
Okay, thank you.
Thank you very much.
Yeah, and the next I would like to clarification from Sudesh. You have observed higher potassium during Rabi season, but when you were mentioning Rabi season, what is the time of the year? Which month? Sudesh, you are there? I think she has left.
So she's there, but she's not responding.
Okay.
Sudesh, are you there? Hello?
Hello?
Yeah.
Yes, sir.
Yeah. So when you are getting higher potassium in which month? Rabi season you have mentioned, but I want to know month.
Okay, sir, I have to look into the data for that. Actually, I have plotted the average values here.
My question, why I'm asking is because the burning, the paddy residual will be even more than the rabi residuals. So that could be because of paddy residual burning.
Yeah, sir, paddy residual are more, but if it also depends region wise. Actually, in my region, there is more wheat residue burning.
But it is so localized.
Not so localized, but sir, nearby my site, there are no fields of paddy because there are irrigation problems. But like 4 to 5 kilometer distances, there are paddy field.
Yeah, because the entire IGP plane is getting affected because of that. So I don't think it should be so localized. And what was the boundary layer depth during that when you were referring it is high or low?
I haven't measured it, but only
no, you cannot measure
general
it.
conditions.
No need, but I think it is available. So if your boundary layer depth is decreasing, the concentration will increase because of that also.
Yes, sir.
So have you correlated that?
Not with the boundary layer, sir.
That is very much required because you are reducing the volume, so concentration will go up. If it is like that.
Okay, sir. I will look into it and add more details of boundary layer.
Okay. Thank you very much.
Thank you, sir.
And I would like to one question on this multi-proxy study of sediment. Kadam.
Yes, sir.
Actually, you have your result was very good. Variation in sediment forces based on your magnetic measurement. But what could be the region when it is shifting? It is from one source to another. I think what is the region? Even like Ganga basin you have shown, and even the further down you have shown. So what is the region? Whether it is climatic or some other factors. So could you please tell something?
Yes, sir. Possibly, sir. Actually, we don't have dates of this core, no, sir. So there is also possibility that because mainly the sedimentation offshore of GB is mainly controlled by the monsoon-driven processes in the catchment areas. So yeah, that could be the reason, sir.
No, but why the source is changing at a given point or given time when it is changing from one source to another? What could be the reason?
Yes, sir. Suppose considering in GB basin, so there are many in-transit depot centers in between. So this GB system is compared to all other two sites. There on these the drainage area, if considered, it is huge. So in between these monsoonal processes, suppose material is getting from because it is a tightly closed system in GB system. So if so that could be the reason, sir. Depending upon lithology, sir, mostly how mythology.
No, that is not exactly the question. When it is changing from one lithology to another, there must be some reason.
Yes. So compositional variability, sir.
I think you should look into that and then we'll discuss it.
Okay, sir.
Okay, thank you very much. Thanks a lot. So I think we have completed our discussion. If somebody else wants to ask something. If no more question, I think we would like to thank all the speakers for providing very nice talks and all the scientific information and making this session very successful. Thank you very much. And I would like to thank our co-coordinator, Rasmi Sharma-ji, and also the rapporteur, Dr. Barua. And very much thank to Professor Devesh Walia-ji for providing this opportunity. Thanks a lot. And so it is up to you what I do there.
Thank you, sir. Thank you. It was nice to be with you conducting this session. And I too thank the organizer for giving me this opportunity. Thank you.
So, Balia-ji.
Yeah, thank you, Chairperson Dr. Sunil ji and co-chairperson Dr. Rashmi Sharma ji for this very important session. And thank you, Dr. Meghali, to be rapporteur during this program. So, dear friends, now we'll be leaving for lunch break. If there is no other announcement by Abhay Bansal ji, and we'll be meeting at dot at 2. Although this link will remain open, but you can join 5 minutes before 2. Yeah, Abhay ji, any announcement, anything?
No, sir. Thank you. Thank you, Dr. Sunil Singh. Thank you, Madam Rashmi Madam. And thank you, Devesh ji, organizing very well. And we are happy. Thank
So
you.
let
We
us,
can. Yes.
Yeah, let us meet again at sharp 2, 5 minutes before 2 rather. 1:55. See you.
Thank you. Thank you very
everyone.
much.
Thank you.
Thanks a lot. Thanks.
Thank you.
Good afternoon, everyone.
Good afternoon, sir.
So after afternoon session, especially after the lunchtime, is very difficult. But still, we see more than 40 participants, so it is very encouraging. आज तो since morning there was no sun. The sun has not. We are unable to see the sun at Shillong. So it is good that we are doing it virtually. Otherwise, you people would have been frozen.
Yes, sir.
शाम को hail storm का वो है prediction IMD का.
Okay, sir.
Sir, it is crossing the cold of Dehradun. देहरादून से ज्यादा ठंडा है हमारे यहाँ.
गुड आफ्टरनून देवेश जी, यहाँ पर भी सन नहीं है और क्लाउडी है, कोल्ड है. It's very difficult. You can see me and then yes.
Yeah, that's right.
Kalachan full topi in there.
अरे भाई, टोपी वाला जो ऐसे प्लेन वाला आदमी टोपी पहनने के बाद कितना मुश्किल होता है मालूम है आपको?
Yes, sir, you are right. From Hyderabad to Dehradun is
very cold, very cold.
अभी अब रूम के अंदर तो ठीक है, बाहर जाते एकदम a lot of difference.
I can understand that.
So good as a whole. What Devesh Walia ji is telling that going on very well. Lot of participants. So it shows a signature of success. So both our organizer and Devesh Walia ji, Bansal, and our part of IGU are extremely happy that it is going on in the right way.
Yeah, correct.
So sessions bhi अच्छा ही चल रहा है. Papers are also being presented. Some of the people are busy in the election duty here also, and some of them are also. I think those who have done any test, almost 80-90% will be positive. So those things are also there.
Election duty में pre-election meetings.
Pre-election, अभी last 1 month से pre-election हमारा भी all scientists are involved.
Oh really? My God.
Yeah, nobody is coming to office.
Yeah.
We cannot say anything against this duty.
Yeah, God, absolutely. There is no.
And, anyway, some of our scientists are also enjoying. Always they say they are in duty.
But the election process is a risky one these days.
Yeah.
Enjoyment is at the risk.
That's correct.
So if Abhay Bansal ji permits, we can start the afternoon session.
Yes,
already
sir.
44 participants are there.
Yes, sir. Madam Rima is there and Professor S.P. Sharma.
Yeah, let me just check.
Bansal ji.
Yes, sir.
This EC meeting and session will be in parallel or what?
No, sir, no EC meeting, no general body meeting.
Why?
No general body, no EC meeting.
I came for that only.
I also opened because
that's right. No, at 2 o'clock he said it's EC meeting na, in that agenda.
In the agenda, but they have postponed. Yeah, and
we discussed with President. President told we have to give.
You have announced that?
We are not yet announced. We are not sent any email to EC.
Announce करो उसको.
And what about tomorrow general body meeting?
No, sir, no.
अभी announce कर दो.
जी sir.
Announce करो. That's better, no? You send a mail to all EC members. Exactly.
But sir, we not send any email to EC member for this EC meetings.
Okay.
Okay, since it is the agenda, I thought that no, it should be there. That's all.
So this should be the new EC, right?
No, that election result has not yet come.
Oh, okay.
And we are planning in end of February this EC meeting and general body.
Okay.
We have to give notice of 2 weeks before organizing this PC and general body.
Okay. Okay, then
Go ahead with the session then.
go ahead with this.
Thank you, sir. Sorry for that.
No problem.
Yeah, it needs to be informed. We can send the email maybe right now also, or we can just inform right now that
Yes.
there will not be any executive committee meeting of IGU.
Okay, sir.
It is listed in the agenda from 2 to 3.
Okay, sir.
So we'll make one announcement and send it in the chat box also.
Yes,
So
sir.
that if anybody joins thinking that this is the EC meeting, should come to know.
Yes, sir.
Can I ask, Kachan, I will take leave then. Eh?
Okay.
Bye.
You have to take permission from Professor Walia.
Yeah. That's right, actually.
Yeah. So we should.
Professor Walia, is this not a EC meeting? This is Rashmi?
No. All of us joined like that only.
All right.
Yeah.
Okay, I'll leave that. Thank you so much.
Some of us joined thinking that EC meeting, but the decision was taken maybe a day before yesterday to postpone this EC meeting, which.
Okay.
All right. Thank you.
No problem. You can go ahead.
Yeah. Similarly, the general body meeting also. But there should be a notice. We should send a notice very clearly stating that. But Bansalji will post it on the chat box. You also can write. Because anybody joining may come to know if he or she is joining because of the EC meeting.
Yes, sir.
So let us start the technical session 7. But Sharma ji hasn't yet joined.
Just call him. You can start maybe. I'm calling him. Rima, Madam Rima is there. You can start.
Yeah, Professor Rima is there. So we can request Professor Rima to chair the session. If Professor Sharma joins later, then both of you can share the responsibility. Otherwise, Professor Rima, we would like to request you on behalf of IGU to be there with us to chair the session. Hopefully, you won't mind being there. And along with the chairperson of the session, we have Dr. Arvind to help the chairperson, Professor Rima Chatterjee. Hopefully, Arvind ji is there. Arvind ji, are you there?
Yes, sir. Yes, sir.
Yeah, because your video is off. It's okay. If your connection is slow, you can keep your video off. No problems. So let us start. So the technical session 7, after the lunch break on the second day, I give the dais to Professor Rima Chatterjee to take forward this session, please.
Sir, Sharma is joining.
Hanji?
With Professor S.V. Sharma is joining.
Is joining. All right. So, should we wait for a minute? Should we wait for a minute?
Yes, we can wait for 1 minute.
Acha. But let us start as we requested.
Okay, sir. Please.
Because sometimes at the last moment, connectivity also takes 3-4 minutes.
Okay, sir. You can start, please.
Because after this also the program is very tight. Schedule is very tight.
Go ahead. Please go
Today
ahead,
up
sir.
to 5:10. He hasn't yet joined. So, yeah, so on behalf of IGU, we welcome all the participants for this session, session 7. So I request Professor Reema Chatterjee to please take forward this session on behalf of Organizing Committee, 58th Annual Convention of IGU with the help of Northeastern University Shillong. Madam, please. Oh, he has joined now, it seems. Yeah, Professor Sharma has also joined. So the responsibility of this session goes to Professor Sharma as the chairperson and Professor Reema as the co-chairperson of this program, along with Dr. Arvind as the rapporteur. So you may please take forward, sir, from here. You need to unmute.
Okay. Can you hear me?
Yeah.
Okay. Okay. Just I joined. I just came from the office. Within 2 minutes, I'm coming to. Yeah.
He is taking a minute.
Yeah.
Just to start. So. So altogether 12 presentations are supposed to be there in this session, and out of which if organizing committee can update, how many of them have come?
9.
9. So it means 9 presentations will be there, sir.
Okay. Okay. Thank you. Yeah. Good afternoon to all of you. Together with my co-chair, Reema Chatterjee, and our colleagues. Because we are already late, I will start. So the first speaker, Deep Kumar Singha, are you there?
Yes, sir.
Okay. So our first presentation is Dr. Deep Kumar Singha. He is speaking on modeling of pore pressure using seismic velocity, a case study of Upper Assam Basin. So Dr. Deep, you start, please.
Yes, sir. Thank you, sir. Good afternoon, everyone. I am going to discuss about this pore pressure predictions from velocity data, and that is a case study in Upper Assam basins. And all of you know, recently there is a happening of blowout, gas oil blowout in 2020. Assam, there is a huge destructions of blowout due to the leakage of the gas. Some officer has been died. There's a means biodiversity problem. So a lot of means losses of money, and this well blowout is completely related to the well designing. How you design your well during the drilling for hydrocarbon productions. And this well designing depends on the selection of the mud weight, minimum mud weight and maximum mud weight. And for choosing the exact and appropriate mud weight, you have to know the information about pore pressure, the pressure which is exerted by the fluid. Slide is not changing. Currently, change the slide. Okay, so the pressure is pressure which is exerted by the fluid within the rock is called as a pore pressure, and basically these pressures remain hydrostatic when sedimentation depositions occur. But in some area, in some condition, under some geological condition, such as disequilibrium compactions, tectonic compressions, aquathermal pressurizations, dehydrations, and hydrocarbon generations. Out of these, pressure can be so much used and highly pressurized. So in that case, if you drill a well and if you cannot defend this pressure, so fluid can enter into the borehole, and consequently, a well becomes unstable, even it becomes blowout. So pressure is very much important for designing a well in each and every sedimentary basins, that is either in Assam basins, or some blowout is also happened in KG basins 1992. So I would like to show you how do you identify the overpressure zone from oil log data. So I have plotted, you can see the porosity, that porosity is density porosity and sonic porosity together with depth. So if there is any high pressure, there is no separation between these two porosity. But once there is a difference between this density porosity and sonic porosity, so they are assumed to be generations of high pressure. So you can see below 1200 meter, you can guess that there may be presence of high pressure. And near to the 1800 meter, there's a clear separation between density porosity and sonic porosity. So that is indications of presence of high pressure. And that same things also been identified from sonic travel time if you plot with depth. So there's a sonic travel time for shale is clearly departure from normal compaction trend. So this depth is identifying or signifies there's a presence of high pressure zone. And from oil data, we can understand that Kupili formations basically responsible for creating this overpressure zone, followed by some portions of some little bit mild pressure is present in barrel formations. Now in next, I want to show you, tell you that how do you compute this pore pressure. Pore pressure has been estimated directly from either RFT data, DST data, or MDT data, or it can be modeled from velocity data. And how do you model? We generally use these equations. Eton equations, this is the equations which is given, that is related to the vertical stress and normal travel time. And also we can use these Bauer's equations. This Bauer's equation is nothing but a transformations of effective stress from velocity. So that's mean if you know the velocity either at oil locations or seismic data, you can transfer it into effective stress. Having these three parameters, BS, A, and B for particular and specific area. And once you get the effective stress using these Tarjaki equations, you can get pore pressures. Okay, so Eton equations and Bauer's equations are used to compute the pore pressure at the oil location. Here you can see the left side, we have applied these equations and we got more or less same pore pressure, and pore pressure has been validated by the RFT data at selected depth interval. You can see star mark is there. So we believe that this pore pressure model is quite satisfactory, and also this pore pressure have been validated by the mud weight. You can see, and this pore pressure is also signifies there's a presence of high pressure zone in Kupili formations that is obtained from the log signature from porosity and sonic travel time. Okay, and to estimate this coefficient BS, A, and B, we have to plot this plot, that is velocity and normal effective stress, and then you will get the value of BS, A, and B. So in this way, we can compute pore pressure at any oil locations. In next slide, I'll discuss that, as I already told you, in Bauer's equations, once we get the velocity, we can transfer into the effective stress. The same thing in seismic data. In seismic data, we get the velocity during the processing. And if you don't have any velocity and having only post-stat data, then you can transfer this post-stat data into impedance data using some inversions. There are a lot kind of inversions techniques are there, but in that case, I have used model-based seismic inversions to get impedance and then velocity. And we have gone through each and every steps of model-based inversion technique. We have created low frequency model. We have created, these horizons, barrel horizons, Kopili, Silhouette, basement for this 3D seismic data. And we have used this wavelet to transfer the reflectivity series into the impedance. Okay. And here in this left-hand side plot, you can see after getting the impedance, applied the inversion technique, we have convert that impedance into velocity by using Lindsay equations. And here you can see the seismic predicted velocity at the oil locations are more or less matching with each other. So that's mean whatever we are getting the velocity from this impedance data quite satisfactory. And this is the, you see, can we change the slide? Yes, again, come to the previous slide. Yes, so this is nothing but a velocity cube. So this velocity cube of 3D seismic data we are obtaining from the model-based inversions followed by the impedance, and impedance has been transferred into the velocity model using Lindsay equations. Okay, so once we get this velocity data, we can easily convert into effective stress by the Bauer's equations. Obviously, we have applied these Bauer's equations and we got the effective stress. Although I'm not showing here, but I have done. And we got effective stress from seismic data. We can also transfer this velocity and impedance, density data into vertical stress. So once we get the vertical stress and effective stress, we can have pore pressure using Tarjai equations, which I shown in my previous slide. So kindly change the slide, change it. So this is nothing but a 3D pore pressure modeling. You can see pore pressure is increasing with depth, but in Kopili formations, if you look closely, you are seeing the kind of higher value of pore pressures, and that is indicated by the almost blue color. So the Kopili formations in 3D seismic data is also showing presence of high pressure. That is also correlating with the oil log predicted pore pressures. As we have 3D seismic data, also, kindly change the slide, please. So we can display our pore pressure for 2D horizon for different formations. I have shown here, this is the 2D horizon of pore pressures, special distributions for barrel formations. Here you can see at the well locations, you are not getting any high pressure, that is normal pressure, but away from these well locations, you are getting some spaces is high pressure zone. So if you want to drill in this high pressure zone, you have to change the mud weight which you have modeled at the oil locations. But overall, in barrel formations, the formation is in under normal pressure, not significantly high pressure is found out. Can you change the slide? This is the special distribution pore pressure for Kopili formations. Already I told you in Kopili formation from oil log data we got the high pressure zone. And the special distribution of the pore pressure for Kopili formation you can see in this direction, that is southeast direction, there is more high pressure than the oil locations. So whatever you are modeling or you are optimizing of oil during the drilling at this oil location, and you are fixing the mud weight. And if same amount of the mud weight, if you carry for this higher OPZ, the problem will be created. There may be some serious problem, maybe some blowout. So it doesn't mean that each and every formation have same amount of the high pressure. This high pressure change from special to special depending on the geology, depending on the deposition of the sediment or thickness of the sediment or any kind of tectonic activity or any secondary causes. So you can see it is clearly picturized or understood from this special distribution of pore pressure for Kopili formation. The pressure is not actually uniform. It is being changed and become higher toward the southeast directions. Next. Yes, in the Silhouette formations, pressure is not although so much high, becoming high, normal pressure, but toward the northeast directions, we are getting slightly high pressure region So here, obviously, when you want to drill, you have to change your mud weight. Then these locations oil KM and oil KE. So this is my short presentation that how we identify or compute pore pressure from using oil log data and seismic data. And pore pressure is very fundamental parameter for designing a well. And in Northeast, KG basins all are affected by the severe problem, high pore pressure. So, and there is a obviously blowout of oil, and there is a tremendous loss amount of money, and in terms of casualty also occurred, and a lot of officer also has been died. So this is very much important parameter, that is pore pressure. So what is my result and conclusions of my presentations? That we have got pore pressure gradient varies from 4.2 to 15.50 MPa per kilometer. Top of the pore pressure varies from 1225 to 2182, and the pressure that is becomes high pressure is due to the disequilibrium compactions in nature in our study area. And you can see 8 to 10 MPa changes pore pressure is happening toward the eastern side. So that means you have to change mud weight from 4 to 8 MPa for this study area. So this is my all presentations, and next slide. And thank you all. So thank you all for listening my presentation within these 5 minutes.
Okay, thank you very much, Dr. Deep. Any questions from participant?
The questions we can have together towards the end. That may be better.
Okay, okay, thank you. So I think there will be a time limit for 5 minutes only. I could see from the list. Okay, okay, I'm going to say is Vivek Singh is there? Second presentation.
So thank you, sir. I'm leaving.
Yeah, sure. Vivek Singh is there? Second presentation, it seems not there. Third presentation.
Chinmay Sethi is the presenter.
Yes, sir.
Vivek Singh with the second paper.
No, sir. Vivek Singh is the author, but Chinmay Sethi is the presenter.
Okay, whoever be the presenter. So the second paper is being presented now?
Yes, sir.
Yes.
Okay, so the second paper is impact of temperature on the strength of sandstone, a case study from coal bearing sequence on Earth by Vivek Singh et al. So please present.
Good afternoon, everyone. My name is Chinmay Sethi, and I'm an ACSI research scholar from Rock Mechanics Laboratory of CSI at Simfer. So I am presenting today a topic which is about impact of temperature on strength of sandstone, which is a case study from coal bearing sequence of Sonat Coalfield, India. So to understand the influence of temperature on the strength properties of sandstone is essential, because in projects like underground coal gasification, so in such projects what happens is we try to convert coal into gases. So during the process, the surrounding temperature might hit the melting point of the rock which is surrounding that particular portion, as we can see from the figure. That is the first figure from anti-clockwise, in clockwise direction. The first figure is about the sandstone location from which we have taken the sample. So it is a borehole rock. And in the second figure, we can see is the instrument which we have used to analyze the physical mechanical properties of the sandstone. So our objective is about analyzing the variations in physico-mechanical properties along with the mineralogical and microstructural changes in the sandstone due to temperature effect. So we have heated those samples at different temperature intervals, which is 250, 450, 600, 750 degrees Celsius at a rate of 5 degrees Celsius per minute, and we kept it inside the electric furnace for 6 hours. We have uniaxially loaded the samples at a rate of 250 Newton per second until failure. So please move on to the next slide. Yes. So what we have analyzed is UCS, Young's modulus, axial stress and strain plots, and Poisson's ratio, as well as the physical properties. So we found that the UCS of sandstone had two-stage behavior. So at first, from 25 to 250 degrees Celsius, the strength of the sandstone has increased slightly. And in the second stage, there was an overall decrease in the strength. And the major observation that we found that is the ductileness of the sample is increasing from 450 to 750 degrees Celsius, as opposed to the brittleness. From the figure of axial strain and axial stress and axial strain, we observed that that from 25 to 250 degrees Celsius, the nature of the sample is brittle, but from 450 to 750 degrees Celsius, it is increasingly ductile. And similarly for Young's modulus, with increasing temperature, it is showing an overall decrease. But in case of Poisson's ratio, what is happening that it is an inconsistency from 25 to 600 degrees Celsius. So there is no major impact of temperature on the Poisson's ratio. But at the highest test temperature, that is 750 degrees Celsius, it is showing a drastic increase. And in case of physical properties, there is gradual decrease in density, PV velocity, and SV velocity. So in the next slide, we will try to understand the corresponding effect of mineralogical and microstructural changes with the physico-mechanical properties of the sandstone. So please let's move on to the next slide. Yes. So in the figure 1, it is the petrographic analysis of the sandstone, and in figure 2, it is the FESM analysis. So from our petrographic studies, we found that the major minerals, framework minerals, were feldspar and followed by quartz. So the sandstone was arcosic in nature, and we observed that in 25 and 250 degrees Celsius, in 250 degrees Celsius, there was no major changes in the mineral grains. Only the feldspar, some of the feldspar grains has cracks in it. But from 450 to 750 degrees Celsius, the feldspar started to decompose into clay matrix. So, and it is forming a pseudo matrix kind of material, as we can observe from the thin sections of petrographic analysis. That is C, D, and E. The C is representing 450 degrees Celsius, and D is 600, and C is 750 degrees Celsius. So the feldspar grains are increasingly decomposing with increasing temperature. And from 600 degrees Celsius onwards, we saw that quartz grains also showed some cracks in it. So there is an overall weakening of the framework structure of the rock. And similarly, from FESM analysis, we observed that from 450 to 750 degrees Celsius, there is increase in cracks, micro cracks. So in individual grains, there were intragranular crack, and in between grain boundaries also there were cracks. So the interconnectivity of these cracks has weakened the framework structure. This is why in previous slide, we saw that all the major changes are happening in the stage 2, that is from 450 to 750 degrees Celsius. So let's move on to the next slide. So our major observations were that the uses of this particular sandstone, which is arcosic in nature, had two-stage behavior in the changes of strength, of only the strength properties. But it has also shown us that from 25 to 250 degrees Celsius, the sample was behaving in a brittle manner. But from 450 to 750 degrees Celsius, it has become increasingly ductile. The framework mineral grains, that is quartz and feldspars, has developed some, the feldspar in particular has decomposed to pseudomatrix, and quartz had started developing fractures from 600 to 750 degrees Celsius, because we know that quartz changes its phase from 570 degrees Celsius. So that's why the major changes was observed from 600 degrees Celsius. And there were development of intergranular and intragranular cracks from 450 to 750 degrees Celsius. So overall, we observed that both the mineralogical and microstructural changes due to the heat impact had significant effect on the strength properties of the sandstone. Thank you.
Okay, thank you very much, Chinmayji. Now we are moving to next presentation. Is Sheikh Naseem Ahmed there? Next presentation.
No, sir. Next will be.
Okay. So we are going to next one. Manoj Kumar Bharti is here.
Yes, sir.
Okay, so please present your talk.
Can you please put my presentation?
Yeah, so improvement in structural imaging in fold belt area in such line seismic data. Please, Manoj Kumar Bharti.
Good afternoon, sir. Good afternoon to all of you. My topic is improvement of structural imaging in Tripura fold belt area by swath line seismic data. Next slide, please. As we all know that there are many challenges in fold belt area, like highly undulated topography, which lead difficult logistic for planning seismic survey, hard formation exposure, which lead to difficulty in drilling the short hole, poor receiver coupling, more skips, irregular fold distribution, poor subsurface sampling, near surface velocity varies very rapid and random, poor energy penetration, scattering, lot of coherent noise, and guided wave, which lead poor seismic data quality and very low seismic to signal to noise ratio. This area is structurally very complex and out of plane reflection are very common. In spite of advancement in seismic data acquisition and processing, imaging in a structurally complex area such as Tripura fold belt has improved marginally. In such geologically complex area, conventional approach to imaging did not yield a satisfactory result. Though in such area, 3D survey is more preferable, but due to several constraints like rough topography, difficult accessibility, etc., 3D seismic data acquisition is very expensive and sometimes it's impossible to carry out 3D survey. Next slide, please. Conventional 2D land seismic data has its own limitation. It cannot record out of plane waves. So as an alternative to the conventional 2D seismic in such area is a swath line recording geometry. The swath line recording geometry consists of 3 parallel receiver line, in this case 40 meter separation, and a single short line along central receiver line. So a short record, we can clearly see the 3 short record coming from 3 receiver lines. This is just 2 additional receiver line in conventional 2D seismic. Next slide, please. And processing of this swath line geometry is taking extra care because there is no established workflow for this swath line geometry. This is neither 2D and nor complete 3D. So special care is taken during the seismic data processing. And there are most of the places we follow treat this data as a 3D with the special care of 2-3 steps like statics. In this area, elevation variation is much. In this case, we can see elevation is vary from 32 meter to 116 meter. So conventional field statics is not valid. It is based on near surface model estimated using sparse uphole survey. So in this case, we have applied a reflection statistics derived from data itself by first back breaking. Solution is based on nonlinear tomography. First arrival times are interactively picked on all the shots and near surface velocity model is generated. And next one is velocity picking. In general, signal to noise ratio is very poor in this case in fold belt area. Reflection hyperbola is hardly seen. So as no consistent hyperbola available in the data, velocity analysis based on flattening of hyperbola is not valid in this case. And the semblance based approach is also not valid because semblance is very poor in this case. So I have followed a constant velocity stack approach to pick the initial velocity model. Next slide, please. And for the comparison, I have processed the same data in 2 fashion. The right hand side is the swath line geometry. We have taken all the 3 receiver line till PSTM, and the left hand side I have taken only 1 receiver line along the short one, just like conventional 2D. And I compared the result. I have processed total 8 lines 3 in deep direction, sorry, 5 in deep direction and 3 in strike direction. And image quality significantly improve in deep direction lines, because anticline portion is very clearly, we can see in the right hand side, we clearly the visual, and fault demarcation is also very good in swath line geometry. So next slide, please. So to the conclusion, in the current study, it is shown that the fold belt area having severe topography and difficult accessibility, conventional 2D seismic data acquisition failed to provide adequate image, and the 3D acquisition is too expensive and logistically very onerous. So high fold swath line data acquisition is better option in that case. Swath line recording and processing provide much higher foldage along with significant improvement in signal to noise ratio, and thus provide a superior subsurface image quality in this area. With this, I am thankful to IGU for giving me the opportunity to present my work, and thankful to Professor Uma Shankar to encourage me to carry out this work. And I am grateful to ONGC for providing the necessary facility to carry out this work. Thank you. Thank you.
Thank you very much, Manojji. Now we are moving to next presentation. This is by Anjali Dikshit, Nimesh Mandal, and SS Ganguly. Is the author here?
Yes, sir, I'm here. Sir, I'm
Okay,
the presenting
so
author, Anjali. Yeah.
Okay, so Anjali is presenting application and uncertainty analysis of GADAM optimizer in semi-supervised sequential convolution network for seismic impedance inversion. So Anjali, please present.
Yep, thank you, sir. So good afternoon to all of you. Myself, Anjali. I'm a second year PhD student in Department of Earth Sciences, IIT Kanpur. So today I'll be talk about the application and uncertainty analysis of GADAM optimizer, which is a hybrid optimizer, and that we applied in a deep sequential convolution framework using semi-supervised learning for acoustic impedance inversion. So moving to the next slide. So as we all know that acoustic impedance is a very important parameter for evaluating the petrophysical properties and characterizing the reservoir. However, due to the non-linear relationship between the seismic data and the impedance, which is due to the present noise and unknown nature of the wavelet, or due to the measurement error, we got the non-linear relation, and which lead to the non-convex objective function between both these attribute and or multimodal objective function we got. So to calculate the impedance inversion, there are two type of approaches. First is the local optimization scheme. So in that we need first an initial model that we run and got the minimized objective function. However, the scheme is very fast, but it prone to converge to the nearest minima point due to selecting an starting initial model. So to anticipate this challenge, there is another optimization scheme, which we called a global optimization scheme. Unlike local optimization scheme, global optimization schemes work with multiple models. So they ensure that conversion is happening at the global minima point. However, due to the multiple initial model, it requires a large search space, which makes this technique computationally extensive. So recently, a researcher has come up with another approach, which we called as a hybrid global optimizer, and which is a GADAM. So GADAM, it is a combination of genetic algorithm and ADAM optimizer. So here in this study, we tested the application of GADAM in the seismic impedance inversion. So to just brief about the GADAM, here you can see in this figure that first we create a pool of models, then we apply the ADAM optimizer, and again with the genetic operator like crossover and mutation. Okay. So again with the genetic operator like crossover and mutation, we get another set of models, and then out of these two set of models, we select the best models which is having the less loss value. So in that way, we get the most optimal generation, and this generation can be like terminate when the stopping criteria has been met. So in a summarized manner, here you can see the first figure where the green dot is representing the global minima. So in case of ADAM, due to the single initial model, it is converging at the minima, but this minima is not a global minima. But in case of GADAM, since we are working with multiple models which are highlighting with the black dots, so with that we were able to achieve the global minima. So moving to the next slide. So this is the framework. Please move to the next slide. So yeah, this is the framework that we have designed to apply the GADAM in the impedance inversion. So first we fed the available seismic data and the well log data in the trace form, and then using the inverse model, we got the predicted impedance. But as we all are aware that these deep learning models require a huge amount of learning data to train themselves. So to circumvent this problem, we also applied a forward model, and that's why we are calling this technique as a semi-supervised learning scheme. So with the forward model, we are generating the synthetic data as well at the same time for those traces for which we don't have the well log data. And then we combining the total loss, which you can see in this equation. So we are combining the inverse model loss, which is giving us the impedance misfit log, and with the help of the forward model, we are getting the synthetic seismic data loss. And then with the help of GADAM, which is a hybrid optimizer, it tries to optimize this loss value. And after getting the minimal loss value, we stop the training and we get the optimal impedance. So to check this efficacy on the synthetic and real seismic data, we, can you move to the next slide? We applied into the, this is the section for the Mermauzi 2 synthetic data, where the A image is representing the true impedance, and this red circle is highlighting the guess charge zone, and B is the inversion that we got after applying the GADAM optimizer, and the C is we got after applying the ADAM optimizer. And now you all must be thinking that why we are applied the ADAM optimizer, because ADAM is the most widely used optimizer in this deep learning framework till now. So now if we compare both the results, we can see that the guess charge zone is more effectively characterized by the GADAM optimizer, because here the white lines, though here also we can see the white lines, but for the case of ADAM, they are widely spread over the zone, but here for GADAM, it is confining to just around this black area. And if we talk about the in terms of reflectors, so here also we can see that the red area for the ADAM, I hope you can see my marker, is it? So here you can see that there is a lots of discontinuity around 2500 cross line, and the time range around 1500 milliseconds. But for case of GADAM, we are getting the continuous reflector, which is similar as the true impedance model. And moving to the next section, which is the we applied it on the real data as well, and for that we use the F3 well data that we haven't used for the training. So here you can see that the correlation coefficient for the GADAM is higher as compared to the ADAM optimizer, and also we are able to see the significant deviation between these two optimizers as compared with the true impedance trace. And again, and after that, we compared the accuracy of both the optimizer. For the first one figure is for the synthetic Mermauzi 2 model data, and the second figure, the below one graph, is for the F3 data. And here also you can see that like for the Mermauzi model case, like around 300 epoch, the accuracy of GADAM is highly increasing. And this is because for the training of the M2, like Mauzi-2 model data, we have the sufficient training data. So that's why the GADM was able to train itself quite good and surpass the accuracy of ADAM optimizer. But here for F3 data, as we gave only 3 well data for the training, so that's why it took some time to surpass the accuracy of ADAM, but around 800 epoch, the accuracy was improved significantly.
Anjali, you have taken 5 minutes. Try to wind up quickly.
Yeah, so only last slide is left. So moving to the next slide. So as we know that the deep learning prediction are deterministic, so it is very important to calculate the predictive uncertainty as well. So we also did the predictive uncertainty for GADM and ADAM optimizer. And here you can see that for the GADM optimizer, the first figure, which is the confidence band, which is plotted between the predicted mean impedance and the observed impedance, the same well that we used as a blind well for F3 data. So here, if we compare for the GADM or ADAM confidence band, so the ADAM confidence band is quite dispersed. It's not the confined. So it shows that there is a deviation between the true and the predicted value. Similarly, for the case of miscalibrated area, so where the diagonal line is the absolute prediction, and if there is a deviation, then it is showing that your value is deviating from the true value. So here the miscalibration area is 0.09 in case of GADM, and for the case of ADAM, it is 0.13. Also, moving to the next, we use some scalar evaluation criteria. So here are the values that you can see that that are indicating that the uncertainty for case of GADM is less as compared to the ADAM. So these are the conclusions that we can apply this hybrid optimizer in seismic impedance inversion, and the results are quite satisfactory. Also, they are leading with a less uncertainty. So yeah, it's a good option for applying it for acoustic impedance inversion. Thank you all for listening.
Okay, thank you very much, Anjali. We are running out of time.
Yeah,
so
sorry, sir, for the.
Moving to the next is P. Akhil is there, Amal Roy and Subhash Chandra.
No, sir. No, sir. Who on the next?
Okay, so moving to the next, PD Raju is there, Saurabh Datta.
Yes, sir. I'm audible.
Yes. Can your name, good name, please?
PD Raju Yalamanchi.
Okay, so next presentation with this Yalamachi.
Yes,
about the pore structure analysis and permeability prediction by using fractal theory based on SEM image and carbonate samples. So, Yamanathi, please present.
Yeah, very good afternoon to all. Myself is Pedro Almanchi. I am the research fellow from the Department of Applied Geophysics, IIT ISM Dhanbad. Today I am going to discuss about the pore structure analysis and permeability prediction by using the fractal theory based on SEM images of the carbonate samples. Please move on next slide. Yeah, why the pore structure characterization important? Because the pore structure is mostly complex nature. The pore structure parameters are controlling the fluid flow and also it affecting the reservoir quality, like pore size distribution and throat size distribution and pore connectivity between the two pores, and also grain size distribution and porosity. And you all know the permeability is the main crucial parameter to understand the fluid flow in any porous medium. In this study, mostly we are focusing on the permeability prediction by using the fractal theory by the fractal characteristic parameters like fractal dimension and also pore structure parameters is the maximum pore diameter. But several existing permeability calculation models also is there with some empirical parameters and some unclear physical meaning. But compared to that models, the fractal prediction is a more accurate and reliable permeability prediction model. A main object of this study is the pore structure characterization is quantitatively analyzed by using the 2D SM images. Means we are calculating some porosity values and pore size distribution and the grain size distribution, and also we are presenting some effective, efficient method to estimate the microscopic permeability of the carbonate samples at two different magnifications. In this study, we are using the two different magnification. One is the 1500 magnifying scale, and second one is the 2000 magnifying scale with the help of the Koenig-Kärman equation. And also we are evaluating the logarithmic relationship of the geometrical parameters of the pores like pore area and pore perimeter by using the green and Euler distance method. Please move on next. The methodology. In this study, we are taking the 2D SEM images as an input, and then we are applying the different segmentation algorithms to binarize the image. But the binarization is the imaging process. It's in that process we are choosing one threshold value, and the pixel values which are above this threshold value are representing the white, and the other pixels are representing the black spaces. The segmentation means the segmentation gives an image is a clear, visible, and also it makes it easier to analyze the image. In this study, we are using the three different threshold algorithms. One is the Hang algorithm, the second Otto's algorithm, the third one is the max entropy algorithm. After converting the binary images, we are calculating the porosity. The porosity is calculated by the number of pores of the represents the pixel values of the pores, and it is divided by the total number of the pixels. By using some MATLAB coding, we are determining the porosity values. From these porosity values, we are compared with our measured porosity values. Then we are finalized the max entropy threshold algorithm is the best threshold algorithm. It gives the accurate porosity values is similar to our measured values. Then after completing the porosity values, these max entropy segmentation binary images are used for the further studies like pore structure parameter calculation, grain size and pore size, and also fractal dimension calculation and the geometrical parameter calculation. Finally, we are using the pore size distribution and the fractal dimension with calculating the permeability. These permeability values we are compared with our measured permeability values to know how the fractal dimension is accurate and reliable. Please move on next. The result and discussion. In this study, we are using the total 4 carbonate samples named as S1 to S4, but for clear convenience, I am showing here only one sample, S3 sample, at 2 different magnification. One is the 1500 magnification scale, and second one is the 2000 magnification scale. The AB are the original images, and the image figure C to E shows the S3 image at 1500 magnification scale at 3 different segmentation algorithms. Algorithm, max entropy, and Otto's algorithm. Same like F2H, also different in S3 sample S3 at 2000 magnification at the 3 algorithms. In these binary images, from these binary images, we are observed to the 2 different spaces. One is the black and second one is the white. In the black parts are representing the pore spaces, and the white parts are representing the matrix of the samples. Please move on next slide. Here I'm going to presenting the porosity histograms of the 3 different algorithms, Hung and max entropy and Otto's algorithm of the 4 different carbonate samples, S1 to S4, and the figure A shows the samples at 1500 magnification, and figure B shows the sample at 2000 magnification. And these porosity values we are compared with our previous studies petrography analysis. In this comparison, we are finalized the max entropy algorithm is given us similar closer values to the measured values of the petrography analysis. Then we are using the max entropy segmentation algorithm for the further studies. And figure C and D here, the geometrical relationship of logarithmic relationship of the geometrical parameters, pore area and pore parameter. We are doing up the sample S3 at 1500 and 2000 magnification. Here you're getting the best fit lines, and R square also you're getting the more than 0.98 values. Please move on the next slide. Yeah, in this figure, we are showing the pore structure parameters like pore size and the grain size distribution variation with relative frequency, and how these parameters are varying the different magnification. In the figure 3A, it's a pore size variation. It's a two different magnification of the sample S3, and figure B is showing the grain size distribution. We are observed here the.
Raju, can you mute your conclusion?
Yes, sir. It's in 1 minute. 1 minute I will complete. It's in 1 minute. Here observed here at the magnification is increasing, the parameters of pore size and grain size are gradually decreasing. In the figure A and 4A and 4B is the fractal dimension calculation. By using the box counting method, we are calculating the fractal dimension by draw the logarithmic relation the box size and the count of log of the count. Next slide, please move on. Yeah, by the help of all these parameters, we calculated the permeability with the help of the fractal dimension and also area and maximum force distribution with using the Courgeney and Carmen equation. The G is the geometric parameter constant. In this, we are getting the permeability values in the range of 0.00442. The maximum value is equal to 0.1899 C. In these values, we are compared with our measured values, which is measured from the LBM permeability, lattice Boltzmann method. In these values, we are getting 0.0016 to 0.0029.
Please, conclusion, you have gone to 10 minutes instead of 5. You should have come prepared with...
My conclusion, sir. Please move on next slide. Yeah, we are coming with some conclusions. In this, we are coming the porosity based on the SI images of different segmentation algorithm. We are calculated. We are concluded the max entropy algorithm is closer to our measured results. Then second is the porosity, pore structure parameters with magnification. With increasing the magnification, the pore structure parameters are decreases. And the third one is the binarization process of the binarization process. Geometrical parameters and fractal fitting parameters of the rock sample are calculated or analyzed, and finally we found the fractal theory is reliable to estimate the permeability of the carbonate samples with its parameters and from the microscopic images. Thank you. I would like to thank you, Professor A.S. Maurya.
Okay, we have read your acknowledgement. Thank you very much.
Thank you for giving extra time.
Next presentation. Next presentation by P. Shivshankar. Is there?
Yes, sir. Yes, sir.
Okay, so next presentation is by P. Shivshankar et al. The site characterization study of Suri Kalwa Mani fault, Eastern Dharwad. So please present P. Shivshankar.
Okay, sir. Good afternoon, one and all. I P. Shivshankar, Research Scholar, CSR NGRI, Hyderabad. Now I am presenting site characterization studies at VKZ fault, Eastern Dharwad Craton, multi-channel analysis of surface waves. The figure one shows that my study area is a crescent-shaped. Crescent-shaped Kadapa Basin is located in Eastern Dharwad Craton, extended from north-south direction 450 kilometers, and its center 145 kilometers width. The concave-shaped eastern margin is tectonically activated and highly deformed, folded and faulted nature compared to the western margin of this Kadapa Basin. And figure number 2 shows that the 60 kilometers VKZ fault oriented north-northeast direction to west-southwest direction extended from Eastern Dharwad Craton to Kadapa Basin. It is known to be a strike slip character. So previous studies of this VKZ fault reflected that the repeated movements which are associated with down dip and up dip movements, and due to this strike slip movement of this different region along this VKZ fault represents it a steep monocline structure. That means it's gently dipping sequences observed. And Chetty and Nagaraja sir reinterpreted this fault is not a simply strike slip fault, it is a transform fault. So in this scenario, we observed that historically no major earthquakes are recorded except 1843 Ballari earthquakes at 5.6 magnitude earthquakes is recorded. It is 80 kilometers far from our VKZ fault area. So this table we shows that recently during 2012 to 2016, 3 microseismic events recorded in CSIR NGRA observatory in the vicinity of this VKZ fault at the average depth of 13 kilometers. So in this idea, we need to understand the site characterization studies near to the Kalwa region. So move on to next slide, please. So the site character studies, one of the best technique is multi-channel analysis of surface waves. This surface wave seismic multi-channel analysis of surface waves is a seismic exploration technique to evaluate the ground stiffness by estimating the shear wave velocity of subsurface in 1D, 2D versus depth up to 30 meters with high resolution maps. So this figure shows that MASPA field setup with 49 shots. So this MASPA survey is carried out to 3 locations using 24 channel seismograph with considerable source and offset configurations. The subsurface alleyways we obtained from spike coupled low frequency multi-channel seismic records. And the dispersion curves are constructed. Here we have showing the dispersion curve, right side. Dispersion curves are constructed from the field transfer method. In this terms, it is phase velocity with respect to the frequency. After this experiment, finally we got the shear wave velocity model obtained from the experimental dispersion curves from this inverted dispersion curves by using the Monte Carlo inversion technique. Can we move another slide, please? So it is observed that we have got three seismic three observed from the 3 shear wave velocity images with velocity by using the velocity model VS30 estimated from 100 meter per second to 1500 meter per second. On an average, it is 850 meter per second. Now the velocity, now according to National Earthquake Hazard Reduction Program, sites are classified to A to B, which the velocity is 1500 meters. It is the hard rock we have shown in this table, and it's 850 meters. It is the rock. So finally, we have seen in profile 1, we have 0 to 10 meters. We have the soil low velocity, alluvium, and 10 to 25 meters. We have the hard rock. And finally, with profile number 3, we have seen completely a hard rock. And then it is the completely hard rock. So the recent earthquakes activity near to the fault may suspect the great potential of earthquakes in the future. That's why we compare to our MASPA results, early detection of this fault characteristics with respect to the recent earthquakes activity is useful to reduce the damage for nearby areas. So my study with this my study with these results, we need to avoid the reduce the damage of the nearby areas of Kalwa region. Thank you, sir.
Okay, thank you very much, Shiv Shankar.
Thank you, sir.
We are moving to the next presentation. Vasu Deshmukh is there? Vasu Deshmukh, P. Vijay Kumar, P.
No, sir. No, sir.
No,
No, sir.
okay. So next presentation is Vishnukant Verma and Anand Singh. Is Vishnukant Verma there? No.
He should be there, sir. I saw his name.
Okay. Vishnukant Verma.
Good day, sir. Am I audible?
Yes, sir. You are. Please continue.
Okay. A very good day to all of you. I am Vishnukant Verma, a PhD research scholar at Department of Earth Sciences, IIT Bombay. In this presentation, I am presenting on unstructured grid-based forward and inverse modeling using magnetic method to improve the subsurface imaging of the Darwara region in Madhya Pradesh. Next slide, please. Yeah. We know that recovering the true physical property distribution is not possible in most of the cases. For example, in my first figure, there is a plot of 2 models. The first one is the synthetic model and the second one is the inverted model. Although both the model are able to fit the data exactly, but they are quite different nature. The layer boundary is not sharply defined. Also, the physical property variation is huge there. In my second figure, I have 2 rectangular blocks, and I have performed the inversion using different inversion methodology. For example, L1 inversion, L2 inversion, and we can see that different inversion algorithms are able to produce the different subsurface model. So there is a ill-posedness in the geophysical inverse problem. In my third figure, in my below figure 3rd and 4th, I have tried to discretize a subsurface using rectangular grid and triangular grids. Here I am trying to demonstrate the benefit of triangular or irregular grid. For example, when I am trying to fit the irregular topography using rectangular grid, it is not able to fit it properly. There are some gaps. But when I do the same using the triangular grids, the triangle side become the topography edge. So it is able to fit the body correctly. Also, if there is some complex subsurface body, that can also be not properly modeled using the rectangular grid, but the same will be more properly fitted by the triangular grids. Also, the number of model parameter when I choose the regular grid geometry is 408, for example, in this figure. When I discretize the same surface using the triangular grid, there is 301 number of model parameters only. So with the decrease in model parameters, my computational efficiency will increase. It is happening because my triangular grids can be made finer where there is any sharp boundary, and it can be made as large as required in the homogeneous area. So it was the motivation introduction for the present research. Next slide, please. So for forward modeling, I have done the methodology like this. I discretize the subsurface using triangular grading. The benefit was that it was able to produce the irregular topography. It was able to model any complex subsurface body, and at the same time, it also reduces the number of model parameters. For forward formulation, I can calculate the gravity anomaly or magnetic anomaly due to a triangular cell. So gravity or magnetic method are potential field methods. So if I'm able to produce the anomaly due to a triangle cell, I can sum up the anomaly due to all the triangle cells because they are potential field methods, so follows the principle of superposition. Also, the forward formulation for magnetic method comes in the form d equal to gm. So it helps in solving the linear inverse problem. For inversion framework, I am currently using the preconditioned conjugate gradient method. Preconditioning here is compensating for decrease in response of the potential field with increasing source depth, and the conjugate gradient method is finding the search direction in step size. Here I have demonstrated a simple flowchart of the same. Next slide, please. Here I have performed or analyzed my methodology over the synthetic and a real field data set. So for a synthetic model, I have taken two rectangular body in the subsurface of having the susceptibility as shown, and the same set of forward formulation was also done by the Geophysical et al. 2014. So I was matching my result with them. So for forward modeling case, it is matching the data as expected. Now for the real field data set, I have the magnetic data of the Gurdwara region in Madhya Pradesh. So this was the data in black color. I have taken this from the paper by Raju et al. So they produces the inverted structure like this shown in the below figure, and my structure is matching up to some extent, although it is some preliminary result and we are still working on it. It is able to demarcate the body approximately, and we are currently working it to improve it as well. Next slide, please. So it was the content of my presentation. Thank you for your kind attention. If you have any query or suggestion, feel free to write to me at
Yeah, we'll come to that, Vishnu. Thank you, Vishnu.
Okay.
Thank you, sir. To our next presentation is B. Lakshman there. B. Lakshman, K. Satish Kumar.
Yes, sir. Satish is there, sir.
Okay, so next presentation is a response of chromite in laterite environment, theoretical gravity approach. So please present B. Lakshman.
Yes, sir. Good afternoon to everyone. First, I would like to thank to organizing for IGO and chairperson. So my topic is chromite signatures in laterite environment and a theoretical gravity approach, sir. Actually, chromate exploration, the gravity method is a basic method to use the dissipate the chromite because it is a very high density, denser body. Further to we have did some theoretical approach for the lateral environment. As everybody knows, the Sukunda is one of the repository of the chromite deposits in the in India. Most of the chromite deposits were contributed by Sukunda Valley. So in near every area, one Katpal is also there with the extension of the Sukunda area. We have recently done some gravity matter experimental studies we have done. So we have faced some of the problems to identify some of the chromite mineral. For that, we have done some synthetic models how to get into out of the laterite problem. So what we are showing here is some of the samples what photographs near in the Katpal area. The basic idea what we have drawn here, actually we have analyzed the nearly 5 to 6 borehole data. From the 5 to 6 known borehole data, we have generated one representative borehole. What we are showing in the figure, it is a laterite cap and limonite cap, and what are the chromite bands what you observed within the serpentinite. The thickness of the chromite what we observed is hard lumpy component nearly 15 to 16 meters. Next slide, please. So the experiment is how we have approached the experiment is first we have gone for the ideal cases. First we have seen the how laterite will respond to the gravity. First in the first model 1, we have taken the thickness of the laterite is 5 meters. Afterward it is increasing 11 meters and 23 meters based on the what is the representative borehole it is showing. Like that we have seen the response of the gravity. The gravity, what we have seen, the response gravity is very low over the lateritic body. And then right side corner, what we're showing is the response of chromite. In the same way, we have seen the chromite also in the different thicknesses we have observed in the chromite layers also. In the chromite, what we have observed is the high gravity anomaly. It is a well-known thing. Chromite is a high density body, will get the high density, high gravity anomaly. For the laterite, we seen the low gravity anomaly. Next slide, please. Next. Okay. So now we coming to the actual problem. What will happen if laterite is capped by chromite? Chromite is capped by laterite. So here, the table at left hand side, what is showing is we have did the 64 synthetic models we have carried out. The horizontal side, what is 5, 11, 20 is 20 meters of the chromite thickness, and left side lateral weight, what is 5, 11 is also a thickness of the laterite. So for suppose 5 meter thickness laterite, so the chromite persistence of 5 meters, 11 meter, 20 meter, 23 meter, what will happen? So for that we have seen first in the first left hand side first figure you can see at 5 meter laterite thickness. If it is concealed by any chromite, 5 meters, 11 meter, 20 meters, what is the response? The response is highly, it is a positive. Why? Because it is a thickness, thin laterite is covered by a chromite. In the second figure, what will happen? The thickness of the laterite is increased. It is 11 meters. Now you can see the response of the chromite also high, but wherever the response, the black color and blue color, the response of the chromite is laterite is increased, we could not see the response of the chromite. Next slide, please. So now you can see that if we increase the thickness of the laterite, here 20 meter lateral thickness will be increased. So we can see even chromite is a higher density body also. We could not see the high gravity anomaly here. Only feeble anomaly gravity high and only were observed over the chromite body, which is capped by a 20 meter thick laterite. And then really in the Sukunda region, we generally we got thickness of the laterite is 20 to 50 meters. The previous studies also we are reflecting. So if the thickness of laterite is increased more, you can see in the left side, right hand side figure, it is 49 meters. So we could not able to identify the response of the chromite. If either it is ore body is existing also, if it is laterite cover in the gravity, we could miss the signature of the laterite. Next. So what we come to the conclusion from this our synthetic study, what we respond is, if it is alone, an ideal case is if laterite alone is present, the negative gravity anomaly we can observe. If it is in only chromite alone, ideal cases, we can observe the positive gravity anomaly. Suppose if it is combination of chromite and laterite, if thickness of the laterite increases, we can see the only negative gravity anomaly. If the thickness of laterite is minimized, you can see the response of the chromite. Actually, what will happen, the laterite cap in gravity survey, what we are in the general procedure, what we did is, we can identify where are the high gravity anomalies we picked, because chromite, because the high density, it is by proportionally we can pick. But in the laterite environment, it could not. You can also concentrate on where are the gravity lows also we should concentrate. Hence, it is a advice to the gravity survey. We have to filter the laterite response from the gravity anomaly. Then only we can get the ore body. Whereas if it chromite also existing also, we could miss. And another case is, if you target the laterite, we can identify another mineral also, nickel also. We can identify. Thank you, sir.
Okay, thank you very much, Satish. Now we are coming to our last presentation by Arvind Kumar and Shalivahan and Akash Chandra. Are you there, Arvind Yadav?
Yes, sir. Yes, sir.
Okay, so his presentation is interpretation of EM data using the concept of analytical signal. So please present, Arvind.
Okay. Good afternoon, everyone. I am Arvind Yadav. Today I am going to present on topic interpretation of electromagnetic data using the concept of analytical signal. Next slide, please. Here a flow of presentation. Next slide, please. Now introduction. Electromagnetic prospecting technique is most commonly used in mineral exploration. EM data can be acquired by different combination of transmitter and receiver. But for the same type of geological structure, different combination of transmitter and receiver result in different response. And EM data also obey the Laplace equation. In the present work, one intends to interpret the EM data using the concept of analytical signal. Amplitude of analytical signal is approximated by bell-shaped function, which is dependent on the constant horizontal and vertical location of the source and the nature of the causative body. And the constant depends on physical property, and the peak of the amplitude of analytical signal coincide with the age or the peak of the source. The methodology is the unified approach, which does not require any a priori assumption about the nature of source geometry. Next slide, please. Here we use the concept of analytical signal over a sphere body, buried sphere body in the mathematical form. We know that the potential in a homogeneous isotropic medium for DC source are very low frequency AC sources satisfies Laplace equation, where del square B equal to 0, where V is the electric potential. Since potential is directly proportional to resistivity, so it also follows the Laplace equation, where del square rho equal to 0. And equation 3 is the amplitude of analytical signal, where under root is del V by del S whole square plus del V by del Z whole square. This is the form of amplitude of analytical signal. And when we calculate the potential over buried sphere in figure 1, where potential we calculate at the point of P, where a three-dimensional body of P, the external potential may be developed in the sphere. So the potential at point P, X, Z will be amplitude of analytical signal equal to C upon under root square X square plus Z square whole cube. This equation comes after simplification of equation 3. And now we will move towards bell-shaped function. For electromagnetic data and electromagnetic anomaly, it's follow the bell-shaped function concept, where total gradient equal to d upon r by beta, where beta is the geometrical shape factor and d is constant. Now this equation can be in generalized form like equation 6, where k is also constant and q is the shape factor. when we calculate the value of equation 4 and equation 6, we get the value of shape factor is 3/2. So we can calculate the structural index n equal to 2q minus 1 equal to 2. From here we say that the structural index for a sphere body is 2. This is the mathematical form which I have derived. And now we will move towards experimental part. Next slide, please. Here the horizontal loop survey response over buried sphere, and in this figure we can see that dotted line is the anomaly over electromagnetic anomaly over sphere body, and after apply the concept of analytical signal, we get the two analytical signal peak. And on this peak, when we apply Gray-Wolf optimization and PSO technique, we get the response in this table, where we get the horizontal location, amplitude, depth, and Q shape factor. From here, in this table, we can see that the after variation of search space, we get the value of Q factor is 1.47 for GWO for peak 1, and for PSO we get 1.47, and for peak 2 we get 1.5 the value of shape factor, and 1.47 the value of shape factor. So from here we conclude that the value of structural index will be 2, because in previous slide we can see that the n equal to 2q minus 1. From there we get the value of structural index is 2. So as well as mathematical and experimental parts also show that the value of structural index for sphere body is 2. Next slide, please. We have taken another one example over vertical sheets. In case of vertical sheets, we see that here also dotted line show the anomaly over the EMM anomaly over vertical sheets, and we get the analytical signal, and we apply GW and PSO optimization. From here we also get the value of shape factor, horizontal location, and depth, where the value of shape factor is 1.12 for GWO, and for PSO 0.94, and for peak 2 the result is same. So from here we also calculate the value of structural index is 1, n equal to 2q minus 1, where value of q is 1. So the structural index for vertical sheet, so 1. Next slide, please. Now here the conclusion. Structural index over spherical body and vertical sheets is 2 and 1 respectively. And we inverted field example from published literature data set. The inverted result have been compared with GW and PSO optimization. We report the utility of Gray-Wolf in solving multi-parameter optimization problem in geophysics. Thank you, sir. Thank you so much, everyone.
Okay, thank you very much, Arvind. We have almost consumed all of time. I sincerely thank all the speakers. Professor Rima Chatterjee is here.
I'm here.
Okay, so please take care if there is some any discussion, question, answer from audience sitting.
Sir, what is A mode and what is G mode? A mode and G mode.
This question is with whom? With which author?
With author, the lady.
Okay, Anjali. Anjali, are you here?
Yes, sir, I'm here.
Oh. Anjali, are
What
you here?
is G mode and what is A mode?
Ma'am, I think it's a G Adam optimizer. Am I correct? Are you talking? What? G Adam, are you asking? GADAM?
Yes.
Okay. So, so it's a hybrid optimizer. So it takes the advantage of like Adam, which is a very popular optimizer.
Don't tell me all this thing. Tell me what is G mode and what is A mode.
Can you spell it? Genetically evolved adaptive momentum estimation is G Adam, and ADAM is the adaptive moment estimation optimizer.
Okay. So you have to specifically write all these things.
What I wrote?
You have to write this thing specifically.
I have to write the abbreviation. Yes, ma'am. Yes. Sorry, I missed it. Yes, ma'am.
Okay. Thank you.
Sorry, ma'am. I missed. Next time I'll keep in mind.
Okay. Any other question to any presentation? If no, Vishnukant is here. Can you hear me, Vishnukant?
Sir, he's not here.
Okay. Okay. Then any other question from any audience or anybody? If no, I sincerely thank all the speakers and organizer for giving me opportunity to organize this session. Now I hand over to Dr. Bansal and organizer. Please take care.
Yeah, thank you, Professor Sharma, and thank you, Madam Professor Rima Chatterjee, for nicely managing with the help of Dr. Arvind this session. And on dot, you are finishing, so it is 3:30. Thank you very much for excellent management of time. Thanks to some of the people, those who are absent, because of which we could manage time also.
Yeah.
So thank you very much, sir. Thank you, and IGU will remain indebted to both of you for excellently managing the program.
Okay.
Now, dear participants, now we have come to the last session of today, which will take 5 minutes break, and then we'll start the next session at 3:40, 3:35. So there is a 5 minutes break. So I would like to request Professor Uma Shankar ji, are you there? And Dr. Tanvi Arora ji and Abhishek ji. Three of you have to manage next session, which is the poster presentation section. Are you there?
Yes, sir, I am here. Good afternoon.
Yes, sir.
Yeah.
Yes, Malia Saab. Good afternoon.
Professor Uma Shankar, Professor Tanvi, and Abhishek ji. So
Yes,
we'll
sir.
take 5 minutes break. If you permit, if you want, we can start.
Yeah. Hello, Tanvi. How are you?
Good, sir.
Yeah, your team is excellent, and yesterday also you maintained excellent time. So we are very much thankful to you.
Thank
And
you,
in
sir.
the report we have written today, you have got very good rapporteur also, Abhishek. So probably this session also will be managed nicely. So we can start the program. It seems, do we have Bhaskar Sakia?
No, sir. The first poster which I have is number 4.
Is number 4. Do we have Padmavati?
Yes.
Sir?
Yeah, so sir, it seems we can give 5 minutes break because last session ended on schedule.
Yeah.
So still 5 minutes are there. So if you want to say, if anybody wants to ask anything, you are most welcome in this 5 minutes from any of the presenter or anything.
Yeah. How many presenters are there?
Altogether, there
Altogether,
was
so 28, but I have 16 posters with me.
16 only.
16.
Okay. Yeah, that's
we have
good.
got sufficient time.
Yeah.
But we would like to end it as early as possible.
Yes.
Because Shillong is very cold, considering the cold of Shillong. You may be at a very comfortable place.
No, sir. Varanasi is also very cold, actually.
No, Varanasi is a blessed place near river Ganges.
Hyderabad is pleasant, I think. So.
Very pleasant.
Yeah.
We have our ceiling fans on, so.
The fan is on, and here hot air blowers are on.
So we will take a break and then start.
Yeah, 5 minutes break we can take.
Okay.
We'll start at 3:35 rather, 3:40.
Yes, sir.
Yeah, Dr. Shikhar, you can play some video or some audio or whatever.
All right, sir.
हाँ नमस्कार सर। नमस्कार सर। हेलो हेलो।
Yeah, once again, good afternoon, everyone. And today's poster presentation will be chaired by Professor Uma Shankar and co-chaired by Dr. Tanvi Arora ji, and the rapporteur of the session is Abhishek ji. So I would like to request Professor Uma Shankar and Dr. Tanvi Arora, please take forward this session. Thank you.
Sir, your voice is not coming actually.
My voice was not there.
it was there. उमर सर शायद आपका ऑफ होगा.
आपका कनेक्शन थोड़ा सा वो होगा, स्लो होगा सर. Maybe the music was very loud.
Yeah, it's fine now.
Yeah.
So should we start?
Yeah, again, we welcome all the participants in the 8th session, and this session is the poster session. So yeah, I request Professor Uma Shankar and Dr. Tanvi Arora madam to please take forward this session.
Okay, sir. Thank you very much. In this 8th session, good afternoon to all, and welcome you all in this session. So in this session, we have 3 parts basically related to atmospheric, space and planetary sciences, then marine geosciences, and then last one is solid earth geosciences. And total presenter is 29 listed here, but I think a few are missing or absent in this list. So directly we come to the first presenter, atmospheric, space and planetary geosciences. So as you know that from the technical program, it is very clear that you may get only 2 minutes, but less participants is there, then maybe you can take 1 minute or so more. Okay, so there is a first presenter is Bhaskar J. Saikia is there.
No, sir, he's not there. The first presentation which I have is number 4, sir, on the list.
Number 2 is not there. Manas Pant is not there.
No, sir. And number 3 also.
Shruti Verma is not there. Then we straight come to the Padmavati, please.
But I can't find them in the list as well. Means I have their presentation, but they are not in the. Are they? I'm just asking, Miss Padmavati or Mr. R.K. Tiwari or Mr. V.M. Tiwari, are you here? No, sir, they're not here.
So that's 5th one is Pawan.
5th one is also, I don't have the presentation, sir. And we have to go to number 6.
So it means atmospheric and space planetary geosciences, nobody is there.
At the moment, no, sir.
So
this is remarkable.
Yeah. Why they have submitted the abstract for the listing itself, or I don't know for what. So next stream is marine geosciences. Is Abhishek is there?
I can see his names.
Hello. Yes,
Abhilash.
Abhilash. Yeah.
Abhilash, sir.
Abhilash is there. Then you can present. You can share your screen, please.
I'm sharing, sir.
It's making our job easier, sir.
Yeah.
Yes, good afternoon all. The poster is a statistical study of the earthquakes of the mid-Indian Ocean ridges. The Indian Ocean divergent boundaries are mainly controlled by the tectonic activity of the Indian Ocean. So the Indian Ocean consists of primarily of 3 mid-oceanic ridges joining an inverted Y shape, meeting at a Rodriguez triple junction. The Central Indian Ridge, located at the north of the triple junction, with a spreading rate of 32 to 44 millimeter per year. And the southwest arm is the Indian Ocean ridge is called the Southwest Indian Ridge, with an slow to ultra slow spreading ridge with a spreading rate to 14 to 20 millimeter per year. And the other arm of the spreading ridge, the Y-shaped ridge, is the Southeast Indian Ridge, which is an fast spreading mid-oceanic ridges with a spreading rate of 60 millimeter per year. 60 to 72 millimeter per year. And the seismicity of the ridges are the earthquakes of the ocean floor is generally concentrated along the spreading axis, and they'll have the events are having shallow hypocenters, and very large magnitude events are infrequent in case of the mid-oceanic ridges, and the range of normally the range of earthquakes will be around 3.5 to 3.5 to 4, and most of the magnitude cut off in the range between 4.5 to 5. And the methodology for the study I use the magnitude and the frequency relationship for calculating the b value, and we use the Gutenberg-Richan relationship, which is an empirical relationship which gives the log to the base 10 of n is equal to a minus bm, where the n is the number of earthquake of magnitude m or greater than the b is the slope of the distribution. And for the calculation of the b value, I use the maximum likelihood method has been used for by the Aki 1965 used for the calculation of the b value. And the data I have taken the reviewed IAC catalog from January 1964 to December 2018. There are 15,500 events in the whole region, including the three ridges, and the most of the events are falling in range of 3.5 to 4.5 magnitude, and few higher magnitude earthquakes also present. And for the homogeneity, I took the body wave magnitude scale for the whole the respective region. And for the calculation of the b value, the one of the main important the parameter which need to be calculated is the MC, and the MC is calculated from the FMT the distribution, and MC is calculated using the FMT 90 method by the Weimer and the Weiss. And coming to the results, the seismic parameters A and B values of the three ridges are calculated, and for the central intent ridges, the B value is 1.44, and the A value is 9.768, and for the southeast inter ridge, it is 1.42, and the A value is 9.99, and for the southwest inter ridges, it is 1.17, and the A value is 8.518, and it can be from there. It's the alto sport. The lower the spreading ridge, the rate, the B value is higher in this the ridges. Yeah, thank you, sir.
Okay, thank you very much, Avilas, for your nice presentation, quick and nice presentation. Now we have to, we can discuss, take the question answer at the last, okay? So be present or be online, okay?
Okay, sir.
Yeah, so don't leave the meeting and be there, so we can discuss that. So next presenter is this D. Harita is there.
Yes, sir. I'm here.
Yeah, please. You can share your screen.
Yes, sir. Good afternoon, everyone. This is Harita, and I'm the student of NEHU from NGRI. Today, my topic is convolutional bidirectional SDM network for generation of missing and log data.
You can also put your video on.
Okay, ma'am. Yes, ma'am. Can I continue?
Yeah, you can go ahead, please.
Thank you. Generally, well-log data gives the geological information of a borehole. Distorting data is very common in well-log data due to the instrument damage, poor boreholes, and imperfect logging. And these causes are missing in the well-log data, and it leads to poor interpretation. So without increasing of expenditure, the missing well-log data can be retrieved the information with using a deep learning methods. So in this study, I have used convolutional bidirectional long short-term memory with fully connected layers to estimate to predict the missing well-log data. You can see the flowchart of convolutional bidirectional LSTM network in our methodology. In the first layer, I'm considering the convolutional layer, and in the second layer, I'm taking a bidirectional long short-term memory layer, and the third one is a fully connected layer. All these are connected with each other, and full convolutional layer is generally captures the spatial information from the input data, and the information which came from the input convolutional layer act as the input to the bidirectional long short-term memory, and bidirectional long short-term memory will capture the temporal or the logging shape of the curve, and a fully connected layer will helps to capture the full information, and it will send to the output layer. This is the flowchart of the convolutional bidirectional LSTM network. In the analysis and the discussion, we can see the hypermeters which I have used in this network to predict the neutron log, which is the missing log in our work. In our work, I have considered one convolutional layer and the two bidirectional layers and the two fully connected layers. In between the bidirectional layer and the fully connected layer, I have used a dropout. Why I have used a dropout is the network is easily can fall into the overfitting. To reduce that fitting, I have used the dropout as a regularization, and the dropout is a 0.3 probability. And here I have used the Adam as an optimizer, which is used to reduce that loss function. And here the loss function is mean square error. Excuse me. I have the predicted result which came from the convolutional bidirectional LSTM network is also compared with other networks like bidirectional LSTM and the AMN. The output, we can see the output from the three networks in the results. So from this method, we can see that it is successful in detecting a missing well log data by using the available logs from the well log. Thank you.
Okay, Harita, thank you for your short presentation. So now straight we can move to the third presentation. Jyotsana is there, please?
Yes, sir, I'm here.
Yeah, you can present now.
Sir, I cannot share my screen. It's showing host disabled.
Yeah, he is sharing your screen. No problem.
Okay. Yeah, sir, can you see my screen now?
Yeah.
Okay. So good afternoon, everybody. I'm Palle Jyotsna, working under Dr. Satyavani ma'am in CSIR NGRA as a research scholar. Today, my topic of presentation is gas hydrate dissociation in the Krishna Godavari basin. Role of salinity and bottom water temperatures. We all know that gas hydrate is a crystalline solid in which the methane gas is entrapped, and these gas hydrates are confined to the continental margins and the continental slopes. So in the history, there are prehistoric landslides has occurred due to the gas hydrate dissociation. So this is my motivation towards this study, where I've chosen why the gas hydrate in the Krishna Godavari basin is dissociating. So here. The figure 2 is the study is my study area, Krishna Godavari basin, that is which lies in the eastern margin of India. And for this, I've used seismic data and also the well log data. What I did is, which is shown in the figure B and C, that I have downloaded the salinity in the study area at the depth of 1000 meters, salinity profiles from the 2004 to 2020, and also the bottom water temperatures from the 2004 to 2020. Here, the important thing is the seismic data is acquired in the year 2004, and I have downloaded salinity profiles from the 2004 to 2020. So if we see from figure B and figure C, the salinity is increasing. The figure B is the bottom water temperatures, and figure C is the salinity in the study area. Both the figures shows the increasing trend. So we state that due to the increase in salinity and the bottom water temperatures, the hydrate is dissociating. So I have taken one inline from this 3D data, which is shown in figure 4. In this one, we can see there is a fault A and also the fault B. These fault A and fault B are the active migration pathways through which the free gas below the BSR is dissociating and reaching to the seafloor, and it is causing two slope breaks which are marked by the SB and on the seafloor. So SB indicates the slope break. There are two slope breaks in the region. So we say that this increase in salinity and increase in bottom water temperatures is causing the gas adder to dissociate. In order to further confirm this, there is a laboratory experiment done in which the dissociation temperature for the gas adder is observed at 6.5 to 7 degrees centigrade. So from the figure C, we encountered the similar temperatures at 1,000 meters of water depth. So, so it is concluded that these are the reasons for the gas adder dissociation. And from the figure, that is the steady area, we see there is a circle marked in the red color. So that circle shows that the area where the slope has already occurred. So yeah, from this study, we can show there are submarine slope failures in the KG basin, which are triggered by the gas adder dissociation due to increase of salinity and also the increase of bottom water temperatures. So this is the conclusion. Thank you.
Okay, thank you very much, Jyotsana. Now we have to move. Next presentation is by Satinder Singh. Is there?
Yes, sir. I am there, sir. Good afternoon, sir. Good afternoon, madam.
Good afternoon. You can present now.
Sir, I want to launch my poster from here. Can
yeah, they are going to share the screen. There is no problem.
No, sir, I want to control actually, sir, because I prepared in PPSX format.
They can do because you are already uploaded.
Yes, sir. I have given morning.
So kindly load his presentation, please.
Not this one.
This is yours, I think, Satinder.
Yes, मेरा ही है sir. सुबह किया था मैंने, इसलिए I want my control from here. Some correction is there.
So you want to?
Yes, I want to share.
So you can share. There is no issue.
I want just.
You share from your screen also. Now you are not sharing. Don't take long time. Share.
Okay. You can present him in this one. There is no issue. If there is small changes are there, you can explain that one.
Okay. Please launch. Yeah, good afternoon, everyone. I'm myself Satyendra Singh from CSIR NGRI. Today I'm going to talk about subsurface structures of KG Basin revealed from seismic attributes and other geophysical data sets. Here you can see the study area of key map and geology and tectonics of the region. As we know that KG Basin is bounded by the Eastern Ghat Mobile Belt, Pranita Godavari Gavan Karpa Basin, and Southern Granite Terrain and Pennar Peninsula Basin. And Krishna and Godavari River are throwing a huge amount of sediment into the basin to make it a suitable bomb of hydrocarbon accumulation. So NGRI itself has acquired a lot of seismic data for identification and quantification of gas hydrate. So I have chosen just 2 seismic profiles to pursue the research work. And I have taken a cross line also, which is taken from IONX GXT India SPAM program 2007, which is showing the pink color here. So next slide, please. Please click to second portion. So it is just PPX format, sir. Yes, here is the methodology adopted to pursue this research work. We have just simply processed the data and finally generated that pre-stack time aggregate section, which has been taken forward for data conditioning by applying that seismic data processing and steering the data. We have applied deep steering median filter to enhance the seismic reflector and increase in the resolution. Then we have followed the seismic attribute analysis and computed that some instantaneous amplitude, instantaneous phase, instantaneous frequency, and coherency and energy attributes. And similarly, we have taken other geophysical data sets like from Jevco bathymetry data sets and free air gravity from Sandwell and Smith 2014 and EMAG2 version 3 magnetic data I have taken, and I have done calculation to calculate RTP reduced to pole from magnetic to magnetic grids and Boger gravity from free air gravity. And I have then extracted anomalies, these anomalies from these grids along the seismic lines. And I have plotted those results and response along the seismic profiles. Next, please. Yes, these are the seismic sections of chosen lines, and the data length is 8-second data. Then I have taken 4-second data. Another I have chosen for interesting area zoom portions, which has to be interpreted. Then clearly we can see on the seismic section like major geological features like faults, folding, and gas type chimney structures are easily can be seen. But for better understanding, we need some further processing. Next slide, please. Yeah. So these results are the seismic attributes along the zoom portions. Here we have calculated amplitude, phase, frequencies, and coherency and energy. And each of these attributes, there are a lot of attributes which are the quantity derived or extracted from the seismic data. So each attribute is having their own importance and giving their own interpretations. So energy is giving the reflectivity, and the phase is giving the continuity of the reflector, and frequency also, that how the frequency is changing while moving the waves through the subsurface and deeper part. Coherency is giving the similarity between the adjacent traces, and likewise energy also. If amplitude is high, energy also will be high. So considering all these information and collaborating all these results, we have interpreted the seismic section, which is the right side portion. So we have find out many geological and geophysical and tectonic features like MTD, mass transport deposits, and acoustic transparent zones, and mini fill basins type of structures, seamounts, and mainly BSR. Our main intention was the BSR, which is the prime marker for gas hydrate presence, BSR bottom surface. So we can see clearly visual here and here also. Actually, this presentation I made in another presentation in Zoom part, but I am, if possible, you can please zoom it again. This last portion, please. Yes. So like gas type chimney structures, and so many features we have clearly identified and collaborate and validated with these seismic structures. Similarity attributes are very much useful to enhance the faults and fractures zones. Next slide. Same result we have followed with other line B also. So here also we have find out like folding type of structure and thrust fault type of structure, gas chimney, seamount, and BSR. BSR is clearly, you can see here this pink color line. Here also it's clearly in energy, and this one also it is very clearly visible on the seismic section here also, and here also. You just see the amplitude here. This which is a prime marker of gas hydrate, mimicking the shape of seafloor, opposite polarity, and cutting dipping geological strata. So we have find out so many geological and geophysical scenario in that seismic lines, both of the lines, inlines and cross lines. Next slide, please. Then we have calculated that velocity analysis, and I have superposed all the 4 anomalies over the seismic lines to see how the trend is moving according to the subsurface structure. I have not done modeling work, but I just have plotted the response over the profiles like gravity, how gravity, magnetic, and bathymetry, and free air gravity, how it is changing that trend. And this last figure is showing the 3D conceptual model, how the live location of the profiles are falling in the basin. We can see that how the Krishna Godavari rivers are making the delta fan in that, how the sediments are coming to the basin to make this basin for hydrocarbon exploration. we can see clearly here. So there are host and graben type structure in northwest and southeast profiles, and there are deep gradient in that shorter profiles while moving to the deeper ocean parts. So we have next. Yes, so this is the conclusion. We have demarcated a undulation seafloor topography while generating the host and graben trends along the strike and the northwest southwest profiles, MTDs, faults, forts, channels, and gas type chimney structures and blanky chaotic reflections we have found out. And BSR we have clearly demarcated along the profiles. I thank to Director CSR and NGRI to pursue and permit the result on this platform. Thank you, sir. Thank you. Thank you all.
Thank you very much, Satinder, for your nice presentation.
Thank you.
And in this marine geosciences, this last presentation by Gaikwad.
Yes, sir.
So you can present, please.
Good afternoon, all. Myself, Wilson Gaikwad, working as a PhD scholar at CSIR NIO under the guidance of Dr. Firoz Badesab. My topic is a comparative diagenetic analysis of shallow and deep-seated gas-headed systems from the Bay of Bengal. This is the systematic high-resolution rock magnetic study complemented by mineralogical and petrological observations conducted on the sediment cores representing the shallow and deep-seated gas-headed from the Bay of Bengal. In this study, we try to address two key questions. The first one is how magnetic minerals respond to the geochemical environment at two different diagenetic settings, experiencing variable fluid sequences. And the second question is to elucidate the control on the magnetite and greigite orthogenesis in sulfidic, methanic, and gas-headed bearing sediments. Sediment magnetism in both cores are carried by complicated magnetic mineral assemblages of detrital, titanomagnetite, or silica-hosted magnetic inclusions, then diagenetic pyrite and orthogenic magnetite or greigite minerals. Magnetic mineral proxies like ARM by SRM and SRM by kappa provide the useful insights on the diagenetic and orthogenic formation and preservation of magnetic particles in the studied core. Then preferential diagenetic dissolution of fine magnetic particles in sulfidic and orthogenic formation of magnetite in methanic zone is clearly evident in the ARM by SRM ratio profile. Elevated values of SRM by kappa in the sulfidic, methanic, and gas-headed bearing zones indicates the enrichment and preservation of ferrimagnetic minerals like sp greigite particles in both the cores. Based on the magnetic proxies, which are ARM by SRM and SRM by kappa, with XRD and SCM data, we demonstrated that the formation of orthogenic magnetite and magnetite in sulfidic and methanic zone is tightly linked with the microbial iron reduction processes. Then multiple layers of methane-derived orthogenic carbonates throughout the sulfidic and methanic zone provides evidences of the episodic intensification of anaerobic oxidation of methane at both the sites. We summarize our finding in the conceptual model, and we put forward 4 scenarios to explain the plausible mechanism of greigite formation and preservation above and within the gas-headed zone in deep-seated gas-headed, which is a NGHP 01 15A profile, and the shallow gas-headed core, which is the SSD 45 station 4 GC1. In the deep-seated gas-headed core, decline in rising methane flux due to hydrate accumulation in the underlying sediment constant, the sulfide production, and preferentially favored greigite formation and preservation above the present-day gas-headed occurrence zone. That is from approximately 75 meter below sea floor to 81 meter below sea floor. The second scenario is the slow diffusion of methane after dissociation of fossil gas added horizon, enriched the microbial activities and favored the greigite orthogenesis. That is another reason. And in shallow gas added core, a close linkage between presence of orthogenic greigite within the fracture filled gas added layer demonstrate the greigite formation in the zone was governed by microbially mediated diagenetic reaction fueled by the presence of gas added, or the another possibility is that thick layer of orthogenic carbonates in uppermost sediment intervals acted as barrier and hindered the supply of downward diffusion seawater sulfate concentration and subsequently create a sulfide deficient zone which provide a conductive environment for the greigite formation and preservation within the gas added zone. All these interpretations are supported by the thermomagnetic low temperature data, Fock diagrams, ACM, EDSA, and XRD data and petrographic observations on the orthogenic carbonates. And this study was submitted to marine geology, and recently we got the positive reviews from the journal. Thank you, sir.
Okay, thank you, Gakwar. Thank you very much for your good presentation. Now we have to go through the solid earth geosciences presentations. So Tanvi, you can take care, please.
Okay, sir. Thank you. So, do we have Abhishek Kundu?
Yes, ma'am. Hello.
Yeah.
Am I audible?
Yes, Abhishek. So, Abhishek, you can put your video on and then start the presentation.
Sorry, ma'am. I am using a desktop and I don't have a cam.
Okay, then please proceed.
Good afternoon, everyone. I am Abhishek Kundu, working as a research scholar in the Wadia Institute of Himalayan Geology under the supervision of Dr. Debojit Hazarika. Today, I am going to present a seismotectonic study of the Lohit Valley region in the Eastern Himalaya, Arunachal Pradesh. The seismicity in the northeast corner of the Indian plate in the Eastern Himalayan syntaxis has been studied using local earthquake data recorded by seismological network established by Wadia Institute as well as the ISC reviewed catalog. The Eastern Himalayan syntaxis forms a complex triple junction that joins the Indian and the Eurasian plate with the Burma plate. This region is tectonically different from the rest of the Himalayan mountain belt, as the EHS marks the transition from collisional tectonics of the Himalaya to strike-slip tectonics in the southeast Tibet. This region has already produced the largest intercontinental earthquake ever recorded, the 1950 Assam earthquake, which is marked by the blue star in the map. At the frontal segment of the EHS, the geometry of the Mishmi, Lohit, Tiding, and Walang faults at depth has not been studied earlier. So we choose this area along the BB section along the Lohit River Valley for the seismotectonic study. Before going into the geometry of the faults, from this figure at the right hand side, it can be seen that the active subduction of the Indian plate beneath the Indo-Burma ranges ceases beyond the 27-degree northern latitudes, as there is no signature of Benioff zone like structure further north of the 27-degree. While the crust beneath the Siang window and the Lohit Valley is seismically active up to 40 kilometer depth. Now moving forward. From the focal mechanism solution, can you go a little down? Yes. From the focal mechanism solution, yes, thank you. Solution of the local earthquake data along the BB- profile, it can be seen that the Mishmi, Lohit, and Tiding faults are steeply dipping thrust faults. While Walang fault can be characterized as a strike-slip faults with minor deep-slip component, which supports the existence of the indentation and rotational tectonics at this corner of the Indian plate. From the distribution of pressure axis orientation, it can be seen also that there is a significant strain partitioning present in the crust due to oblique convergence of the India with Southeast Tibet, as well as complicated due to complicated syntaxial tectonics. The strain partitioning can also be described in terms of right lateral strike slip tectonics in the back arc region along Jiali fault and the Walang fault, and slightly oblique motion along the Mishmi thrust in the front arc. Thank you, ma'am.
Yeah. Thank you, Abhishek. Do we have Mr. Bhaskar?
Yes, ma'am, present.
Yeah, please present your poster.
Okay, can I share, ma'am? Yeah.
If possible, you can put your video on.
Sure, ma'am. 1 minute. Ma'am, presenting in system, ma'am, it is not possible to do.
Okay, go ahead.
Good evening to all. Myself, Bhaskar, working with Dr. Prakash at CSR and JRI. My presenting topic is SN wave and VPS tomography of promotion beneath the Indian shield and its adjacent regions. We are presenting high resolution SN tomography by using the active data. The average SN velocity is varying in the region. Average SN velocity is 4.6 km per second, and fast SN velocities are found in Indian Catons, Tarim Basin, northwest part of the Indian Plate and Bay of Bengal, whereas Burmese or Hindukos, Tibetan Asian parts of India is dominated by the SN velocities. And this is the tectonic map of the Indian region. It is Indian region, southern regions, the Indian shield. It carrying their catons separated by fold belts and social zones, and western part of the Bay of Bengal, surrounding regions of Hindukos, Tibetan Plateau, and Burmese. The high resolution SN waves propagating twice reflect from submoon and eventually recorded as a first era waves at regional distances. The propagation of SN is influenced various factors like promotion, mantle thickness and thermal state, which can be interpreted as a composition of water and water content. Stable and cold stable regions have less influence of SN wave propagation, whereas unstable and hot mantle upwelling regions are strongly attenuated. This is the data criteria we have to apply for SN and even the PN is also. I present PN because in VPBS image it is required the PN velocities also. So we have restricted epicidal distance of events is 40 km below, and epicidal distance is 2 to 15 degree. And body wave method always we have taken for because these two waves are very low amplitude. We have to choose magnitude size is very earthquake sizes should be very high. This is the methodology we are following here in 1996. This is the the large scale tomograph problem solved by LSM or iterative speed that is developer found and sounders. And the result of discussions as a part of most of studies in result of 1 degree, 1 by 1 degree size, and that is the SN velocity map. It is under 0.08 km per second error map. And this is the final SN wave tomography map. This is the 4.6 km per second is the mean velocity. Blue one indicates the high SN wave velocities, and red one indicates the lower SN wave velocities. The most of Indian region is varying SN velocity is 4.2 or 4.4 to 4.75 km per second, and western and eastern Java patterns are nicely separated by closed granite, and high SN wave velocities in the you can find out here. This is the Kadapa basin, high SN wave velocities you can find out, and the Basta crater and Aravali crater and Singwang crater is showing low SN wave velocities due to warm lithosphere. And the blue one you get the Indian plate subducting the beneath the Himalayan regions, supporting the subduction. And this is the image generated by VPBS tomographer of the Indian region. Here we are using the PN wave velocities also. The VPBS values are ranging from 1.69 to 1.89, and it is supporting the magnitude tectonic region. And you can find out the low VPBS is separating the RGP from Darwa crater. And most interesting results finally here to find out the Bay of Bengal region. It is low VPBS clearly separated from Indian region. At the same time, The Bay of Bengal is separated by 90 states. Western side is you can find low VPVS, and the western side is the high VPVS. High VPVS velocities clearly indicate to the presence of parsiments and subducting the Indian lithosphere beneath the Andaman region of Sunda plate. And in western part, you can find out the low VPVS, which is clearly indicate the chemical alteration, maybe presence of other pyroxenates or eclogate due to plume effect, past plume effect. Here, other pyroxenates presence is clearly supported. You can find when it is magnitude is increasing, then it will indicate the presence of other pyroxenate. It will produce the low VPVS ratio. You can find out Lee 2003 paper. That's it, final.
Okay, thank you, Mr. Bhaskar.
Yes, ma'am.
Do we have Mr. Dalai?
Yes, madam, I am present.
I request all the presenters to be present here till session ends. There may be questions for you.
Okay, madam. Can I start, madam?
Yeah, please, Mr. Dalai.
Good afternoon to all of you. And I am Vijayananda Dalai, presently pursuing my PhD at CSIR NGRI, Hyderabad, under the guidance of Dr. Prakash Kumar sir. My poster is all about the application of an unsupervised deep learning approach to minimize the noise present in the receiver functions data. Basically, receiver functions technique is a robust tool to image crustal and upper mantle subsurface structure. And like other seismic wave field, receiver functions data also contain different kinds of noise, and that leads to the overinterpretations of the data. So in order to overcome this kind of problem, here we have used deep learning based encoder-decoder framework, where the input for the network are the patches extracted from the directly raw RF data directly. Please zoom in figure 3 to 5. Please, can you please zoom in figure 3 to 5? Yeah. If you see figure 3 to 5, subsequent parameters are fixed by considering the realistic scenarios by adding different types of Gaussian noise to the synthetic RF data. And in order to mimic the real scenario, the RFs are computed using single and multi-layer velocity models and are contaminated with different amount and different kinds of noise, such as spike-like noise, deconvolution artifacts, and real noise extracted from the field RF data sets. It's shown in figure. Please go to figure 5 to 7. Yeah. Go down here. These are the figure 7 shows the spike noise, and the figure 8 shows the deconvolution artifacts. And in all the cases, the crustal and intercrustal and upper mantle converted phases are well resolved, even the corresponding multiples also. Now please go to figure 10, 12, 11, and 12. Okay. Here we check the performance of the present network on the observed data set. At first, we apply it to the Hyderabad stations. It's shown as figure 10. Here, the weak converted phases from X and 660 km discontinuity are well resolved. And then, interestingly, we apply the same to the more noisier data sets collected from the two international data stations, that is LBTV and CORE. That the crustal, if you see the RF images, the crustal and upper mantle phases are improved significantly, which are barely visible in the individual RF data sets. And we hope this study can be further implicated in different aspects of seismology too. Thank you very much.
Okay, thank you, Mr. Dalai.
Thank you, madam.
Do we have Charu here?
No, ma'am.
Okay. Mr. Chinmay?
I have his presentation.
Yeah, he is there. Chinmay is also here. Okay. So, Chinmay, please start with your presentation. We are not able to hear you, Chinmay.
Okay. Good afternoon, all panel members virtually present here. I am Dr. Chinmay Haldar, working as a scientist at Warren Institute of Himalayan Geology. And can you go please little below? Okay, this is my study region. Kistabar is a seismically active and it is bounded by different thrust and Kistabar window, Pranjal thrust, and also covered by compressional extensional shear. So here we present the first seismic image of the crust and intercrustal low velocity layer within the Doda Kistabar region. And this figure shows the different seismic teleseismic event whose waveform used in the study. And here we use the reserve function technique, and this figure shows the synthetic reserve function, and this is the observed reserve function. The red line shows the conversion time from the MOHO beneath the individual station. Please go upper portion. And this figure shows the stack reserve function, and positive black color indicates the positive conversion and gray color indicates the negative conversion. The positive conversion from the MOHO varies from the 6 to 7 seconds, and negative conversion takes from the low velocity layer varies from 1.6 to 2.8 seconds, and the positive conversion from the mega Himalayan thrust beneath the 4th station varies from 3 to 4 seconds. And this figure shows the model of the shear velocity got from the inversion. From the inversion result, we can see that the MOHO thickness varies from 47 to 58 kilometers, and it increases from north to south direction, and also the top of the low velocity.
I think we lost the connection, Dr. Chinmay.
Yes, ma'am, it seems.
Hello?
Yeah, we can hear you.
You can put your video off. I think signal strength is not good.
So low velocity layer varies from low velocity layer with lying top portion varies from 11 to 13 kilometers and extended downward up to the 29 kilometers. Please go a little below. Get a good correlation. We superimpose the depth of the seismic event with the shear velocity model got from the inversion result. And interestingly, we can see that the most of the earthquake lies within the low velocity layer. So we can suggest that the low velocity layer associated with the weak zone that has enabled to enable the pre-existing fault and activated the pre-existing fault to generate the most of the earthquake. Thank you.
Okay. Thank you, Dr. Chinmay. Do we have Mr. Dilip Kumar Yadav?
No, ma'am.
Okay. Mr. Gaurav?
Yes, ma'am. Good afternoon, ma'am.
Yeah, good afternoon, Gaurav. Yeah.
Good afternoon, everyone. My name is Gaurav De. I am going to present my research work on a topic of spatial B-value variation and hazard analysis in the Naga-Patkai Hill of Indo-Burman range. As this region is highly seismic prone due to convergence of Indian plate and Burma plate, more than 1200 earthquake with magnitude earthquake recording in this region in the last 25 years, which is represented in figure 1. For estimating the B value, maximum curvature method is used, which shows a average B value of 0.66 and magnitude of completeness of 3.0. This is represented in the figure 2 and figure 3 and 4, which shows a distribution of the earthquake with time and magnitude histogram respectively. The earthquake data of this region is taken from the CSIR niche data and ISC catalog with a grid parameter of 0.01 degree. In the figure 5, this is the 3D distribution of the earthquake. The next figure in the figure 6, the area with a lower B value, which demarcates the high stress development whereas the region with a higher B value indicate high seismic prone area with heterogeneity. In the figure 7, with increasing depth, the overall B value increases. There are two distinct stress partition layer is showing at a depth of 20 to 25 kilometer and 40 kilometer. The overall spatial variation in the B value across this region in between 0.6 to 1.05. Now this spatial B value study helps to identify the potential hazardous zone using the spatial variation. The lowest B value observed in the southern part of this region and the northern part which is showing the higher B value. So the region of the lower B value possibly likely to be prone of the larger earthquake in the coming future. Thank you, ma'am, and I am really grateful to IGU for giving this opportunity.
Yeah, it was very timely, Mr. Gaurav.
Thank you.
I think all the presenters are keeping timelines very nicely. Do we have Mr. I don't know how to spell the name.
No, ma'am. Number 18 is not there.
Rama.
Rama. Yeah.
He's
Okay,
not
he's
there.
not here. Okay. Manjula is here.
This way.
Okay.
Job and print together.
Manjula, please start your presentation.
Dr. Manjula, can you hear me? Ma'am, she is not responding.
Manjula, are you here? Oh.
She's here, ma'am, but she's not responding.
Okay, then we can go for the next one till she comes back. Miss Ramya? M. Ramya, are you here?
I have the presentation, ma'am, but the name is not there in the list. Means they're not online.
Okay. Mr. Sushil Kumar?
Hello, ma'am.
Yeah.
Hello, ma'am.
Yeah, Manjula?
Ma'am, am I audible?
Yes.
Yes, Manjula, you are audible.
Oh, sorry.
Is it Manjula or Ramya?
Hello, Dr. Manjula. Again, no response.
Okay, let's go for the next one till the connectivity is solved. Mr. Sushil?
Hello, ma'am. Tell me, ma'am, am I audible?
Yes, Manjula, you are audible. Manjula, you can start the presentation, please, if you are here.
Yes, sir. I am here only, sir.
She's hearing the voice in a delayed manner, ma'am. That's why she's responding late.
Okay. So, Manjula, please start your presentation.
I think she's not in good connectivity.
Hello? Sir?
Yeah, Manjula is there.
Manjula, if you can hear us and if you can see this shared
sir.
screen, you can start with the presentation now.
Yeah, you can go ahead, please. Manjula, you can go ahead.
Hello.
You are mute. You are mute. Unmute yourself. Manjula, unmute yourself.
Sir, she's having network issues. I'm pretty sure.
I think there is a lag. It should not
Yeah,
be there.
there is a lag, ma'am. Yes.
Yeah. So, sir, we can put her on hold for some time.
No, we can take him in last, maybe.
Okay.
Yeah.
Okay. Do we have Sushil?
No, ma'am.
No?
Ma'am, Tanvi ma'am.
Yeah, Manjula, we can hear you. If you are able to hear us, then please start your presentation.
Okay, ma'am. Okay, ma'am. I'm starting from other computer. Please, 1 minute, ma'am.
Yeah, sure. Sure.
The presentation is on the screen, Manjula. You don't have to share it.
Okay. Sorry, everyone. I'm Manjula from Geometric Observatory, NGRI. Today, I'm going to present our work on the characteristics of geomagnetic variations at geometrically conjugate locations over in a sector. Geomagnetic field is constantly changing, and this field shows a seasonal and day-to-day variability, and this geomagnetic field has internal and external source. The variations about a few nanotesla minutes to days. This is from the external source. From this figure, it is understood that we have a diurnal changes daily from morning to in the evening. We have we can see the maximum amplitudes during local noon time, and this is due to the ionospheric current systems. And at in our study, we use the two conjugate sites location. One is Hyderabad in northern hemisphere, and Gun is at southern hemisphere. And also we have taken Tirunelveli observatory data. It is from equatorial station. Please go to right top. This figure shows data from 2012 to 2016. Here in this figure, we have taken geomagnetic H component peak values, daily peak values. Here at Hyderabad data, top panel, it shows the maximum H amplitudes during spring equinox and minimum value winter solstice. And at Tirunelveli and Gun, it shows the equinox seasons. It shows the maximum and minimum at the summer solstice. When coming to the daily amplitudes, this shows. This figure shows the daily H amplitudes, and Hyderabad has the low amplitudes when compared to the Gun data. Where we take the Tirunelveli data, it has the higher amplitudes because of the additional equatorial electrojet effect. When we are coming, please go down slow. Please go up. Sorry. Please go up. This corner figure, right corner figure, shows the EEJ peaks. EEJ is equatorial electrojet effect, which is calculated using the low and equatorial sites. At equatorial side, we have the additionally enhanced field because of the EEJ. Here, when we calculated the EEJ using Hyderabad data, EEJ amplitude shows the equinox seasons peaks at Hyderabad. When coming to the Tirunelveli, it shows GAN plus Hyderabad data. It shows the minimum seasonal trends. When coming to the EEJ peaks using GAN data, it is not showing any seasonal trends. This figure shows that EEJ effect is clearly seen at Hyderabad. Is clearly seen using calculated using Hyderabad data, and it is minimum EEJ amplitudes noticed at using GAN data. And coming to this figure, please go down. And this is the counter electrojet effect calculated using Hyderabad plus GAN and GAN data. We noticed counter electrojet, clear counter electrojet when we calculated EEJ using GAN data, and which is shown in green color. Coming to the seasonal trends, CEJs, more number of CEJs occurred during During spring equinox, at all three stations, means Hyderabad, Gan, and Hyderabad place Gan, when we calculated. In spring equinox, we noticed maximum number of CEJs, but more number of CEJs observed when we calculated EEJ effect using Gan data. From our studies, we have noticed that longer width diurnal variation noticed at a Gan observatory when compared to the Hyderabad, and clear EEJ amplitudes noticed at when EEJ calculated using Hyderabad data. Less amplitudes noticed when we used GAN data. Thank you, ma'am.
Okay, thank you, Manjula. Since you put so much of effort to finally present your work.
Thank you, ma'am.
So moving on, do we have Ramya? I think she's not here.
No, ma'am. I have the presentation, but she's not here.
Okay. So Shil Kumar is also not here.
No.
Yeah. Jyoti Priyam Sharma.
Yes, ma'am.
Yeah, please, Jyoti. Please present your poster.
One second, ma'am.
Yeah. Okay.
Good afternoon, ma'am. I am Jyoti Priyam Sharma, research scholar from Applied Geology Department of IIT ISM Dhanbad. The topic of my presentation is copper mineralization in the North Delhi Fold Belt, a prognostic IOCG type deposit in the intracontinental rift setting. Now, my study area is Nimka Thana Copper Belt, which is a part of the North Delhi Fold Belt. It is a southeastern, it is towards the southeastern fringe of the Khetri Copper Belt. It is mainly hosted by the metaphylites and the dolomites. It is of Mesoproterozoic age. Now, it is the only bornite-dominated copper deposit of India. Although they are mostly in the world, chalcopyrite is basically dominated, but it is the only bornite-dominated. And GSI has found approximately around 130.3 million tons of has been estimated from the area. Now, the bornite domination is mainly in the form of secondary minerals, secondary copper sulfides, and primary. Even though copper mineralization is there, there are also the occurrences of the barite and the iron mineralization. It also albitization and scapulitization are present in the area. Now, it is on to know about more about the mineralogical aspect to correlate the mineralogical to the rift tectonic setting. We have taken up petrography and the geochemistry, including the XRF ICPMS and the mineral chemistry using the LICPMS. Now, when we go to figure 1, we have done ore petrography and hosto. We can see that I have given field photographs, also the petrological evidences. We can see that the malachite stainings are present within the barite vein as well as the metaphylites, and we can see a iron vein and the scapulite. Now, from the figure 1C, we can see a photomicrograph. It shows that there are disseminated forms of bornite present in the area, which is the suggestive of the syngenetic nature of the deposited. Also, from D, we can see that pyrite, chalcopyrite, and magnetite are simultaneously precipitated within the dolomite, which shows the epigenetic nature. From figure D, we can see that from G, sorry, I can see that there is a simultaneous precipitation of the chalcopyrite and the bornite, which also shows the syngenetic nature, and the H, which also shows the supergene enrichment. As we can see that the magnetite is being formed with the bornite, and there are relics of chalcopyrite still present in the rims. Then we took up, as we know that the geochemistry of sediments are used to understand the tectonic framework. Some selected samples were presented here, and from which we can see that most of our data fall within the passive margin setting. Also, we have a copper-nickel ratio from the trace element data, which is less than 1, but this is also a signature of the sedimentary origin. Now, even now from in the results, I can say that there is a dominance of the secondary copper sulfide mineralization, which is linked to the supergene enrichment of the primary sulfide mineralization. Previously, I had also done the thermometry, microthermometry from that is a fluid inclusion data, which shows the temperature range from 225 to 320 degrees centigrade. Also, the tectonic discrimination diagram showed that most of our metasediments fall within the passive margin, and there is wide scale solar metasomatism, which is evidenced by the presence of scapolites and albitites in the area. And the trace element data also shows that the cobalt by nickel ratio is less than 1, which points towards a sedimentary origin. Now, briefly, I have to summarize. Then I can say that the distribution of the sulfides can give an idea of the basinal condition. As we can see, the secondary sulfides are dominant in the oxic condition, which is a shallow basinal condition, and the anoxic conditions present towards the deeper parts is evidence from the primary sulfide mineralization. Then the temperature range from 225 to 320, it suggests the fluid epithermal hydrothermal activity. Whereas the low to moderate salinity is indicative of the interaction of the hydrothermal fluid, not the water circulation. And the massive soda metasomatism and could be linked to the granitic emplacement, which is already established in the Delhi supergroup and also the North Delhi fault belt. Also, the activity of the hydrothermal include, which provides the you can say the chloride ion serves as a ligand for the copper mineralization. So it is the hydrothermal activity. And obviously from the major element data, we can see that most of the selected samples fall within the passive margin, which is the mature and the recycled sediments. And it is also consistent with the deposition of the Delhi supergroup, that is an evolving intracratonic rift basin. Now, finally, I can say that because there is massive elevation in the area, Khetri is already an established IOCG deposit, and the Nimka Thana is also a IOCG, probably a IOCG deposit, and the similarities with the Olympic Dam deposits, all those two things, and favor towards a rift mineralizing belt for the copper mineralization in the Nimka Thana copper deposit. Thank you.
Thank you, Jyoti. Do we have Monica? Miss Monica? Sayan Kumari?
No, ma'am.
Okay. Mr. N.N. Chakravarti?
I have the presentation, yes.
Yeah, please. Please present your poster.
1 second, ma'am.
Yes. Good evening, all. Myself, N. Chakravarti, working as a research scholar in CSRI, NGRI. In my present topic, in my present poster presentation, I am presenting the Palgar seismic storm activity, which is presented in the western part of the Deccan volcanic provinces. So, in this, to understand the role of seismic genesis and subsurface crustal structures, we used MT method to understand the genesis of the region. So we carried the profile 1 along the seismogenic region to understand the seismogenicity of that region. So further to understand more about the crustal structures and understand the pre-earth structures of that region, we carry another profile to further south of that profile 1. So here we can see that the profile 1 in this where earthquake storms are concentrating on the present profile 1 region. So move on, please. So here we carried MT survey for broadband. We carried a broadband MT survey to understand the crustal structures of that region. So we continue because there is more crustal scale features which are presenting on that region, and also which are impacting more that which in the present which are more affecting the presence of that model in that region, which can be shown in the phase sensor analysis of the data, which is on in short time period. So here we can see the three-dimensionality of that model. So to get the 2D model to move about, to get the 2D pseudo section, we have to reduce the three-dimensional effects of that region. So we use the downweighting method to dismiss this effect in the 2D model, and then we carried we checked robustness of the model by carrying the sensitive analysis. So after doing this modeling and processing steps, so we finally got this 2D section for this profile 1 and profile 2. So where this in both the sections we can see the extension of the U-shaped conductors and crustal scale features present, conducting features present on the model. So here also in the profile 1, we can clearly see where the effects are majorly concentrating on the conducting zones which are in the very shorter crustal levels, and also from other geophysical and geological evidences, we found that there is a small scale crustal faults and present and regional scale structures present in that region. So here that U-shaped conductor could be the high level crude body rift zone, which is also contacting with this small scale crustal faults, where we can see the resistivity contracts. This could be the small scales are present on the crustal level. So where there is a contact in these zones, which could be leading to the weakening, so making this zone to more vulnerable to the stress accumulation. So when there is a there is stress accumulated in this region by aid of external fluids or some external water or some other contents, which also can contribute in this region to for further increase of the stress levels. So when these stress levels are more, then the energy is releasing in the small scale magnitudes in long durations. So this region is this region is so getting this storm type activity because of this interaction of this crustal scale and regional scale contraction of the structures along with the presence of this fluid in this region. Thank you.
Okay.
Yeah, okay, Mr. Chakravarti. Do we have Subhash Smita Biswal?
No, madam.
Okay. Utsav?
I have
Good evening, everyone.
Yeah, good evening, Utsav. Please present your work.
Yeah. So I'm a doctoral candidate in Earth Sciences Department, IIT Kanpur, under the supervision of Dr. Nimesh Mandal. So in this work, I want to show the application of dimensionary reduction techniques on DNN models. So what happens, like now this deep neural networks gaining popularities. So, but they need huge training data set to get trained. So, but huge data sets bring us the redundant information, which decreases the speed of training and as well as introduces the overfitting in the model. So to avoid that, we can, this is also termed as a curse of dimensionality in the machine learning community. So to take care of this, there are some techniques which could be applied, which we can apply on this data sets before training the model. So in this work, I have chosen two techniques, which are k-means clustering and principal component analysis. So first, what I did, I have generated synthetic data sets using one open source Python library. And then I applied first k-means clustering on the data set. So when I applied the k-means clustering, So it reduces the whole data set into a data set into 4 clusters eventually. So you can see on the figure number 2. So, and due to which the size of the image also drastically decreases. So we don't need a big storage space to store the data set. So first benefits comes in terms of storage, and plus less clusters are present in our data set. So next we applied PCA. So PCA is also reduces the dimensionality of the data sets. So earlier we have like something in lakhs number of features in our training data sets. Then we applied PCA on the data set. So PCA, what it does, it aligns the data set into number of principal components. So applying PCA on our data set with 99% variance, the total features reduced to 300 features only. So which is a significant reduction. So afterwards, what I did, like, or we did, like, we trained our model, deep neural model with without applying these techniques, and then then we applied these techniques to data set, and then we trained our model. So like figure 3 is the figure 3A is showing the results obtained when we haven't used any we haven't pre-processed the data sets. Similarly, the figure B is when we applied k-means clustering and trained the data sets. Figure C is like when we applied PCA to the data sets and then trained the model. So what we conclude is we see that there is a significant reduction in computational times for PCA. But in terms of k-means clustering, we don't see much time, but still our data sets and storage space is reduced to significantly. And if we compare the results in terms of error, we can also see that there's not significant variations in the RMS error. So and still so far I have applied it into 3,000 data sets only. So as soon as our data set will increase to 30,000 or 40,000, which is usually the trend currently in my field is going. So generally people's past work have used 30,000 or 40,000 data sets. So I have applied in 3,000 data sets so far. So this much improvement I've already seen. So what I want to conclude is like there is a trade-off between error and computational time. So when you are applying, and what are the techniques you are, like, you can see there's k-means clustering, there is a less improvement or less error or more computation time. So you always have a trade-off, like, and there are many other techniques also available. So you can test your data sets and perform the training and see like how this dimensional reductions is improving in your work. So that's all from my side, and thank you so much for providing me opportunity to present my work. Thanks. Thank you all.
Yeah, thank you, Utsav. So the last presentation, do we have Mr. Vinod Matthews here?
Yes, ma'am.
Yeah, please.
Okay, I don't have your PPT, Mr. You can, I guess, share by yourself.
Yeah. Yes, sir, I can share. Is it visible, sir?
Yes.
Yes.
Yes, please. Yeah, Mr. Vinod, please go ahead.
Yeah, ma'am. Yes, good evening, one and all. First of all, I would like to thank the entire IGU team for providing, giving me the opportunity to present my work. The work constitutes the prediction of groundwater level changes from precipitation data using Bayesian neural networks in Visakhapatnam district. It is a well-known fact that precipitation is a major factor that could influence the input or the recharge of a groundwater system. And also these were influenced by the solar activity and ocean atmospheric circulations when measured from, or when we look from annual mode to many number of years. Here I tried to analyze the groundwater levels which were derived from the GRACE and GRACE FO missions and the average precipitation data which were collected from the rainwater gauges in and around Visakhapatnam district. The study area constitutes, just a second please. Yeah, the study area is shown here, which constitutes the GRACE data, which is represented with capital G, and the rainfall sample locations were indicated with L1 to L9. The raw and interpolated GRACE equivalent height data and the Persian rainfall data were shown in figure 2, and the light green line circles denote the equivalent water height data, which is taken as the index for predicting the groundwater levels. The shaded region shows the gap between the GRACE and GRACE FO mission, and the data was actually taken from April 02 to April 2020, from April 2002 to 2020. So the procedure which has been employed in carrying out the neural networks is mainly by taking training, testing, and finally validation. The Bayesian neural networks, these are actually probabilistic approaching methods. These constitutes of weights and biases that are probability distributions. The architecture is present here, which constitutes an input layer and output layer, and the connection between the input layer and the output layer can be viewed by hidden layers. In my work, I have taken 10 hidden layers, and the input data we have taken as the rainfall or the precipitation data, and the desired output is the estimation of groundwater levels in Visakhapatnam district. So the general architecture can be seen in this figure, and so here we can observe that the training, testing, and validation, when we look at this, the best output could be seen in the training at R is equals to 0.7. Here, while carrying out the process, the first, actually the nodes, which were also called as neurons, between these neurons, the signals were passed using the connection links. The connection links represents the biases and the so-called weights, which constitute the signal strength. And each node applies a non-linear transformation, which is called as an activation function. Here, a sigmoid function can be used as an activation function in order to bring out the desired output from the input. We can observe the best performance, training performance, which was arrived at by using the trial and error. The trial and error were performed by taking monthly data starting from 2 months to 12 months. And finally, the best output or the best fit has been achieved at around during 6 months lag. So here we can observe the best performance is at 37.48. And finally, we try to analyze the equivalent water height data from the GRACE and GRACE-FO missions and the average precipitation or the rainfall data in order to find out or predict the groundwater levels. To carry out that work, we used non-linear autoregression Bayesian neutral networks. Finally, 78% of groundwater level changes are sensitive to the rainfall or precipitation has been deduced, and 22% of the changes are attributed to the randomly varying man-made and weather changes. So to conclude, I want to say that these artificial neural networks can be used to predict the groundwater levels by taking various impact factors. Thank you, one and all, and thank you very much for giving me this opportunity to present my paper. Thank you, ma'am.
Thank you, Mr. Matthew. Uma sir, so over to you now.
Yeah, thank you very much to all the presenters. Discussion part, session is open for the discussions. If you have in audience some questions to the particular presenter, then they can ask quickly, please.
Yeah, we have done the team, Professor Uma Shankar and Dr. Tanvi Arora, you have done excellently well, and you too have managed with the support of some of the absentees. The time was very well managed. Excellent.
Hello, Professor Uma Shankar. Am I audible?
Yeah, yeah.
Yeah, it is Dr. P.C. Kumar from Wadia.
Yeah.
Yeah, I have a question to one of the presenters who presented on structure and tectonics of Krishna Godavari Basin revealed from seismic attributes and other geophysical data.
Okay, that is Satyen Kumar.
Yes, sir, I am there, sir.
Yeah, a question for you. You can ask.
Please, sir.
Satyendra ji, can you please in one of the slide you have shown some host graben feature by superimposing your seismic data and the conceptual model.
Yes, yeah, please, Abhishek ji, can you please launch that?
No, it is not possible to display this presentation.
Can you? Yeah. So what I feel that it's my observation that rather instead of calling it as a host graben feature, because you are seeing all those type of feature towards the slope. So according to the seismic data that you have displayed, what I observed is that these are equispaced canyons that have intersected the slope.
Canyon type features.
No, it's not canyon type features. These are equispaced canyons. So we should not demarcate them as host graben features.
Okay, actually these are the 2D lines. So we can, if we have more other profiles also, then we can clearly validate this because I have chosen only just the anomalous one profile. So parallelly along with the 2-3 profiles or 3D seismic data, if it is there, then we can clearly shown this type. It is possible. Yeah, it may be. Sure.
Yeah, because I mean, Professor Uma Shankar also might agree to this point because
thank you very much.
We cannot say those as host graben structures. Rather, those are we see from seismic data. Those are all canyon cuts. What we observe close to the slope.
Yes. Because 2D line only we can see 1D type of structure like dipping and upwarping, dipping or working. So if we have some other lines also, then we can make some continuity and this channels type structure, it can be enhanced. Yeah, it is possible. Yeah, I will see that. I will see another profiles also. Thank you very much for your nice comment.
Yeah, thank you. Thank you. Thank you.
Oh, okay, thank you very much. I have a question to Jyotsna. Is there? Jyotsna?
Yes, sir.
Yeah, you are there.
Yes, sir.
Can you just put a light on that? How salinity can responsible for the landslide?
Okay, sir, salinity is not the direct indicator of landslide here. First, the gas hydrate will dissociate. Further dissociation, the salinity is a primer for dissociation. In such a way that
This is a basically indicator of dissociation of the gas hydrate, not the responsible. This parameter is not responsible for the that landslide and other things directly.
not directly, sir. It's indirectly. Like due to the dissociation, we are seeing slope breaks on the seafloor. And that's how in the bathymetry map, we are seeing the, those slope failures in the bathymetry map. So not directly, indirectly, we can say.
So once gas hydrate dissociated, then what is the effect of salinity, dissociation of gas hydrate?
Okay, the increasing salinity is stopping the further gas hydrate formation, sir, in the subsurface. So
salinity, it means salinity increase the gas hydrate depth should be increased or decreased?
It will showing upwards, sir. It will decrease actually.
Decrease.
Yeah.
Okay.
Yeah. Then there will be a difference in the temperature and pressure conditions, and it will go out of the stability zone.
Yes.
That's how the gas hydrate will dissociate.
So this is not direct relation with the avalanche and any kind of landsliding phenomena.
No,
Okay.
sir. No, it is not. Yeah.
So any some more questions to the presenter?
Sir, I have a question for Utsav. Utsav, are you here?
Yes, ma'am. Yes.
Yeah, Utsav, thank you for your presentation. Actually, this was a good attempt on the resistivity data set. Already, what I understood is you are trying to further decrease the dimension quotient, and you are trying to reduce the inhomogeneities in this near surface data sets of resistivity, because your elevation was not very high. It was even less than 100 meters.
No, ma'am. No, ma'am. Actually, when we train our deep neural model, we give them array, and array are the pixel values of the image. Okay. So what happens when we have, like, for in case of synthetic data, we have only like background resistivity, and then we have one anomaly, which is a rectangular block or anything. So, but when we create a pseudo section, we have like interpolation and all those pixels. So there is a too much repetitive data in that array. When we plot that thing into a RGB space, we see a huge dimension. So what happens? These techniques reduces this like k-means, makes clusters, because training set always takes data in form of array pixels. So we can always align our pixels in like k-means clustering. We can align the clusters into like in our work, it has aligned the whole space into 4 clusters only. So it is a process of removing redundant information.
That I understood, but I am still trying to find out the scientific interpretation which you are trying to deduce on the real data set. So how this process of reducing dimensionality will add up to the interpretation of near surface inhomogeneities or the layers?
That we need to check, because when we further after the training, when we import the results out of it from the model, when we generate the result in the form of pseudo section, so that we need to evaluate how much change actual is happening from the original model. That we need to check.
Yeah, because RMS error wise also there is not much difference. So if there is a drastic difference, change reduction in error wise, then this technique may be really helpful. So it will be interesting to see this application of this technique on real data set. So here you have shown only the synthetic resistivity, So
Definitely, ma'am. And we are planning to increase the number of data to 30,000, 40,000. And then we can see that how that overfitting and all those problems are resolving using these techniques. Plus, we are planning to check it on the real data set. So these are the, this is the preliminary work results we have obtained.
yeah, so I would be interested to see the results when you will be applying it on the real data set. So
Sure,
that will be really good.
Definitely.
Okay.
Thank you so much.
Thank you, sir. Chairman, sir, so over to you now.
So, some other questions? If not, then I hand over to Walia, sir, because we are going to wind up then this session because it's too late.
Yeah, there can be a short report by the rapporteur if he is around.
Yes, sir.
Would you like to say a few words?
Yes, sir.
Yeah, please.
Good evening, everyone. Here I have concluded a brief review report on today's technical session 8. First of all, I would like to thank Chairperson Dr. Uma Shankar, Professor BHU, Co-Chair Dr. Tanvi Arora, Scientist NJRI, and of course Professor Devesh Walia. In the present session, total 28 poster presentations were scheduled. That is related to atmosphere, space and planetary science, marine geoscience, and solid earth geoscience. Surprisingly, we don't have any participant from the atmosphere, space, and planetary geoscience. So out of these, we have total 15 participants present their work. The sessions was start from the marine geoscience. The first poster was presented by the Abhilash, based upon a statistical study of the earthquake of mid-Indian Ocean Ridge. D. Haritha presented a poster on a convolutional bidirectional LST network for generations of missing well log data. Josna presented a poster on gas hydrate dissociations in a Krishna Godavari basin. Satyendra Singh presented a poster on a structure and tectonic of Krishna Godavari basin, offshore basin as a revealed from the seismic attribute and other geophysical data. Varsen present a poster on comparative diagenetic analysis of shallow and deep-seated gas hydrate system from the Bay of Bengal. In a section of solid earth geoscience, the first poster was presented by the Abhishek Kundu based upon seismotectonic of the intending northeast corner of the Indian plate. The next poster was presented by the Bhaskara based upon SN wave and VP by VS tomography of the uppermost mantle beneath the Indian shield. And next poster was presented by B. Dalai based upon a fully unsupervised deep learning approach for denoising the converted wave seismic data. Next poster was presented by Chinmay Helder based upon crust and upper mantle beneath the Kiteshwar region of Northwest Himalaya. Gaurav, they present a poster on a spatial B-value variation and hazard analysis in the Indo-Burma range. Al Manjula present a poster on geomagnetic variation of geomagnetic conjunction site for the Indian sector. Next poster was presented by Jyoti Priya Sharma based on copper mineralization in the North Delhi fault belt. NN Chakravarti present a poster on the role of the pre-evaporative tectonic structure in the occurrence of seismic swarm activity in the Palgad regions based on magnetotelluric studies. Utsav Mishra presented a poster on the application of the dimensionality, the reductions and image compression on ERT dataset. And the last poster was presented by G. Govind based on predictions of groundwater level change from the precipitation data. So on behalf of all the committee members, I would like to thank everyone for their informative talk, and thank you.
Yeah, thank you for excellent report, Abhishek. And with this, we have come to an end of today's program. And I would like to thank Professor Uma Shankar and Dr. Tanvi Arora who have helped us in conducting this program, this session of IGU, and Abhishek for to be the rapporteur. So with this, I think there is. Is there any announcement for tomorrow?
No, we don't have any.
Only for the participants. just to remind you that tomorrow 9:40 the session will start with very good presentation, invited talk, as well as the award talk by Dr. Anil Kumar, and that talk is IGU Dr. J.G. Negi Young Scientist Award, and he'll be talking on aggradation, incision, and paleohydrology from the Indus River, Ladakh, Himalaya. So it is going to be very exciting, very good talk. So please take out time to be there with us from 9:40 sharp. Tomorrow, our sessions will end by 2:15, by 2:15, and after that we'll have around 40 minutes valedictory program. So, so by 3 you will be free. So please take out time to be there with us tomorrow sharp at 9:40. The talk will be of 15-20 minutes, and after that the last 2 sessions will be there. So thank you everyone for being with us. Thank you once again, Professor Uma Shankar and Dr. Tanvi and Abhishek.
Thank you, sir. Thank you very much.
With us.
Yeah, thank you, sir. And also, I want to say thanks to the man behind the show who has been running all the posters on time. And
very important.
Yeah, so I don't know what's his name. I think it's Abhishek.
You can just yeah, he's the one. We can see his photo.
Yeah, so he's very prompt and
Dr.
very
Shekhar.
Okay.
Constantly guiding through and managing and receiving, and so many communications are on back channel.
Yes.
So many people are asking so many questions. Most of the questions are of less relevance, but he is replying to all of them constantly. So thank you, Dr. Shekhar, to be there in the background. I thought that maybe tomorrow we'll thank you, but Madam reminded us informally, formally. We are very much thankful to you for managing
the
whole show, guiding through the whole show.
He's doing he's doing top job with ease.
Yeah. Arey, sir, you are also there. We would like to request all those who can switch on their video so that we can have one photo, one pic right now. Those who can, Utsavji, Vinod, Jyoti, Haritha, all those who can switch on your video, and let us click one or two pics so that all of those for whom it is possible, please switch on your video. It will be not more than 1 minute. Time won't take. Meghali, if you are there, you can switch on. Anand, Akilan from Vadia Institute, Sonia, whomsoever is possible. Names which are appearing in black, I am reading those names only. So if possible, please switch on your video so that you can be captured. Yeah, still some of you, they are moving or something. Dr. Meghali, Anand, Akilan, if you can switch on your video. Yeah. So hopefully, because it is being recorded also live, so your video is getting recorded not only here by a snapshot, but also on the YouTube. So with this, I think Prasad Saab is there. So on behalf of IGU, I would like to thank you all, those who have switched on your video and who are there with us for the program. Yeah, thank you once again to all of you.
Thank you,
bring Prasad Saab also on the forefront. Now he wants to say something.
No, it's okay. My special thanks to Dr. Uma Shankar and Dr. Tanvi Arora and Abhishek.
Thank you, Guru. How are you?
Fine, thank you.
Thank you, sir.
Thank you,
sir. So tomorrow again at 9:40 sharp. All right then. Thank you, everyone.
Yes, sir.
Okay,
thank you for being with us.